The question of whether everything we know started from nothing strikes at the very core of our understanding of the universe. For as long as humanity has existed, the origins of the cosmos have been a topic of fascination. From ancient philosophers pondering the concept of nothingness to modern scientists seeking clues scattered across the stars, the quest to uncover the true nature of the universe's beginning is one that has captivated minds for centuries. But how did it all start? Was there a moment when the universe emerged from nothingness, or is there more to the story than we can imagine? In cosmology, the term universe encompasses every particle of matter, every star, every galaxy, and the vast, seemingly infinite stretches of empty space between them. It is the sum of all known existence, including all forms of energy, the fundamental forces that govern them, and the very fabric of space and time itself. Think of the universe as an immense tapestry, intricately woven from countless threads, each one a galaxy, each one a cosmic structure, all interconnected. Yet the universe is more than just the physical objects we can observe. It stretches beyond the limits of our telescopes, far beyond what we can currently see, extending into regions of space so distant that light has not yet had time to reach us. These are the parts of the universe that remain hidden, invisible to our understanding, perhaps forever out of reach. But the universe is not static. It is a living, breathing entity, expanding ever outward since the Big Bang, a monumental explosion that marked the beginning of both space and time. Since that moment, the universe has stretched and grown, galaxies slowly drifting away from each other as space itself continues to stretch. The expansion of the universe is not merely a visual phenomenon, but a profound reflection of its underlying dynamism. Yet, within this vast and seemingly infinite universe, there are phenomena that still challenge our understanding: dark matter and dark energy. Dark matter, invisible and undetectable through conventional means, does not emit light or energy. Yet it exerts gravitational forces that influence the structure of the cosmos. Dark energy, meanwhile, seems to drive the accelerated expansion of the universe, pushing galaxies farther apart at an ever-increasing rate. Understanding the universe involves piecing together the cosmic puzzle, exploring its history, structure, and the fundamental forces that shape its behavior. Over time, our knowledge has grown, and we have come to recognize the universe as a vast, complex system governed by principles far beyond what we could have imagined just a few centuries ago. But the story of the universe is not just written in the stars. It is also shaped by the way humanity has interpreted the cosmos throughout history. Across cultures, the sky has been a source of wonder and meaning. Ancient civilizations crafted rich mythologies and cosmologies to explain the mysteries of the heavens. In Mesopotamia, for instance, the night sky was seen as a canvas, a realm where gods and goddesses played out their dramas. These celestial bodies were not just distant stars, they were integral to the lives of the people on Earth, with their movements influencing everything from politics to agriculture. The ancient Egyptians, too, imbued the stars with sacred significance. They constructed pyramids aligned with the stars, reflecting their belief that the heavens were a gateway to the afterlife. The appearance of certain stars, such as Sirius, was closely linked to the flooding of the Nile River, which was crucial to their agricultural cycle. In China, the cosmos was understood as a grand harmony, a delicate balance between opposing forces, encapsulated in the idea of yin and yang. The stars and planets were part of this greater balance, reflecting the cyclical nature of life itself. Similarly, Native American cultures developed their own rich cosmologies, seeing the sky as a living entity with constellations that told stories of animals, heroes, and spirits. The stars served as bridges between the earthly realm and the spiritual world, offering wisdom, guidance, and moral lessons. In contrast, Western traditions evolved in a more scientific direction, like beginning with ancient Greek philosophers such as Aristotle. Their models of the universe, though mythological at times, laid the groundwork for the scientific inquiry that would follow. By blending observation with reason, figures like Ptolemy and later Copernicus and Galileo shifted humanity's view of the universe, helping us to transition from mythological explanations to those based on empirical evidence and logic. These shifts in perspective, though disparate in their origins, all reflect a shared curiosity about the cosmos, a desire to understand the forces at play and the purpose behind it all. Each of these perspectives, rooted in their respective environments and cultures, offers a unique insight into how different societies have approached the mystery of existence. Whether driven by spiritual beliefs, philosophical musings, or the desire for scientific understanding, humanity's exploration of the universe has always been deeply intertwined with our search for meaning. These stories are not merely explanations of the stars above. They are reflections of our deepest desires to understand our place in the cosmos, to make sense of the world around us, and to seek wisdom that might guide our actions and choices. The origin of the universe, as a question, is one that bridges both science and philosophy. It probes not only the mechanisms behind the physical processes that led to the universe's formation, but also the deeper questions of existence itself. At its core, this question asks, where did everything come from? What is the nature of the cosmos that we inhabit, from the smallest subatomic particles to the largest galaxies? Science, with its theories and models, provides us with possible explanations for the universe's birth, while philosophy invites us to consider the meaning behind these explanations, the cause of the cause, and whether there is a greater purpose to it all. From a scientific standpoint, the Big Bang Theory offers the most widely accepted explanation for the origin of the universe. According to this theory, the universe began as an incredibly hot, dense point roughly 14 billion years ago. This singularity, this infinitely small and compact state, exploded in a rapid expansion that set the stage for the creation of everything we know today. The universe began as an energetic mix of particles and radiation, cooling over time, allowing for the formation of atoms, stars, galaxies, and eventually the complex structures that fill the cosmos today. This theory is supported by several key pieces of evidence. One of the most compelling is the discovery of cosmic microwave background radiation, which scientists interpret as the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe shortly after its formation, offering a glimpse of its state just moments after the event. Another piece of evidence is the observed redshift of galaxies. When we look at distant galaxies, we find that their light is shifted toward the red end of the spectrum, indicating that they are moving away from us. This expansion suggests that at some point in the past, everything in the universe was concentrated in a singular, incredibly hot and dense state. The further away a galaxy is, the faster it appears to be moving away, leading scientists to trace this expansion back in time to the moment of the Big Bang. This observation is supported by the abundance of light elements in the universe, particularly hydrogen and helium, whose proportions match predictions made by the Big Bang Theory. The large-scale structure of the universe, the way galaxies are organized into clusters and filaments, further corroborates the Big Bang model. Computer simulations that model the evolution of the universe from a hot, dense state predict that matter would clump together over time to form the intricate web-like structure we see today. Observations of the universe's structure align perfectly with these predictions, reinforcing the idea that the Big Bang was the event that set the universe into motion. The concept of the Big Bang Theory, first proposed in the early 20th century, was initially sparked by observations of distant galaxies moving away from us, a phenomenon that led to the realization that the universe was expanding. Belgian physicist Georges Lemaitre, in the 1920s, suggested that the universe had begun as a primeval atom, containing all the matter and energy that would later form the cosmos. This idea was later refined by Edwin Hubble, whose observations in the 1930s confirmed that galaxies were indeed receding from us at speeds proportional to their distance, providing strong evidence for the expansion of the universe. Further developments, including the discovery of cosmic microwave background radiation, confirmed that the universe began from an incredibly hot, dense state, making the Big Bang Theory the leading explanation for the universe's origins. The Big Bang, as described by scientists, wasn't just a simple explosion. It was the birth of time and space themselves. Everything we know, the laws of physics, the fabric of space-time, and the very matter that makes up the stars and planets, emerged from this single moment of immense energy and potential. Over billions of years, this energy cooled, allowing the first atomic nuclei to form, setting the stage for the creation of stars and galaxies. The process of nucleosynthesis, when the first atomic nuclei formed, was one of the first steps in the universe's evolution, leading to the creation of the elements that would eventually give rise to planets, life, and everything we know. As we look to the stars and ponder the question of where everything came from, we are reminded not only of our scientific understanding of the cosmos, but also of the philosophical questions that have shaped humanity's journey. The origins of the universe are not just about understanding how stars are born or how galaxies form. They are about understanding our own place within this vast, ever-expanding universe. The question of whether everything started from nothing may be one that remains unanswered for now, but it is a question that continues to drive us to explore, to seek, and to understand. The universe in its early stages was a place of extreme conditions, too hot for atoms to form or hold together. This primordial heat kept the universe in a state where light could not travel freely, being trapped in a dense, opaque fog of particles and radiation. However, this situation would change dramatically, and it wasn't until about 380,000 years after the Big Bang that the universe had cooled enough for a significant transformation to occur. At this pivotal moment, the temperature dropped sufficiently for electrons and protons to combine, forming neutral hydrogen atoms in an event known as recombination. This moment is not just a simple cooling of the cosmos, it marks the birth of transparency in the universe. For the first time, light could travel freely through space, no longer impeded by the hot, dense medium. The release of this light is what we now observe as the cosmic microwave background radiation, or CMB. This faint, ubiquitous glow still permeates the cosmos today, providing us with a snapshot of the universe in its infancy, a mere 380,000 years old. Imagine the universe then, a place of swirling chaos, immensely hot, dense, and filled with energy. Over millions of years, this radiation, this faint glow, has traveled across the universe, preserving a memory of its early state. Scientists today, using incredibly sensitive instruments, can detect this faint glow, offering us a glimpse into the past, into the universe when it was an infant, unrecognizable from the vast cosmos we observe now. In the aftermath of this cooling, gravitational forces began to take hold, slowly pulling matter together, ultimately forming the first stars and galaxies. This marked the beginning of structure in the universe, the formation of the building blocks of the vast, complex cosmos that we know today. Each step along this journey, from the primordial soup of particles to the formation of the first stars, was a crucial chapter in the cosmic story. These formative moments created the necessary conditions for the formation of planets, stars, and, eventually, the complex structures that would give rise to life. The CMB, the cosmic microwave background, is not just a relic of the past. It serves as one of the most important pieces of evidence in supporting the Big Bang theory. To truly grasp its significance, one must imagine the universe shortly after its birth, approximately 13.8 billion years ago. During those first moments, the universe was an extraordinarily hot and dense place. As it began to expand, it began to cool, leading to dramatic shifts in the state of matter. The moment when electrons and protons first combined to form hydrogen atoms was not merely a chemical reaction. It marked the transition from an opaque, light-trapping universe to a transparent one. The light released in that moment, the CMB, is still detectable today. This radiation fills the universe uniformly, casting a faint glow that offers us a snapshot of the universe at its infancy. It's a cosmic photograph, taken not with a camera, but with radiation itself. The CMB provides a wealth of information about the early universe. By analyzing this faint radiation, scientists can infer vital details about the universe's age, composition, and rate of expansion. Even more importantly, subtle fluctuations in the temperature of the CMB correspond to variations in density in the early universe. These density fluctuations were the seeds from which galaxies, stars, and all of the structures we observe today would later grow. The CMB acts as a fingerprint of the universe's early days, providing an invaluable tool for understanding how the universe evolved over billions of years. A key idea in understanding the origins of the universe lies in the notion of quantum fluctuations. At first glance, this might seem like an abstract concept, but it offers critical insights into how the universe could have emerged from an apparently empty void. To grasp this, imagine a perfectly calm, empty space, nothing but vacuum. According to quantum mechanics, however, even this vacuum is not truly empty. At the smallest scales, it is alive with activity, with particles spontaneously appearing and vanishing in what seems like an imperceptible dance. These seemingly fleeting appearances are not random. They suggest that even in the emptiest of voids, there is potential energy, just waiting for the right conditions to manifest into something more substantial. Quantum fluctuations might very well have been the catalyst for the universe's creation. In this context, nothing is not truly nothing. Rather, it is filled with a potential energy waiting for the right moment to coalesce into existence. Imagine these fluctuations as ripples in a vast ocean of energy. In this quantum sea, it's as if tiny, transient disturbances could become stable, evolving into particles and eventually into the matter and energy that form stars, galaxies, and everything else in the universe. Thus, the universe could have emerged from a fluctuating, energetic void, a sea of potential that churns beneath the surface of what we perceive as nothingness. This brings us to the fascinating Heisenberg uncertainty principle, a fundamental concept in quantum mechanics that captures the inherent unpredictability of the microscopic world. The principle states that it is impossible to simultaneously measure both the exact position and momentum of a particle with absolute precision. It's akin to trying to track a tiny, erratic insect flying in a dimly lit room. The harder you try to pinpoint its exact location, the more uncertain its speed becomes. This principle is not just a quirky aspect of quantum mechanics, it fundamentally reshapes our understanding of the universe. At the quantum level, particles don't behave like solid objects. Instead, they behave more like waves, and these waves can fluctuate in and out of existence. These quantum fluctuations are brief moments when energy levels in what seems like empty space shift momentarily, creating pairs of particles that spontaneously appear and then disappear. This behavior is not a theoretical curiosity, but a crucial element in many physical processes. For example, it is believed that quantum fluctuations played a pivotal role in the formation of the universe itself during the Big Bang. These fluctuations in the energy of the early universe could have led to the creation of the large-scale structures we see today. In this sense, quantum mechanics doesn't just govern the behavior of tiny particles, it may have also laid the groundwork for the universe itself. The uncertainty and unpredictability inherent in the quantum realm, embodied by the Heisenberg uncertainty principle, may well have played a fundamental role in the creation of our universe. In the quantum world, virtual particles play a unique and somewhat surreal role. These particles, which seem to appear and disappear in the vacuum of space, provide us with a deeper understanding of the nature of energy and matter. Virtual particles are not stable or long-lived. They exist only for the briefest of moments before vanishing. In the early universe, conditions were ripe for these virtual particles to emerge spontaneously. The incredibly hot and dense environment allowed for these fleeting particles to appear in the fabric of space, creating a dynamic and turbulent backdrop for the birth of the universe. These virtual particles can be thought of as the most basic units of energy fluctuation, and their behavior provides valuable insights into how the universe began. Imagine a universe that begins not with stable particles, but with these unstable virtual entities. These virtual particles could have had profound effects, leading to the creation of real particles. As the universe expanded and cooled, the balance between matter and antimatter shifted. Some particles survived the annihilation of their counterparts, leaving behind the matter that constitutes everything we see today. The dynamics of virtual particles were instrumental in this shift. The energetic fluctuations that created virtual particles were not just abstract phenomena. They played a key role in the formation of the very substance of our universe. The concept of the multiverse introduces an even more mind-bending idea. What if our universe is just one of many? What if there are countless other universes, some like ours, others vastly different, each with its own set of physical laws, constants, and histories? To understand the multiverse, imagine a vast library, its shelves filled with countless books, each representing a different universe. Some of these books might tell a story similar to ours, while others could describe entirely different realities, where time and space operate under different principles. This idea challenges our most fundamental assumptions about the nature of reality. The concept of the multiverse suggests that the Big Bang, which created our universe, could have been just one of many such events in a much broader framework. Perhaps the birth of our universe was simply one chapter in an ongoing story of universe creation, where each universe emerges from a fluctuating quantum state, similar to how our universe was born from the energetic fluctuations that occurred during the Big Bang. If true, this concept radically changes the way we think about existence, introducing the possibility of an infinite number of universes, each with its own unique set of physical laws and outcomes. Understanding the multiverse is not without its challenges, however. For one, the multiverse is incredibly difficult to observe. Since these other universes may not interact with our own, proving their existence using traditional scientific methods is nearly impossible. Furthermore, the concept of the multiverse raises the question of testability. In science, a theory is valuable when it can be tested and potentially proven wrong. Since the multiverse theory cannot currently be tested by any experiment or observation, it remains largely speculative. Some critics argue that without empirical evidence, the theory cannot be considered scientifically valid. Nevertheless, the idea of the multiverse challenges our conception of reality itself, prompting us to rethink the nature of the universe and its origins. It is a thought-provoking and deeply mysterious idea, one that opens up the possibility of infinite worlds, each as unique and complex as our own. This paradigm-shifting idea continues to captivate the imaginations of scientists and philosophers alike, urging us to ask profound questions about the universe, existence, and everything in between. The multiverse concept, while captivating the imagination and opening new horizons for exploration, can also act as a significant roadblock to scientific progress, especially due to its immense complexity. The theories supporting this idea, such as string theory and cosmic inflation, are intricate and difficult to grasp, even for the most seasoned researchers. These frameworks, though fascinating, are often abstract and hard to connect with observable phenomena. One of the main hurdles scientists face is the challenge of translating these esoteric ideas into something that can be empirically tested or confirmed. As a result, many researchers find themselves wrestling with how to move beyond abstract models and work towards something tangible that can be scrutinized in a laboratory setting. This complexity, however, is not limited to just scientific technicalities. The implications of a multiverse also touch on deep philosophical questions about reality and existence. These theories compel us to rethink our fundamental understanding of what is real, raising questions about our place in the cosmos and how we define the nature of existence itself. If there are indeed infinite or multiple universes, what does that mean for our own experience? How do we reconcile the idea of an ever-expanding set of realities with our deeply ingrained perceptions of the world we inhabit? These are questions that extend far beyond the realm of science and into speculative territory, where empirical verification becomes an elusive goal. The nature of truth itself comes into question, as we must now consider that what we know as real may only be one part of an unimaginable, ever-changing multiverse. This philosophical and scientific conundrum creates an environment ripe for debate. While the concept of the multiverse is undeniably fascinating, its validation or refutation remains an incredibly difficult task. It is not merely a matter of proving a hypothesis, but of addressing profound questions that touch upon the very nature of reality, existence, and the universe's origin. These questions intertwine with intricate scientific theories, each adding layers of complexity that resist easy resolution. Thus, the multiverse remains an intriguing yet challenging idea, one that pushes the boundaries of both science and philosophy. On the other hand, the concept of the universe emerging from nothing offers a different yet equally profound perspective on how gravity fits into our understanding of the cosmos. Imagine, if you will, the universe in its earliest moments, a blank canvas entirely devoid of matter and energy. From this nothingness, the universe somehow transformed into the vast and complex space that we now know. It is here that gravity, one of the fundamental forces of nature, plays a critical role in this transition. Gravity exists wherever mass is present, and its force shapes the very fabric of space itself. It may seem paradoxical at first to think of gravity arising in a state of nothingness, but quantum physics suggests that even in a completely empty universe, tiny fluctuations in the quantum field could lead to the appearance and disappearance of particles. These fluctuations, like ripples on a blank canvas, could be seen as the first hints of structure in an otherwise empty universe. Once gravity comes into play, its immense force begins to pull together these tiny particles, eventually forming clumps of matter and energy. This process marks the beginning of the formation of stars, planets, and galaxies. Without gravity, these particles would have dispersed, and the formation of structure in the universe would have been impossible. In this sense, gravity not only challenges the idea of nothing by requiring particles to exert force upon, but also supports the notion by bringing organization and structure to the universe, transforming it from a state of emptiness into the complex reality we observe today. This dynamic interplay between gravity and matter suggests a potential pathway through which nothing becomes the fertile ground for creation. Gravity provides the mechanism that turns the absence of matter into the very substance of existence, shaping the universe from a non-existent state into the vast, structured cosmos we inhabit. It invites us to reconsider our understanding of nothingness and ponder whether the true essence of nothing is not emptiness, but rather a latent potential for something to arise. Through the lens of gravity, nothing becomes a complex and dynamic state filled with the possibility of creation, waiting for the right conditions to manifest into a tangible reality. One of the most intriguing theories that tries to understand the universe's inception is loop quantum gravity. This theory challenges the traditional view that space and time are smooth, continuous entities, suggesting instead that they are made up of tiny, indivisible units, much like matter is composed of atoms. In this framework, the fabric of space-time is not a continuous, flowing entity, but is woven together from discrete loops, forming a kind of network that operates on a quantum scale. This approach offers a radically different perspective on the universe's beginning, particularly when compared to the Big Bang theory, which traditionally posits that the universe originated from a single, infinitely dense point. Loop quantum gravity offers an alternative narrative. Rather than a singular explosion from a point, the universe may have undergone a series of events in which the compression of space reached a critical limit, causing a bounce rather than a collapse. Think of it like inflating a balloon. As the balloon expands, it reaches a point where it cannot stretch any further without bursting. Similarly, in loop quantum gravity, as the universe contracted under its own gravity, it would eventually reach a critical stage where it couldn't collapse any further, leading to a rebirth, a big bounce. This bounce would then mark the transition from contraction to expansion, setting the stage for the universe we observe today. This theory has the advantage of challenging the notion of singularities, places where density and gravity become infinite, as proposed by the traditional Big Bang model. In the loop quantum gravity view, the laws of physics would remain intact even at the most extreme points, allowing for a smooth transition between different states of the universe. This offers new hope for understanding the origin of the cosmos while avoiding the paradoxes and limitations of singularities. It also opens the door for further exploration into the nature of reality itself, prompting scientists to reconsider our fundamental understanding of time, space, and the universe's birth. String theory, another prominent framework in theoretical physics, provides an even more profound perspective on the universe's origin. In this theory, the fundamental building blocks of reality are not tiny particles, as we might imagine, but rather one-dimensional objects known as strings. These strings vibrate in different modes, and the way they vibrate determines the properties of the particles they produce, such as mass and charge. String theory goes even further, suggesting that prior to the Big Bang, our universe existed in a different form, perhaps as a brane, short for membrane. A brane is a higher dimensional surface upon which strings reside, and it is believed that a cataclysmic event, such as the collision of these branes, could have triggered the Big Bang. The universe is not a simple point of explosion, but a complex interaction of higher dimensional objects and forces. The collision of these branes could have caused an immense release of energy, sparking the expansion of our universe. String theory suggests that our universe could be just one of many, with each universe existing on its own brane. This collision theory implies that the universe is far more intricate and multidimensional than we previously imagined, with the cosmos as we know it being the result of highly complex and interwoven forces, still filled with mysteries that we have yet to fully understand. String theory also offers a different perspective on the nature of nothing. In this framework, nothing is not merely an empty void, but rather a complex and dynamic landscape of potential. Rather than being a simple absence, nothing in string theory is a state filled with constantly fluctuating strings and energy. Even in what appears to be empty space, there is constant activity and interaction at the quantum level, suggesting that nothing is never truly devoid of content. This idea revolutionizes our understanding of emptiness, showing that what we perceive as nothing is actually a vibrant and dynamic state, teeming with potential for the creation of reality itself. The concept of branes in string theory further enhances our understanding of the universe's structure. In this theory, branes are like higher dimensional sheets floating in a cosmic ocean. These branes can take many forms, stretching across multiple dimensions and interacting with each other in ways that produce profound implications for the origins of the universe. When two branes come into close proximity or collide, it could trigger the creation of a new universe, similar to how a spark can ignite a fire. This collision could release an enormous amount of energy, leading to the formation of a new universe, each with its own unique properties and laws. Every collision could give rise to a new universe, continuously expanding the multiverse and creating an endless number of realities. Philosophically, the idea of the universe emerging from nothing challenges our deepest concepts of existence and causality. The traditional notion of causality posits that everything that exists must have a cause, but if the universe began from nothing, this idea seems to defy our everyday experiences of cause and effect. Some philosophers, like Aristotle, believed in an eternal universe, one that always existed, while others argue that there must have been some form of initiation, perhaps from nothing itself. This debate raises profound questions about the nature of nothingness and whether it can truly exist as a void, or whether it is always somehow bound to give rise to something. Furthermore, if the universe can emerge from nothing, what does that say about the deeper layers of existence that we have yet to understand? Could there be more universes, hidden from our view, that fluctuate in and out of existence? The concept of a first cause also plays a central role in these discussions. Philosophers such as Thomas Aquinas propose that there must be an initial cause, a prime mover, that set everything into motion. If the universe began from nothing, could this nothing be the cause, or is there something else that initiated the creation? This line of thinking invites us to reconsider the fundamental questions of existence and the origins of everything we observe. Contemporary discussions, particularly from atheistic viewpoints, suggest that the universe could have arisen spontaneously from quantum fluctuations. This challenges our traditional understanding of nothingness and raises intriguing questions about the role of probability and chance in the creation of reality itself. Thus, the mystery of the universe's origin invites both scientific and philosophical exploration, pushing the boundaries of what we know and what we believe about the very nature of existence. At the heart of every philosophical debate lies a persistent yearning to grasp the profound questions about the nature of existence, the mysteries of reality, and the very essence of the universe itself. These intellectual discussions, as complex and layered as the cosmos they seek to understand, constantly beckon us to delve deeper into the unknown. We are compelled to confront timeless questions. What is the nature of our existence? Why does the universe exist in the first place, and what does it mean to be here? The mystery of the universe's origin is an enigma that seamlessly blends science and philosophy. It is an invitation to explore and reflect on the fundamental concepts that shape the reality we inhabit, pushing the boundaries of human understanding. Existential philosophy, in particular, provides a compelling lens through which we can examine the very concept of the universe's origin. It invites us to consider the notion of ex nihilo, creation from nothing. This philosophical framework emphasizes human experience, the quest for meaning, and the search for freedom in a universe that may appear indifferent to our existence. At its core, existentialism wrestles with the paradox of meaninglessness and absurdity, raising challenging questions about whether the universe's origins are purposeful or arbitrary. If we are to accept that the universe emerged from a state of nothingness, we are faced with a concept that goes beyond the physical understanding of nothing. The term nothing here does not simply refer to the absence of matter or energy, but to an absolute void, devoid of any structure, purpose, or even potential for existence. To imagine the universe as arising from such an inconceivable state is to confront the absurdity of existence itself. After all, if the universe was birthed from this total nothingness, it bears no inherent meaning, structure, or rationale. This absence of purpose forces us to ask, why is there something rather than nothing? How can we make sense of our place in a universe that may not have been created for any reason at all? The very notion that the universe emerged from an empty void compels us to reflect on our own existence. As we face the unexplainable, the idea of nothing becomes a gateway for exploring existential themes. It challenges us to confront our feelings of isolation in a vast, uncaring cosmos. The reality of our existence, devoid of any obvious, predetermined meaning, often evokes a sense of existential dread, a recognition that life itself is fragile, fleeting, and in some ways, arbitrary. Yet, paradoxically, this recognition can also offer a sense of liberation. If the universe is truly indifferent to our existence, then perhaps we are free to create our own meaning. It is not the cosmos that dictates our purpose, but the individual, who must take responsibility for the choices they make. In this light, existential philosophy challenges us to abandon the search for answers from the universe and instead focus on our personal experience and choices. It is through these experiences that we find our way and create meaning, even in a world that came from nothing. This perspective fosters a deep sense of empowerment, reminding us that we have the freedom to define ourselves. It compels us to live authentically and embrace the uncertainty of our origins, recognizing that the quest for meaning is inherently personal. Despite the apparent randomness of existence, we are encouraged to find clarity and purpose in our individual journeys. The concept of creation ex nihilo, creation out of nothing, has fascinated thinkers for centuries. It's particularly within various religious and philosophical traditions. Each school of thought offers a unique approach, colored by its understanding of existence, the universe, and the divine. In the Judeo-Christian tradition, for instance, the idea of creation ex nihilo is central to the faith. It posits that a divine being, God, created the universe freely and purposefully from nothing, not from any pre-existing materials. This worldview places great emphasis on the sovereignty and creative power of God, presenting the act of creation as an intentional act that demonstrates divine will. For believers in this tradition, the universe's origin is an expression of God's absolute freedom and creativity. Creation is not a reaction to anything, it is a self-contained act of divine creation. Contrasting this, certain Eastern philosophies, such as those found in Hinduism and Buddhism, offer a radically different perspective. In these traditions, the notion of creation is often viewed through the lens of cycles rather than linearity. The universe is not seen as having a singular beginning, but instead as undergoing repeated cycles of creation, dissolution, and rebirth. Here, the concept of nothingness takes on a different meaning. Rather than representing a literal void, it is often associated with illusion or maya. The belief is that our perception of reality is ultimately impermanent, ever-changing, and insubstantial. In this cyclical view, the universe's origin is not a single event, but part of an ongoing process where the boundaries between existence and non-existence are fluid. The ancient Greek philosopher Plato, too, offered his own understanding of creation, though it diverged from both the Judeo-Christian and Eastern perspectives. Plato viewed reality through the concept of forms, which were idealized, abstract representations of all things. For Plato, creation did not emerge from nothing, but rather involved the ordering of pre-existing chaos into a structured cosmos. Reality, in his view, was not simply about material existence, but was rooted in a higher, abstract realm of perfect forms. The physical universe was a mere reflection of these timeless, unchanging ideals. In more modern secular philosophies and metaphysical discussions, some thinkers argue against the idea of creation ex nihilo altogether. They suggest that the universe may have always existed in some form, rather than having been created at a single point in time. The concept of infinity plays a crucial role here, as the universe could be seen as eternal, uncaused, and ever-present, stretching infinitely into the past and future. For these philosophers, the universe does not need a singular origin, but is instead a continuous, self-sustaining entity that has always been. This perspective challenges the very concept of a beginning and forces us to rethink our understanding of time, causality, and existence itself. Each of these philosophical perspectives adds layers to our understanding of existence and the nature of creation, enriching our exploration of the universe's origins. Together, they prompt us to reconsider what we know and challenge us to seek answers to the most fundamental questions about the cosmos and our place within it. As we probe these deep mysteries, we begin to realize that our understanding of the universe is shaped not just by empirical observation, but also by the stories we tell about its creation. These diverse worldviews encourage us to reflect on the profound complexities that lie at the heart of existence. One of the most captivating and mysterious concepts in modern cosmology is that of dark energy and dark matter, two phenomena that shape the very structure and fate of the universe. While we cannot observe these forces directly, their effects on the cosmos are profound and undeniable. Dark matter, for instance, makes up a significant portion of the universe's mass, though it is completely invisible to us. Dark matter functions like an invisible scaffold, exerting gravitational forces that help hold galaxies and galaxy clusters together. It behaves in ways that are not immediately perceptible, but provides the unseen structure that underpins the visible universe. To visualize dark matter, imagine the intricate threads of a spider's web, invisible yet crucial for holding the entire structure in place. Without dark matter, the universe as we know it would simply not exist in the same way. While dark matter plays a crucial role in shaping the universe's formation, dark energy operates on an even grander scale. Dark energy is the mysterious force responsible for the accelerating expansion of the universe. It pushes space itself outward, creating a form of cosmic tension that drives the universe's expansion. This force is thought to be a property of empty space, a kind of energy inherent to the very fabric of the cosmos. As the universe continues to expand, dark energy plays a pivotal role in determining its future, influencing how it grows over time. If we think about the early universe, at the moment of the Big Bang, it existed as an extremely small, dense, and hot point. During this period, rapid expansion occurred, and it is likely that some form of energy dominated this environment, energy that, over time, has come to be categorized as dark energy. In the context of quantum mechanics, true nothingness is an elusive concept, for even in a state of absolute nothingness, quantum fluctuations can occur, causing energy to spontaneously appear and disappear. These fluctuations may have set the stage for the birth of the universe, providing the seeds for the expansion and development of everything we observe today. As the universe expanded, dark matter and dark energy continued to play crucial roles in its evolution. Dark matter helped matter to clump together under the influence of gravity, leading to the formation of stars and galaxies, while dark energy counteracted this gravitational pull, driving the universe's expansion. Together, these forces shaped not only how the universe began, but also how it continues to evolve, guiding the growth of galaxies and structures within the cosmos. Without dark matter, galaxies might not have formed in the first place. Without dark energy, the universe could have collapsed in on itself. These forces are intimately connected, each influencing the other in profound ways. Yet, despite their crucial roles in shaping the universe's past, present, and future, dark energy and dark matter remain among the greatest unsolved mysteries in modern cosmology. Scientists continue to grapple with how to understand and measure these phenomena. One major challenge lies in the fact that dark energy does not conform to any established physical theories. It resists explanation, defying the current models of the universe. While the Big Bang Theory gives us a fairly good understanding of the early universe, it offers little insight into how dark energy emerged or how it began to influence the expansion of the cosmos. Another significant challenge is the difficulty of measuring dark energy's effects. Observing its influence requires incredibly precise data on cosmic distances and the rate of expansion of the universe. However, the vastness of the cosmos, filled with complex structures, makes such measurements exceedingly difficult. Even a small error in measurement can lead to dramatic misunderstandings about how dark energy operates and affects the universe's expansion. Despite these challenges, the pursuit of understanding dark energy and dark matter continues to be a central focus of modern astrophysics, as scientists strive to unravel the mysteries of the universe's origins and its eventual fate. Thus, the study of dark energy, dark matter, and the universe's formation serves as a powerful reminder of how much we still have to learn about the cosmos. The more we uncover, the more we realize how much remains beyond our grasp. Each new discovery offers another piece of the puzzle, but it also reveals just how vast and mysterious the universe truly is. In the end, these questions about the origins of the universe, the nature of existence, and the role of dark matter and dark energy are not just scientific queries. They are philosophical ones that challenge the way we understand our place in the cosmos. As we continue to seek answers, we are reminded of the ever-expanding mystery that is the universe itself. The mystery of dark energy, a fundamental force shaping the cosmos, continues to intrigue scientists and challenge their understanding of the universe. What makes it even more perplexing is its behavior, which appears to vary depending on the context. For instance, its influence on large astronomical scales seems to differ from its effects on smaller, more localized systems. This discrepancy complicates attempts to formulate a unified theory that can account for all of dark energy's interactions with other cosmic components, including galaxies, dark matter, and the very fabric of space-time. The variation in its behavior raises the question of how, or even if, it can be integrated into the established frameworks that currently govern the behavior of matter and energy in the universe. As it stands, constructing a theory of dark energy that is both comprehensive and consistent with observational data remains a monumental challenge. One of the main difficulties lies in the elusive nature of dark energy itself. To truly understand it, scientists must craft models that generate testable predictions, ideas that can be observed and measured against reality. Yet, dark energy remains so enigmatic that creating hypotheses that can be definitively tested is extraordinarily difficult. This uncertainty persists even as scientists delve deeper into the cosmos, continually attempting not just to identify the mechanisms at work behind dark energy, but also to formulate models that align with both empirical observations and our evolving understanding of physics. This relentless pursuit for clarity underscores the complexity of integrating dark energy into our broader understanding of the universe's origins. To do so, scientists must trace the universe's history back to its very beginning, a time when everything we know was compressed into a singular, infinitely dense point. The conditions during this early phase were far beyond anything we can conceive today. Think of a tiny, minuscule point packed with unimaginable amounts of energy. Then, in a fraction of a moment, this point began to expand at an astonishing rate in what we now recognize as the Big Bang. The initial expansion of the universe was not just a spatial phenomenon, it was the expansion of space itself. As this tiny, hot, and dense singularity exploded outward, space-time itself stretched. Much like the inflation of a balloon, the universe underwent rapid growth in its very first moments, altering the landscape of the cosmos in ways that continue to shape its structure. As this expansion occurred, the universe cooled rapidly, allowing the first building blocks of matter to form. Tiny particles such as protons and neutrons began to emerge, marking the first stage in the creation of atoms. The earliest elements, mainly hydrogen and helium, took shape as the temperature of the universe plummeted. In the aftermath of the Big Bang, the universe entered what is called the recombination epoch, roughly 300,000 years after the initial explosion. During this phase, the universe began to become less opaque as the dense, hot soup of particles began to cool and allow light to travel freely. The release of this light, now detectable as the cosmic microwave background radiation, serves as a faint but profound imprint of the very early universe. This radiation, a relic from that time, offers us a glimpse into the state of the cosmos shortly after the Big Bang, and it is one of the most powerful tools scientists have to study the universe's infancy. As the universe expanded and cooled, gravity began to assert its influence. Over millions of years, the force of gravity gradually pulled matter together, leading to the formation of the first stars and galaxies. These early cosmic structures began to form the intricate tapestry of the universe that we observe today, laying the foundation for the vast and complex universe we continue to explore. By studying this early period in the universe's history, scientists are slowly piecing together the story of everything, tracking its evolution from a singular point of creation to the diverse, structured cosmos that we now inhabit. The origins of the universe itself are most commonly described through the Big Bang theory, which posits that around 14 billion years ago, the universe began as an extremely hot and dense singularity. In a spectacular event, it rapidly expanded and began cooling, eventually giving rise to the simplest forms of matter. During the first few moments of the universe's existence, it was composed primarily of fundamental particles, quarks, electrons, and neutrinos. These quarks would later combine to form protons and neutrons, which in turn would make up atomic nuclei, the core of atoms. As the universe cooled, nuclear fusion allowed the creation of the first atoms, primarily hydrogen and helium. This process, which unfolded in the minutes following the Big Bang, marked the birth of the chemical elements that would go on to form everything in the universe, from stars to life itself. Simultaneously, the forces that govern the behavior of matter began to emerge. Gravity, electromagnetism, and the strong and weak nuclear forces all came into being, each shaping how particles interacted with one another. These forces are central to the structure and evolution of the universe, governing everything from the formation of stars to the interactions of fundamental particles. This foundational understanding is backed by a range of scientific observations and experiments. For example, measurements of the cosmic microwave background radiation, which offers a snapshot of the universe when it was just 380,000 years old, provide direct evidence of the conditions that prevailed in the early universe. This radiation serves as a powerful relic of the Big Bang, allowing scientists to reconstruct the universe's earliest moments and track the development of matter and energy over time. These observations support the theoretical models of the universe's early development and provide a solid foundation for understanding how the fundamental forces and particles emerged from the hot, dense state of the Big Bang. The theory of inflation, one of the most exciting developments in cosmology, explains how the universe expanded exponentially in the moments after the Big Bang. Imagine the universe as a balloon, initially tiny and tightly compressed. According to inflationary theory, in just a fraction of a second, the universe ballooned to an enormous size, expanding faster than the speed of light. This rapid expansion helped smooth out any irregularities in the early universe, leading to the uniform distribution of matter and energy that we observe today. Inflation also predicts certain patterns in the cosmic microwave background radiation, allowing scientists to measure and verify the early conditions of the universe. These patterns match predictions made by the inflationary model, providing strong evidence for this extraordinary phase of expansion in the universe's early history. As a result, inflation has become a crucial part of our understanding of the cosmos, offering a compelling explanation for the large-scale structure of the universe and its overall uniformity. Theoretical physicists use mathematics as a fundamental tool to explore the origins of the universe. This precise language enables them to describe the complex interactions of space, time, energy, and matter in the early universe. By applying equations derived from concepts like space-time and gravity, physicists can simulate the conditions of the universe mere fractions of a second after the Big Bang. These models allow scientists to test hypotheses and refine our understanding of the universe's earliest moments. One of the cornerstones of these models is general relativity, which describes how mass and energy bend space-time. This framework allows physicists to predict how the universe expanded, cooled, and eventually gave rise to galaxies and stars. However, understanding the behavior of particles in the early universe also requires the principles of quantum mechanics. The interplay between quantum mechanics and general relativity provides insights into everything from the formation of matter to the fluctuations in energy that occurred in the first moments of existence. By running simulations based on these frameworks, physicists can not only recreate the early universe, but also answer fundamental questions about why the universe is structured the way it is today. Yet describing a universe that begins from nothing presents its own set of challenges. First, we must define what we mean by nothing. In this context, nothing doesn't just refer to an absence of matter. It implies a state in which the very laws of physics as we understand them may not even exist. This makes it extraordinarily difficult to frame physical laws in such an environment, as the foundational principles upon which traditional physics relies, such as space, time, and energy, simply didn't exist in the way they do now. This lack of a defined framework raises fundamental questions about the nature of causality. In a universe where nothing exists, how can something emerge? Traditional concepts in physics depend on cause and effect relationships, but in the absence of anything, this sequence breaks down. This creates a significant challenge for physicists who attempt to apply mathematical models that depend on established quantities like energy or space-time. Without these quantities, the usual rules no longer apply, making it incredibly difficult to describe how the universe might have emerged from an initial state of nothing. Further complicating matters is the issue of singularities, points where certain physical quantities, such as density or temperature, become infinite or undefined. Singularities are central to cosmological theories, especially when describing the conditions at the moment of the Big Bang. However, mathematically speaking, infinities are problematic. They distort equations and lead to non-physical results, making it nearly impossible to apply traditional mathematical techniques to describe the universe's birth. Thus, the journey from nothing to something, the transition from a singular point to the vast, intricate universe we see today, poses both profound theoretical and practical challenges. Yet it is this very mystery that continues to drive scientific inquiry, as researchers strive to decode the deepest secrets of the cosmos. Through careful study, experimentation, and an unrelenting search for answers, humanity inches ever closer to understanding the profound origins of the universe, from its earliest moments to its present state and beyond. The quest to understand the universe's origin and its ongoing evolution is a journey into the very heart of reality itself, where science, philosophy, and imagination converge. This exploration begins with the mysterious and perplexing nature of quantum mechanics, which introduces an entirely new layer of complexity to our understanding. At the most fundamental level, particles can spontaneously appear and disappear in what is known as quantum fluctuations. These fluctuations challenge our classical notions of stability and being, suggesting that the universe itself could have arisen from such seemingly random occurrences in the fabric of space-time. However, accurately describing and modeling these fluctuations in mathematical terms proves to be no simple task. It requires not only an understanding of probabilities, but also a sophisticated grasp of the intricate interactions that take place on a scale far smaller than anything we can directly observe. The mathematical framework to address these phenomena is one of the most challenging aspects of modern physics, requiring advanced tools and techniques that push the boundaries of what we know. At the same time, when cosmologists attempt to build models that explain the universe's birth and evolution, they often employ advanced areas of mathematics, such as geometry and topology. The relationship between the shape of space and the dynamics of the universe presents profound challenges in formulating the necessary equations to describe these phenomena. This interplay between mathematics and physics reveals a universe that is far more intricate than our everyday intuitions allow us to imagine. Every approach to understanding the cosmos carries its own set of implications and paradoxes, each of which must be carefully resolved to construct a coherent theory of the universe's origin. When theorizing about a universe that may have sprung from nothing, scientists face immense mathematical obstacles, not the least of which include redefining fundamental concepts like space, time, and energy. Addressing the presence of singularities, grappling with the deep mysteries of quantum mechanics, and navigating the complexities of geometry all serve to deepen the mystery of our cosmic origins. Yet these challenges also highlight the incredible richness and profundity of our quest to understand the universe. The tools available to astronomers today allow us to gather valuable clues about the universe's beginnings. These tools combine observational data, theoretical models, and advanced technologies in a multifaceted approach to deciphering the secrets of the cosmos. One of the most critical pieces of evidence comes from the study of cosmic microwave background radiation. This faint, ubiquitous glow is the afterglow of the Big Bang, and it provides a snapshot of the universe's state just a few 100,000 years after it began. By analyzing this radiation, astronomers gain insights into the temperature, density, and structure of the early universe, offering a crucial window into the conditions that led to the formation of galaxies, stars, and other structures. Another key method for understanding the universe's beginnings involves the observation of distant galaxies and their movement. As the universe expands, galaxies are moving away from us, and the light they emit becomes redshifted, shifted toward longer wavelengths. By measuring this redshift, astronomers can determine the velocity at which these galaxies are receding, allowing them to estimate how long the universe has been expanding since its inception. This expansion provides strong support for the Big Bang theory, the leading explanation for the origin of the cosmos. However, observational evidence alone is not enough to provide a complete picture. To deepen their understanding, astronomers also rely on sophisticated computer simulations to recreate the conditions of the early universe. These simulations are based on our current understanding of physics and the known forces that shaped the universe's early development. By comparing the outcomes of these simulations with actual observational data, such as the distribution of galaxies and cosmic structures, scientists can assess the validity of their models and refine their theories about the universe's origins. In addition to these methods, the study of elemental abundances in the oldest stars provides another critical piece of the puzzle. Elements like hydrogen, helium, and lithium were formed in the early universe, and by measuring their ratios in ancient stars, astronomers can learn more about the processes that occurred during the universe's infancy. These measurements help reconstruct the timeline of the universe's expansion and evolution, allowing scientists to piece together a coherent narrative of how the cosmos came to be. By combining observational data, theoretical models, and cutting-edge technological advancements, astronomers continue to refine our understanding of the universe's birth and the complex processes that have shaped it over billions of years. The study of the early universe relies heavily on advanced technologies that push the boundaries of our knowledge. One of the most significant tools is the development of powerful telescopes designed to capture the faintest light from distant cosmic events that took place billions of years ago. These telescopes can observe radiation across various wavelengths, including infrared and radio, each providing unique insights into the formation of the first stars and galaxies. Observing in different ranges of the electromagnetic spectrum opens up new avenues for understanding how the universe began and evolved. Alongside these telescopes, the development of highly sensitive detectors has enabled the capture of cosmic microwave background radiation. This radiation, a remnant from the Big Bang, offers a snapshot of the universe in its early, hot, and dense state. By analyzing this faint glow, scientists can gain valuable information about the universe's composition, age, and evolution. Computational power has also played a critical role in advancing our understanding of the universe. Through the use of sophisticated simulations, researchers can create models that simulate the development of the universe from its earliest moments. These simulations allow scientists to test hypotheses about how matter and energy interacted in the infant universe, providing a clearer picture of how structures like galaxies and clusters of galaxies began to form. By visualizing complex processes that occurred over millions of years, scientists can deepen their understanding of cosmic evolution. Another breakthrough in modern astronomy is the detection of gravitational waves, ripples in spacetime caused by massive cosmic events, such as the collision of black holes or neutron stars. The ability to detect these waves has opened a new window into the universe, revealing events that would otherwise remain invisible to traditional telescopes. Gravitational waves carry valuable information about the most extreme and energetic events in the universe, providing insights into phenomena like the birth of black holes and the dynamics of stellar collapse. Space missions equipped with advanced instruments also play a vital role in our exploration of the cosmos. Specialized satellites can observe cosmic phenomena without interference from Earth's atmosphere, allowing for clearer and more precise measurements. These satellites are essential for studying the universe's origins, as they provide a more accurate view of distant objects and events. Through these cutting-edge technologies, scientists continue to piece together the puzzle of how the universe came to be, unlocking fascinating insights about its earliest moments and helping to shape our understanding of the vast and dynamic cosmos in which we live. When contemplating the origin of the universe, most of us naturally think of the Big Bang Theory, which describes the universe's birth from an incredibly hot and dense state. However, the landscape of cosmology is far richer, with several alternative theories proposing different ideas about how everything began. One such idea is the concept of a cyclic universe, in which the cosmos undergoes endless cycles of expansion and contraction. Imagine a balloon expanding until it reaches its limit, then deflating and collapsing back into a small, dense state. According to this theory, the universe could undergo a similar process, expanding to a certain point before contracting back into a hot, dense state, only to explode again in another Big Bang. This cycle could repeat infinitely, with time stretching infinitely in both directions, challenging the notion of a singular beginning. Another speculative idea is the concept of the multiverse, which suggests that our universe is only one of many. Rather than being the only universe, we could be part of a vast sea of bubble-like universes, each with its own set of physical laws and characteristics. Some of these universes might be similar to our own, while others could operate according to entirely different principles. The multiverse theory challenges our understanding of reality and raises intriguing questions about the nature of existence and the possibility of multiple parallel universes existing alongside one another. The holographic principle is another fascinating idea that has gained attention in recent years. This theory suggests that all the information contained within a given volume of space can be represented as a two-dimensional surface. In this view, the universe behaves like a hologram, with our three-dimensional experience of reality merely being a projection of information stored on a distant boundary. This concept blurs the line between what is real and what is an illusion, suggesting that the universe might not be as solid and tangible as we perceive it. Finally, quantum cosmology represents yet another speculative theory about the origin of the universe, one that incorporates the strange and counterintuitive principles of quantum mechanics. According to this theory, the universe may have emerged from a quantum fluctuation in a stable vacuum, akin to a tiny bubble popping into existence from nowhere. This concept implies that space, time, and the entire cosmos could have sprung into being from a fluctuation in the quantum field, giving birth to the universe as we know it. Each of these theories offers a unique perspective on the origins of our universe, revealing the complexity and mystery that still surrounds the fundamental questions of cosmology. Despite the wide acceptance of the Big Bang Theory, scientists continue to explore and question the very nature of the cosmos, seeking deeper understanding in the face of an infinitely vast and ever-changing reality. Cyclic models of the universe challenge our traditional understanding of creation from nothing, suggesting that the cosmos may not have had a singular beginning, but rather exists in an eternal cycle of birth, death, and rebirth. In these models, the universe undergoes repeated phases of expansion and contraction, each new Big Bang springing forth from the remains of the previous cycle. This vision of the universe as an eternal, cyclical process offers a profound rethinking of time, space, and the nature of existence itself. Instead of a one-time creation from nothing, the universe might be part of a grand, ongoing process that stretches infinitely in both directions. The evolution of the universe is an extraordinary tale that began approximately 13.8 billion years ago with the Big Bang. In that moment, all of space, matter, and energy sprang into existence, and the universe began its rapid expansion. This event, known as cosmic inflation, marked the start of a process that would lead to the formation of galaxies, stars, and planets. As the universe expanded and cooled, the most basic elements, hydrogen and helium, began to form. Over time, gravity caused these gases to clump together, leading to the formation of the first stars and galaxies. As these stars burned through their fuel, they produced heavier elements through nuclear fusion. When these stars eventually reached the end of their lives, they exploded in dramatic supernovae, scattering these new elements across space. These remnants would serve as the building blocks for future generations of stars, planets, and even life. Over millions of years, gravity continued to shape the cosmos, causing smaller gas clouds to collapse and form new stars and galaxies. Our solar system is one such product of this cosmic evolution. As the remnants of past stellar explosions coalesced around a young star, they formed the planets, moons, and other celestial bodies that make up our solar system. On Earth, chemical processes eventually led to the emergence of life, adding yet another layer to the intricate tapestry of the universe's evolution. Today, we observe a cosmos filled with billions of galaxies, each containing countless stars and planets, each one the product of billions of years of cosmic evolution. The universe continues to evolve even now. Dark energy, a mysterious force that is pushing galaxies apart, drives the accelerated expansion of the universe. Understanding the history of the cosmos not only helps us grasp our origins, but also our place in this vast dynamic universe. The study of cosmic events like supernovae offers profound insights into the origins of the universe and its ongoing evolution. Supernovae are not merely the deaths of stars. They are the birthplaces of the very elements that form planets and life itself. These cataclysmic explosions release elements like carbon and iron into space, providing the raw materials for the formation of new stars, planets, and ultimately, life. Through the study of supernova remnants, astronomers can trace how these essential elements were distributed throughout the universe, shaping the formation of galaxies and star systems. In this way, every cosmic event, whether the birth of a star, the death of a massive star in a supernova, or the collision of two black holes, contributes to the ongoing story of the universe's evolution. Each discovery brings us a little closer to understanding the immense, dynamic cosmos in which we live, revealing the beauty and complexity of the universe's unfolding narrative. Astronomical phenomena such as supernova, massive explosions marking the death of a star, are far more than just spectacular events in the universe. They serve as cosmic markers, guiding astronomers through the vast expanse of space. By carefully measuring their brightness and the patterns in their light, scientists are able to calculate distances across the universe with remarkable precision. This ability to measure vast distances is vital for understanding how the universe has expanded and continues to evolve. In fact, supernovae have been instrumental in discovering something astonishing. The universe's expansion is not slowing down, as once expected, but accelerating. The universe's expansion rate is speeding up, an idea that was confirmed through the study of particular supernova. This finding, often referred to as the discovery of dark energy, reshaped our understanding of cosmic dynamics and provided crucial evidence that something fundamental, something yet to be fully understood, is driving this accelerated expansion. Supernovae serve multiple roles in modern astrophysical studies. They act as both a cosmic clock and a blueprint of the universe's history. Each explosion tells a story, not just of a star's demise, but of the larger process of cosmic evolution. These events allow scientists to peer into the universe's past, tracing how it has transitioned from the chaotic conditions following the Big Bang to the more structured and organized systems we observe today. The sudden release of energy from a supernova can, in many ways, be seen as the universe's way of writing its own history, with each explosion adding a new chapter to our growing understanding of how everything came into being and how it continues to evolve. At its core, the question of where the universe came from is one of the most monumental scientific inquiries ever undertaken. This quest to understand the origin of the cosmos requires a collaborative effort that spans multiple scientific disciplines. Each field brings its own unique perspective, and only by combining these perspectives can we begin to construct a clearer, more complete picture of our origins. One of the most pivotal disciplines in this collaborative effort is astronomy. Astronomers, using an array of advanced telescopes, observe distant stars and galaxies, gathering the light that has traveled across unimaginable distances to reach Earth. This light carries with it valuable information about the state of the universe long before it reaches our eyes. By studying the expansion of the universe, its growth from a single point of origin, astronomers can answer key questions about how galaxies, stars, and other celestial bodies formed. It is through these observations that astronomers have been able to measure the scale of the universe and the rate at which it is expanding. These insights form the bedrock of our understanding of the cosmos. However, astronomy alone cannot fully explain the universe's beginnings. Physicists have made equally important contributions, particularly in the areas of particle physics and astrophysics. These disciplines investigate the fundamental particles and forces that govern the earliest moments of the universe's existence. By conducting experiments in particle accelerators, machines designed to recreate the high-energy conditions that existed just after the Big Bang, physicists simulate the violent processes that took place in the infancy of the universe. These experiments help to explain how matter and energy were transformed into the fundamental elements that make up the world we see around us. They provide a detailed picture of the forces that shaped the creation of galaxies, stars, and planets. Meanwhile, cosmology, a branch that straddles both physics and astronomy, explores the larger-scale structure of the universe. Cosmologists study the universe's overall shape, composition, and evolution over billions of years. One of the most intriguing ideas to emerge from cosmological studies is the theory of cosmic inflation. According to this theory, the universe underwent a rapid period of expansion in the first fraction of a second after the Big Bang, stretching from subatomic sizes to vast cosmic dimensions. This sudden inflation may have had a profound impact on the universe's structure, laying the groundwork for the galaxies and clusters of galaxies that would form in its wake. Geology also plays a critical role in understanding the origins of the universe, especially when it comes to planetary bodies like Earth. Geologists study the materials that make up planets, their formation, and the processes that have shaped them over time. By examining the Earth's own history, scientists can gather clues about how the conditions necessary for life arose. Earth is the only planet we know of that supports life, and understanding its formation and evolution helps us make sense of the broader cosmic narrative. Finally, computer science and data analysis have become indispensable tools in modern cosmology. Advanced simulations, powered by immense computational power, allow researchers to model various scenarios and test their theories about the universe's origin. By creating these virtual worlds, scientists can simulate the birth of the universe, tracing its evolution over millions, even billions of years. These simulations provide a window into the distant past, allowing us to visualize how the universe evolved from a singularity into the vast cosmos we see today. Each of these scientific disciplines, astronomy, physics, cosmology, geology, and computer science, contributes a piece to the greater puzzle. Together, they form a mosaic of understanding that is continually expanding. As new discoveries are made, this collective effort pushes the boundaries of human knowledge, offering deeper insights into the nature of the universe and our place within it. The collaboration between different scientific fields has led to some of the most groundbreaking discoveries in the history of science. Particle physics and cosmology, for example, have offered intriguing insights into the nature of nothing. At first glance, the concept of nothing might seem simple. An absence, a void where nothing exists. However, in the strange world of particle physics, nothing is far from empty. Instead, what we think of as a vacuum is actually a seething field of virtual particles, constantly appearing and disappearing. These particles emerge and vanish in the blink of an eye, thanks to the principles of quantum mechanics. Quantum fluctuations allow energy to manifest even in regions where no matter exists. This makes the vacuum far more dynamic than it first appears. Rather than being an empty void, the vacuum is full of potential, a state of constant flux. Cosmology takes this concept even further. According to the Big Bang Theory, the universe began from an extremely hot, dense state, a singularity where traditional laws of physics break down. The concept of before the Big Bang is itself problematic, as it challenges our understanding of time and space. In this context, nothing is not just an absence of matter. It may represent a state where the very fabric of reality as we know it did not yet exist. This idea invites us to reconsider what we mean by nothing. In the quantum realm, even the void is teeming with activity, and from this apparent emptiness, the universe itself may have been born. This concept of nothingness as a potential source of creation is a radical departure from our everyday understanding of the world. It suggests that what we perceive as nothing may be full of untapped energy and possibilities. The very fabric of reality from this perspective is dynamic and capable of birthing new phenomena, particles, forces, and perhaps even entire universes. Ancient cosmologies, those theories and myths devised by early human civilizations to explain the cosmos, have surprising relevance to our modern scientific understanding. Long before the advent of telescopes and particle accelerators, humanity was already grappling with fundamental questions about the universe. The Babylonians, for example, envisioned the universe as emerging from chaotic waters. This image of creation from primordial chaos has a curious resonance with modern scientific theories that suggest the universe began in a state of intense disorder and energy before evolving into the orderly cosmos we observe today. In ancient Greece, philosophers like Aristotle and Plato laid the groundwork for more systematic and observational approaches to understanding the universe. Aristotle, for example, proposed a geocentric model of the universe where Earth was positioned at the center, surrounded by the stars and planets in a complex spherical arrangement. Although we now know that the Earth revolves around the Sun, the questions raised by these early thinkers about the structure of the cosmos and the nature of celestial bodies set the stage for centuries of scientific inquiry. These early cosmologies were pivotal in pushing humanity towards systematic observation, rational thought, and experimentation. As cultures evolved, so too did their views of the cosmos. The ancient Indian cosmology, for instance, introduced the idea of a cyclical universe, one in which creation and destruction are part of an endless loop. This idea of cosmic cycles bears a striking resemblance to modern theories that suggest the universe may eventually collapse back in on itself in a big crunch scenario. This cyclical vision of the universe highlights the continuity of cosmic evolution and the potential for infinite cycles of creation and destruction. The rise of scientific inquiry during the Renaissance brought a resurgence of interest in ancient cosmological ideas. Thinkers like Copernicus and Galileo revisited the heliocentric model, which proposed that the Sun, not Earth, was the center of the solar system. This revolutionary idea challenged the long-held geocentric views that had dominated Western thought for centuries. Galileo's observations through his telescope provided direct evidence that the planets, including Earth, revolved around the Sun, forever altering humanity's understanding of its place in the universe. These ancient and modern ideas, combined with the advancements of modern science, continue to shape our understanding of the cosmos. From the mythic tales of creation to the cutting-edge theories of cosmology, the story of the universe is one of ever-expanding knowledge, where each new discovery builds upon the last, pushing the boundaries of what we know about the nature of existence itself. The Big Bang Theory, which posits that the universe expanded rapidly from a singular point of origin, resonates deeply with ancient cosmological myths that sought to explain the origins of everything. These creation stories, told across diverse cultures, reflect a deep-seated human curiosity about the nature of existence. They provide a rich philosophical framework that has gradually converged with modern scientific inquiry. Even though humanity's technological progress and understanding of the universe have made incredible leaps over millennia, the central questions raised by ancient civilizations still echo in contemporary astrophysical research. This enduring curiosity links our ancient stories to the sophisticated questions scientists now grapple with. What was the origin of the universe? Was there a creator? Is the universe's emergence from nothing a unique event or a universal constant? These questions are not merely artifacts of the past, but are continuously woven into the fabric of our quest for knowledge. urging us to reconsider not only how the universe came into being, but also the nature of existence itself. Ancient mythologies from around the world converge on a similar theme: the creation of the universe emerging from a state of nothingness. In these myths, the void, often described as an absence of light or a profound silence, becomes the fertile ground from which everything else arises. Ancient Greek mythology, for example, begins with chaos, a primordial void that existed before time and space. From this chaotic emptiness, fundamental entities emerged: Gaia, the earth, and Eros, representing love and attraction. Through the interplay of these forces, the cosmos was shaped, giving birth to the complex universe we inhabit. Similarly, in Hindu cosmology, the universe begins from a cosmic ocean of nothingness, an infinite void filled with darkness. From this nothingness, the creator god Brahma arises, and through his divine actions, the universe, living beings, and the delicate balance of existence come into being. In the Maori creation myth of New Zealand, the narrative of the universe's origin mirrors the theme of emergence from nothing. Before time began, there was only darkness, known as te po. From this primeval darkness, light emerged, and the separation of Rangi, the Sky Father, and Papa, the Earth Mother, gave birth to life and the cosmos. In the biblical account, too, creation begins with an infinite, formless void. Through the word of God, light is called forth, and the earth and sky are brought into existence from a place of non-existence. While the specific characters and the details of these stories differ from culture to culture, they all share a common theme: the transformation of nothingness into the vast, structured complexity that defines the universe we see today. These myths serve as expressions of human curiosity, creativity, and a deep-seated need to find meaning in the face of the unknown. They are not just stories, but profound philosophical inquiries into the nature of existence. The notion that the universe might have originated from nothing, what ancient mythologies hint at and modern science continues to explore, poses profound philosophical and scientific questions. If the universe did indeed emerge from nothing, it forces us to rethink the very nature of existence. What is nothingness? How can something come from nothing? These are not merely rhetorical questions, but puzzles that challenge the foundations of reality itself. Traditionally, we associate creation with the existence of something, be it time, space, or matter. But if the universe sprang from an absence of all these things, then perhaps existence itself is far more elusive and mysterious than we think. This idea upends the conventional understanding of causality. If the universe did not require a cause or a creator, it suggests that the universe could exist without a preceding origin, raising questions about the need for a divine creator or an ordered process. Philosophical and religious frameworks for millennia have posited that the universe's creation involved a deliberate cause, a creator, or a purposeful unfolding of events. However, if the universe arose spontaneously from nothing, it could imply that the universe is, at its core, chaotic, random, and without design. This realization is as humbling as it is unsettling. If we are nothing more than a chance arrangement of matter emerging from an indifferent void, does it mean that existence itself is random, with no higher purpose or order? This concept challenges us not just on a philosophical level, but also on a scientific one. Could it be that the universe, as we understand it, is only one possible outcome of an infinite array of possibilities? Might there be other universes, each emerging from its own unique nothingness, creating an expansive and chaotic multiverse where different laws of physics apply? The very possibility of a universe emerging from nothing invites us to reconsider our place in the cosmos, the nature of our reality, and the principles that govern the entire universe. It invites a new kind of inquiry, one that transcends both the scientific and the metaphysical, challenging us to find new frameworks for understanding. The concept of a universe arising from nothing fundamentally alters our perception of reality. For centuries, we have assumed that all creation requires pre-existing materials or conditions. But if the universe could have emerged from absolute emptiness, it suggests that creation may not need a prior state or substance. The very laws of physics, gravity, electromagnetism, nuclear forces, might not be fundamental constants of the universe, but could themselves have emerged alongside space and time. Rather than being imposed upon the universe, these laws might have unfolded as the universe itself took form, emerging organically from the fabric of what we now consider to be nothing. This line of thinking invites us to reconsider the very nature of existence. If nothingness is not truly empty, but a fertile ground for possibility, then what does it mean for something to be truly nothing? Could it be that nothingness is simply a vast potential, a blank canvas waiting to give birth to reality as we know it? Perhaps the concept of nothingness itself holds the key to understanding the origins of the universe. Could the universe be the first expression of an eternal and unmanifested potential emerging from the unfathomable void? In this view, if universes can form spontaneously from nothing, the idea of a multiverse, an infinite collection of universes, becomes conceivable. Each universe might evolve from its own unique nothingness, governed by its own set of laws and constants. Such a notion expands the scope of existence beyond our own universe and places our reality within a larger, possibly infinite, framework. This radically different perspective challenges not only our scientific theories, but also our philosophical understanding of the universe. If we accept that the universe could arise from nothing, we are forced to confront the limits of our understanding. We may have to admit that our current models and frameworks are inadequate to explain the true nature of reality. This realization, however, does not leave us in despair. Instead, it stirs the imagination, inspiring a new dialogue about the very essence of existence and the cosmos. The idea of a grand unified theory is the logical next step in this inquiry. Scientists have long sought a single framework that could unify the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. Currently, each of these forces operates independently, yet they are believed to have been connected in the early moments of the universe, shortly after the Big Bang. As the universe expanded and cooled, these forces separated, behaving as distinct entities. A grand unified theory aims to explain how this separation occurred and offer insights into the very conditions that existed at the dawn of the universe. Such a theory could offer a coherent explanation of why the universe is structured the way it is, why galaxies form the way they do, and why dark matter and dark energy exist, two of the most mysterious and unexplained elements of the cosmos. Though these elements fill most of the universe's volume and mass, they remain largely undetectable. A unified theory could explain the nature of dark matter and dark energy, revealing how they shape the universe and why they remain invisible to current detection methods. In the realm of particle physics, supersymmetry is an intriguing idea that may provide an answer to some of the universe's most puzzling mysteries. According to supersymmetry, every known particle has a corresponding partner particle. This symmetry suggests that particles and forces in the earliest moments after the Big Bang may have been blended together in ways we can hardly imagine. Supersymmetry offers an explanation for dark matter, the strange imbalance between matter and antimatter in the universe, and other unresolved issues. The discovery of supersymmetric particles could lead to breakthroughs in our understanding of both the universe's past and its future. Thus, the exploration of the universe's origins from nothingness to its current form continues to be a driving force behind both scientific inquiry and philosophical contemplation. The quest to understand how the universe emerged from the void, how its forces came to be, and what this all means for the nature of existence itself is an ongoing journey. Whether through the lens of ancient mythologies or the cutting-edge theories of modern physics, we are continually searching for answers to questions that have echoed through human history. And in this search, we are reminded that our understanding of the cosmos is ever evolving, and the mysteries of the universe remain as vast and enigmatic as ever. At the moment of the Big Bang, the universe was so unimaginably hot that it's hard to fully grasp the extremes involved. It is believed that if supersymmetry, an advanced theoretical concept in physics, holds true, then the interactions of particles during those first moments of creation could have led to a wide variety of potential outcomes. These early dynamics are essential to understanding the dominance of matter in the universe today. Why, for instance, do we observe such an overwhelming presence of matter in the cosmos, as opposed to an equal presence of matter and antimatter? This is one of the many mysteries that science hopes to solve through the exploration of supersymmetry. By probing deeper into the fundamental structure of the universe, scientists are aiming to unlock the secrets of how everything we observe, every star, every planet, and every galaxy, originated from that singular explosive event that took place nearly 13.8 billion years ago. In an attempt to answer such profound questions, researchers have developed an array of advanced technologies designed to enhance our understanding of the universe's origins. Among the most exciting of these advancements are the next generation of telescopes, which are being built to observe the cosmos across a broader spectrum of wavelengths, from infrared to radio waves. These telescopes are not merely tools for observing distant galaxies. They allow us to peer deeper into the universe than ever before, enabling us to look further back in time to the very first stars and galaxies that emerged after the Big Bang. The light emitted from these ancient objects is crucial for uncovering the first moments of cosmic evolution. By studying this faint primordial light, scientists are able to glean clues about the conditions that prevailed shortly after the universe's birth. In addition to cutting-edge telescopes, particle accelerators are another cornerstone of modern cosmology. These massive machines accelerate particles to nearly the speed of light and smash them together, recreating the extreme conditions that existed just after the Big Bang. In doing so, they mimic the early universe's high-energy environment, allowing scientists to observe the fundamental particles that were formed in the first moments of cosmic history. By understanding the forces and interactions that shaped the early universe, researchers are piecing together the complex puzzle of how the universe evolved from an initial chaotic state to the structured cosmos we see today. Alongside telescopes and particle accelerators, advances in simulation technology are helping to shed light on cosmic mysteries. Powerful supercomputers are being used to create highly detailed simulations of early universe events, which allow researchers to test their hypotheses against observational data. These simulations provide a virtual laboratory where scientists can explore different models of cosmic evolution, adjusting variables and testing outcomes. By comparing the results of these simulations with what we observe in the universe, scientists can refine their understanding of how galaxies, clusters, and other cosmic structures came into being. Perhaps one of the most groundbreaking technological developments in recent years has been the ability to detect gravitational waves. These ripples in space-time caused by violent events such as the collision of black holes or the explosion of massive stars have opened a new window into the universe. Unlike light-based observations, which provide a limited view of the universe, gravitational waves offer insights into the universe's most extreme phenomena. These waves carry information about the universe's rapid expansions and early behaviors, information that can't be gleaned from traditional telescopic methods. By detecting and analyzing these waves, scientists are uncovering new aspects of the early universe, offering unprecedented views into the cosmos. Each of these technological advancements, telescopes, particle accelerators, simulations, and gravitational wave detectors, contributes to a multifaceted approach to understanding the universe's origins. Together, they allow scientists to gather an unprecedented wealth of information, illuminating the universe's history and the fundamental laws that govern it. As a result, we are getting closer than ever to uncovering the enigmatic story of our cosmic beginnings. Over the course of the last century, our understanding of the universe has undergone a dramatic transformation. At the dawn of the 20th century, scientists began noticing that distant galaxies were moving away from us. This discovery, based on the observation of redshifting light, suggested that the universe was expanding. It was a groundbreaking insight that forever changed the way we view the cosmos. Rather than a static, eternal entity, we now understand that the universe began from a single, extremely hot and dense point known as a singularity. Since that moment, the universe has been expanding, evolving, and cooling. This realization was further solidified with the discovery of cosmic background radiation, a faint glow that fills the entire universe. This radiation, which can be detected in all directions, is essentially the afterglow of the Big Bang. It is one of the most significant pieces of evidence supporting the notion that the universe had a distinct and fiery beginning. Cosmic background radiation tells us that in the very early moments of the universe, it was so hot and dense that it was filled with light. As the universe expanded, this light cooled, eventually becoming the radiation that we can observe today. The study of this ancient light has given us a clearer picture of the conditions that existed shortly after the Big Bang and has helped confirm the Big Bang theory as the leading explanation for the universe's origins. Thanks to advances in telescopic technology and satellite observation, we can now observe ancient light from the very early universe. These observations allow us to peer back in time, providing a glimpse into a period when the universe was only a few 100,000 years old. By studying these ancient photons, we can trace the development of the universe's structure, such as the formation of the first atoms, the birth of the first stars, and the creation of galaxies. This data has significantly enhanced our understanding of how matter and energy evolved over billions of years, eventually giving rise to the vast array of cosmic structures we observe today. Another crucial area of research involves the study of fundamental particles, those tiny building blocks that make up everything in the universe. Advances in particle physics have enabled scientists to delve into the behavior of these particles, especially those that formed during the universe's earliest moments. By examining the fundamental forces that govern the interactions between particles, scientists have been able to learn more about how these forces shaped the development of the universe. This knowledge, in turn, has allowed us to better understand the forces of gravity, electromagnetism, and nuclear forces, key components in the creation and evolution of the universe. The combination of these discoveries, the expansion of the universe, cosmic background radiation, the study of ancient light, and the exploration of fundamental particles, paints a picture of the universe as a dynamic, ever-changing entity. This picture emphasizes not only how we came to be, but also our ongoing relationship with the cosmos. As we continue to explore the depths of space and time, we continually reveal new layers of understanding about our origins, reminding us of how much more there is still to learn. Despite the tremendous strides we've made in understanding the universe's origins, there are still many unanswered questions that scientists are actively exploring. The Big Bang Theory, while widely accepted, is far from a complete explanation of the universe's birth. It suggests that the universe began from an extremely hot and dense state around 13.8 billion years ago. However, many aspects of this theory remain unclear, particularly when it comes to the very first moments after the Big Bang. Because the universe began as a hot, opaque state, light could not travel freely for a considerable amount of time. It was only after a brief period that the universe cooled enough for light to move through space, resulting in the cosmic microwave background radiation we detect today. While this radiation provides important clues, it does not give us a full understanding of the earliest events that occurred in the moments following the Big Bang. One of the biggest challenges in cosmology is understanding what happened before the Big Bang, or if the concept of before even applies. Current theories grapple with the idea of time and space as we understand them, and whether they existed before the Big Bang. Some models, such as the theory of cosmic inflation, suggest that the universe underwent a rapid exponential expansion shortly after the Big Bang. This theory provides a potential explanation for the large-scale structure of the universe, but it is still being refined. Furthermore, while the Big Bang theory explains the expansion of the universe, it does not address the fundamental question of what caused the initial burst of energy or what principles guided that expansion. In addition to these questions, the existence of dark matter and dark energy, two mysterious substances that seem to have a profound influence on the universe, adds another layer of complexity. The interplay between these two realms remains a profound mystery, and scientists are still working to understand how quantum mechanics may have shaped the early moments of the universe's creation. While we have made significant progress in understanding the origins of the universe, there is still much we do not know. Each discovery in this field opens up new avenues for exploration, keeping the quest for knowledge dynamic and filled with possibility. The more we learn, the more we realize how much is left to uncover. The universe's beginnings remain one of the greatest unsolved mysteries in science, and with every new technology and breakthrough, we move closer to deciphering the extraordinary story of how everything came to be. Moreover, scientists are acutely aware that gaps exist in our current understanding of the universe, which drives the formulation of new questions and ideas. These gaps serve as the very foundation of scientific inquiry, challenging existing theories and encouraging the development of novel ones. In an ever-evolving field like cosmology, these questions are not merely academic, but are integral to our broader quest to comprehend the vast, enigmatic universe in which we live. As new data emerges and technology advances, scientists are constantly refining their perspectives, not only to explain what we already know, but also to explore what we have yet to discover. Unexplained phenomena such as dark matter and dark energy, two of the most mysterious and elusive elements in modern astrophysics, have become focal points for ongoing research. These enigmatic forces, which make up a substantial portion of the universe's total mass energy content, remain largely invisible and beyond direct detection, yet their influence is undeniable. Consequently, large-scale research collaborations, including those involving particle accelerators and state-of-the-art observatories, have become indispensable in the search for answers. These colossal research facilities, such as the Large Hadron Collider and the Hubble Space Telescope, allow scientists to probe the most profound questions of our existence. They enable researchers to investigate cosmic events, study the fundamental particles of nature, and examine the properties of distant galaxies. Through these advanced tools, we have glimpsed the birth and evolution of stars, the inner workings of black holes, and the behavior of light across the cosmos. Yet, despite these breakthroughs, many questions about the origins of the universe remain unanswered. The nature of dark energy and dark matter, for example, remains one of the most profound challenges in modern physics. These phenomena are believed to have shaped the expansion of the universe in ways we still do not fully understand. The scientific community, however, continues to embrace uncertainty as a vital component of the journey toward deeper insight. This openness to the unknown is what propels humanity's understanding forward. As technology improves, more discoveries are made, and new theories emerge, the puzzle of the cosmos gradually takes shape, albeit still surrounded by vast mysteries. Scientists often accept the unknowable as an integral part of the process, for it is only through this ongoing exploration and the continual questioning of assumptions that we advance our knowledge. One particularly intriguing concept emerging from these investigations is the idea that the universe might have come into existence from nothing. This proposition challenges our most fundamental notions of existence and is as perplexing as it is captivating. Current theories suggest that prior to the formation of the universe, there may have been a state devoid of both matter and energy, an almost unfathomable notion when compared to the universe we experience today. In this framework, the nothing is not absolute emptiness, but a quantum vacuum that, though seemingly devoid of matter, still contains the potential for energy fluctuations. Quantum mechanics, a branch of physics that deals with the behavior of particles on the smallest scales, tells us that even the emptiest regions of space are not truly empty. Instead, they are filled with transient fluctuations of energy that can, in some cases, give rise to particles and forces. Imagine a calm, still sea where, beneath the surface, small ripples of activity occasionally emerge. These fluctuations, though fleeting, are enough to disrupt the stillness and create something tangible. In a similar way, these fluctuations in a quantum vacuum might have been the catalyst for the creation of the universe itself. This leads to the intriguing question: could the conditions of this nothing have been the spark that ignited the creation of everything we see today? In this context, the exploration of dark matter and dark energy could prove to be pivotal in understanding the true nature of this primordial nothing. If these mysterious substances are, in fact, integral to the universe's creation, it would suggest that nothing is far from empty. Instead, it may represent a dense fabric of potential and chaos, ready to give birth to new universes when the conditions are right. The implications of this idea are profound, as it would radically alter our understanding of the origins of the cosmos and the very nature of existence itself. Furthermore, as advancements in technology continue, future discoveries could provide new insights into the forces and laws that govern the earliest moments of the universe. We may come to understand how energy and particles interacted in the moments following the Big Bang, shedding light on the birth of space-time itself. If we gain a deeper understanding of this crucial period, it could radically shift our perception of a universe that emerged from absolute emptiness. What we once thought to be a creation from nothing could turn out to be a process more interconnected and dynamic than we ever imagined. Such future breakthroughs might reveal that the universe is not merely a random collection of galaxies, stars, and planets, but an intricately woven fabric where forces, particles, and energy are deeply interconnected. This could lead us to a more complex and breathtaking view of the cosmos, one that challenges the idea of creation from nothing and encourages a more nuanced appreciation of the universe's intricate design. A concept that helps bridge the gap between the idea of the universe emerging from nothing and the complexity of the universe we observe today is the theory of cosmic inflation. This theory proposes that in the moments immediately following the Big Bang, the universe underwent an incredibly rapid expansion. Imagine a balloon lying flat on a table. When you blow air into it, the balloon expands rapidly, but this expansion is not uniform at first. Similarly, during cosmic inflation, the universe expanded at an extraordinary rate, growing faster than the speed of light in a fraction of a second. This period of rapid expansion was not merely a growth in size, it was also a process that smoothed out the universe, transforming what was likely a chaotic, uneven landscape into a more uniform, homogeneous cosmos. Before inflation, the universe may have been filled with clumps of matter and energy scattered in a disorderly manner. As inflation took hold, it stretched this initial chaotic state into the vast, even fabric of space we observe today. In this context, the theory of inflation provides a compelling narrative for a universe emerging from nothing. If nothing, in this case, is understood not as absolute emptiness, but as a state devoid of particles, stars, and matter as we know it, inflation offers a plausible mechanism for how the universe could emerge. According to this theory, the universe could have arisen from a quantum vacuum state, a form of energy that exists in its most minimal form. Though we still do not fully understand the processes that led to this energy's transition, it is widely believed that through some quantum fluctuation, this vacuum energy began to rapidly expand, giving birth to the cosmos as we know it. This notion bridges the gap between the idea of creation from nothing and the complexity of the universe. Cosmic inflation explains how a tiny, uniform region of space could evolve into the vast, intricate cosmos filled with galaxies, stars, and planets. Through this lens, inflation not only deepens our understanding of the universe's birth, but also invites us to reconsider what nothing truly means in the grand context of existence. Several pieces of evidence support the theory of cosmic inflation. One of the strongest indicators is the cosmic microwave background, CMB radiation, often referred to as the afterglow of the Big Bang. This radiation is uniformly distributed across the sky, but tiny fluctuations exist. Inflation theory explains these small variations as the result of quantum effects during the rapid expansion that occurred in the universe's early moments. These fluctuations provide valuable clues about the distribution of matter and energy in the early universe. Another compelling piece of evidence comes from the large-scale structure of the universe. If inflation had not occurred, we would expect to see a different arrangement of galaxies and galaxy clusters. However, the current distribution aligns remarkably well with predictions made by the inflationary model, suggesting that the universe's early expansion played a critical role in shaping the cosmos. Additionally, the geometry of the observable universe is nearly flat, which also supports the theory of inflation. This flatness implies that the universe's expansion spread out initial density fluctuations, leading to a balanced, uniform geometry. Furthermore, data gathered by telescopes and observatories such as the Hubble Space Telescope and the Planck satellite has shown results that align closely with the predictions of inflationary theory. These observations reinforce the idea that a rapid expansion at the beginning of the universe is a compelling explanation for the structure and evolution of the cosmos as we know it. When comparing religious creation stories with scientific theories of the universe's origins, we see two distinct yet equally fascinating perspectives. Religious narratives often present the creation of the universe as the deliberate act of a divine being or beings. These stories emphasize themes of order emerging from chaos and often imbue the process of creation with moral and existential significance. From a religious standpoint, the origins of the universe are part of a larger spiritual narrative, one that offers meaning and purpose to believers. In contrast, scientific theories seek to explain the origins of the universe through evidence and observation. The most widely accepted scientific model, the Big Bang Theory, proposes that the universe began from an extremely hot and dense point, which suddenly expanded, spreading matter and energy throughout space. This event eventually led to the formation of galaxies, stars, and planets over billions of years. Scientific discussions of the universe's origins delve deeply into complex ideas in quantum physics, the nature of time and space, and the laws of physics. These theories, grounded in empirical evidence, aim to offer explanations based on observation and experimentation, rather than spiritual or moral considerations. Though religious creation stories and scientific theories differ in approach, they both grapple with the same fundamental question: how did everything begin? Whether through the lens of divine creation or scientific inquiry, both perspectives seek to answer the age-old question that has captivated humanity for millennia. The dialogue between these two worldviews continues to inspire profound reflections on the nature of existence, our place in the universe, and the mysteries that remain. The realms of human understanding, whether through the lenses of faith or science, are rich with imagination, offering diverse and profound ways to explore the depths of the human experience and its relationship with the cosmos. Both avenues provide distinct, yet equally compelling routes to reflect upon the vast mysteries of existence, inviting personal connections that challenge our understanding of the universe. Whether these connections emerge from spiritual beliefs or scientific inquiry, each perspective, shaped by faith or skepticism, contributes to our collective quest for understanding the cosmos. The wonder of existence, a question that has intrigued humanity for millennia, is not simply confined to philosophical musings. It plays a central role in how we interpret our place within this immense, ever-expanding universe. Religious interpretations in particular have historically played a significant role in shaping human perceptions of the universe's origins. Numerous religious traditions across the world offer intricate narratives about the creation of the cosmos, often involving a divine force or being, God, gods, or other spiritual entities. These sacred stories serve as frameworks through which followers make sense of the cosmos and their own existence within it. For many, these narratives are not mere allegories, but rather divine truths that answer the fundamental questions about the origins of the universe and everything within it. As a result, individuals deeply influenced by these religious teachings may prioritize theological explanations over scientific ones when contemplating the universe's beginning, viewing them as the most authentic or meaningful paths to understanding. In contrast, science approaches the question of origin through a methodical lens of observation, experimentation, and empirical evidence. Through the study of cosmic phenomena and physical laws, science has provided one of the most compelling narratives of the universe's creation, the Big Bang Theory. According to this scientific model, the universe began approximately 13.8 billion years ago as an infinitely small, hot, and dense point, an event that set into motion the expansion of space, the cooling of matter, and the formation of the stars, galaxies, and planets we see today. Supported by evidence such as cosmic background radiation and the observed movement of galaxies, this theory paints a picture of a universe born from an explosion of energy, gradually evolving over billions of years into the intricate and structured cosmos we inhabit. For many people, the seemingly opposing views of science and religion are not mutually exclusive. Instead, they coexist in a nuanced relationship that allows both perspectives to inform each other. Some individuals see science as a way to comprehend the mechanisms of creation described in religious texts, understanding it as the how behind the divine why. In this view, the work of physicists and astronomers does not diminish the spiritual significance of the universe's origins, but enhances the wonder and mystery inherent in creation. However, tension can arise when certain scientific findings appear to directly contradict literal interpretations of sacred texts. For instance, if scientific evidence suggests that the universe is billions of years old, it may come into conflict with religious teachings that espouse a belief in a much younger Earth, as found in some creationist doctrines. In such cases, followers of these traditions may reinterpret sacred scriptures, seeking new theological interpretations that reconcile their faith with the evolving discoveries of science. This ongoing interaction between religious and scientific views is complex and multifaceted, with individuals navigating this terrain in different ways based on their cultural backgrounds, personal beliefs, and the interpretations offered by their religious communities. The way in which people respond to the challenge of understanding the universe's origins is deeply personal, shaped by both intellectual curiosity and spiritual convictions. It is this interplay of beliefs, shaped by centuries of tradition and the rapid advancements of modern science, that underscores humanity's eternal quest to comprehend the mysteries of existence, creation, and the cosmos itself. As we delve deeper into the scientific understanding of the universe's birth, one of the most fascinating fields is particle physics. Through the study of the fundamental particles that make up the universe, scientists are able to peel back the layers of time, revealing the processes that governed the early moments of the cosmos. These tiny building blocks of matter, subatomic particles, are the essential components that come together to form the atoms, stars, and galaxies that we observe today. The universe, in its infancy, was a hot, dense soup of particles, all colliding and interacting in a chaotic burst of energy. As the universe expanded and cooled over time, these particles began to form into atoms, which eventually coalesced into the stars, planets, and galaxies that constitute the vast cosmic landscape. Particle physics helps illuminate the forces that govern these interactions, such as gravity and electromagnetism, which shape how particles behave and interact with one another. One of the most significant discoveries in this field is the identification of bosons, particles that include the famous Higgs boson. This particular particle is key to understanding why other particles have mass, which is crucial for the existence of matter as we know it. Without mass, particles would travel at the speed of light, unable to form the stable structures that make up our universe. This discovery has profound implications for our understanding of both the origins of the universe and the nature of existence itself. In addition to offering insights into the behavior of particles, the study of particle physics also allows scientists to simulate conditions similar to those that existed in the very early universe. By accelerating particles such as protons to extremely high speeds and then smashing them together, researchers are able to recreate the intense energy and conditions that prevailed just after the Big Bang. These collisions produce exotic particles that may have existed in the universe's first moments, providing valuable data about the fundamental forces that shape the cosmos. One particularly intriguing phenomenon that has been studied through particle accelerators is the quark-gluon plasma, a state of matter believed to have existed in the moments immediately after the Big Bang. Particle accelerators, often regarded as the time machines of modern physics, allow scientists to peer into the infancy of the universe, creating conditions that mirror the extreme environments of the early cosmos. These experiments help unravel the mysteries of how the universe evolved from a burst of energy into the complex, ordered structure we see today. Each new discovery, each particle observed, brings scientists a step closer to solving the puzzle of our cosmic origins, shedding light on the very forces that shape the universe and continue to govern its expansion. Despite the enormous progress made in understanding the universe's beginnings, the scientific community continues to explore new ideas and models to further expand our understanding. One alternative theory that has gained attention is the steady-state model, which proposes that the universe, while expanding, is simultaneously creating new matter to fill the voids left by this expansion. According to this theory, the universe has no true beginning or end, instead presenting a consistent appearance over time. In contrast, another model, the cyclical universe theory, suggests that the universe undergoes endless cycles of expansion and contraction, like a balloon being inflated and deflated repeatedly. In this view, the universe expands to a great size and then collapses back into a singular point, only to begin anew, repeating this cycle infinitely. Perhaps one of the most mind-bending concepts is the multiverse theory, which posits that our universe is just one of many in a vast sea of universes, each with its own distinct set of physical laws and constants. In this model, our universe is merely one bubble among countless others in a much larger, uncharted multiverse. The implications of this theory are staggering. It challenges our very understanding of existence, time, and space, suggesting the possibility of multiple realities coexisting simultaneously, each with its own version of history, physics, and even time itself. Ultimately, the quest to understand the origins of the universe, the forces that shaped it, and the mysteries that still lie hidden within it is far from over. Whether viewed through the eyes of religious tradition or scientific inquiry, the exploration of the cosmos remains one of humanity's most profound endeavors. As science continues to peel back the layers of the universe's history, and as faith traditions continue to inspire questions about existence and meaning, both paths converge in their shared quest to comprehend the profound and elusive mysteries of the cosmos and our place within it. String theory and quantum gravity are two deeply intriguing frameworks that seek to reconcile two of the most successful theories in modern physics, quantum mechanics and general relativity. Quantum mechanics, which governs the microscopic world of subatomic particles, and general relativity, which describes the dynamics of massive objects like stars and galaxies, operate under very different principles. The challenge has always been how to unite these seemingly incompatible theories into a single, all-encompassing framework that can explain everything from the smallest particles to the largest structures of the cosmos. These theories, though still highly theoretical and not yet universally accepted, suggest the possibility of hidden, intricate structures at the atomic level that could profoundly influence the very fabric of our universe. The promise of string theory and quantum gravity is immense. At their core, they offer a radically new way of looking at space and time, suggesting that the universe operates in ways we can hardly imagine. Rather than treating particles as indivisible points, string theory proposes that these fundamental units are actually tiny vibrating strings. These strings, vibrating at different frequencies, give rise to the various particles and forces we observe in the universe. Quantum gravity, meanwhile, attempts to apply quantum mechanical principles to gravity, something that classical general relativity has not been able to achieve. Together, these theories suggest that the universe might be far more complex than we've ever realized, with underlying structures that operate at a scale and complexity beyond our current understanding. Although both string theory and quantum gravity are still in their infancy and face significant challenges, they provoke a profound reconsideration of the forces that shape our reality. These models open up new avenues for exploring the fundamental questions of existence. How did the universe begin? How does it evolve? And most crucially, is it possible that we are only beginning to scratch the surface of a much deeper, more intricate reality? Each of these theories contributes a unique perspective on the cosmic puzzle, and together they form a collective effort to deepen our understanding of the universe's grand design. The exploration of these ideas is not just an academic pursuit. It is a philosophical quest to understand the very nature of existence, prompting us to reconsider long-held assumptions about time, space, and the structure of the cosmos. What is particularly exciting is that with each breakthrough in these theories, we find ourselves confronted with new questions, new mysteries, and new possibilities about the nature of reality. These questions challenge the limits of human knowledge, forcing us to reevaluate our place in the vast, ever-expanding cosmos. One fascinating theoretical framework that has captured the imagination of many cosmologists is conformal cyclic cosmology, CCC. This model offers an intriguing alternative to the traditional Big Bang theory, challenging some of the most fundamental assumptions about the universe's beginning, its fate, and the cyclical nature of time itself. While the Big Bang Theory posits that the universe began as a singular explosive event, roughly 13.8 billion years ago, CCC presents a very different vision. According to CCC, the universe undergoes an infinite series of cycles, each beginning with a Big Bang, but with a crucial twist. The concept of time, as we understand it, is not static or linear. Instead, it stretches and warps, flowing in a cyclical manner. In CCC, each cycle is not a one-off event, but part of an eternal sequence of rebirths. The model suggests that after the universe reaches a state of maximum expansion, it enters a death phase, where stars burn out, galaxies drift apart, and the cosmos grows cold and dark. However, instead of ending in a final, irreversible death, this phase serves as a transition into the next cycle. As the universe ages, it eventually becomes smoother, with time and space losing their distinct characteristics. When this occurs, the universe undergoes a dramatic transformation. Its previous state is forgotten, and a new Big Bang takes place, starting the cycle anew. In this model, the universe doesn't remember its previous incarnation, much like a book whose pages have been wiped clean, ready to be filled with new stories. The concept of time in CCC is not linear, but rather cyclical, with the end of one universe blending seamlessly into the birth of the next. This stands in stark contrast to the traditional view of the Big Bang, which imagines a singular, irreversible origin. CCC encourages us to think of the universe not as a one-time event, but as an eternal series of cosmic cycles, each one giving rise to new forms of existence and new stories of cosmic evolution. The implications of CC are profound. If true, it challenges the very nature of beginnings and endings in the universe. Rather than a singular origin point, the universe could be part of an infinite loop, where each cycle contains its own history and its own cosmic events. This opens up the tantalizing possibility that the universe might not have had a singular birth, but could instead be an ongoing, never-ending series of births and deaths, stretching endlessly into the future. Observational cosmology is the window through which we attempt to peer into the distant past of the universe. Using powerful telescopes and other instruments, scientists can observe light, radiation, and other signals from galaxies, stars, and other cosmic objects that are located far beyond our reach. These signals carry with them vital clues about the conditions of the universe at various points in its history. One of the most important discoveries in observational cosmology is the detection of cosmic microwave background, CMB radiation. This faint, omnipresent glow fills the entire universe and is a relic of a time when the cosmos was still in its infancy, hot, dense, and rapidly expanding. By studying this radiation, scientists can uncover insights about the early universe, how it looked, how it behaved, and how it eventually evolved into the universe we see today. Another key discovery made through observational cosmology is the measurement of the universe's expansion. By observing the motion of distant galaxies, scientists have confirmed that the universe is indeed expanding, with galaxies moving away from one another over time. This observation led to the development of the Big Bang Theory, which suggests that the universe began as a singular, infinitely dense point, often referred to as the singularity, and has been expanding ever since. The rate at which galaxies are moving apart provides crucial clues about when the universe began and how long it has been expanding. This expansion, once considered a theoretical curiosity, has now been confirmed through decades of observations. In addition to the expansion of the universe, the distribution and behavior of galaxies, galaxy clusters, and other cosmic structures also offer valuable insights into how the universe evolved. By studying these structures, scientists can develop models that explain how galaxies came together and evolved over billions of years. These models not only describe the forces that shape the universe, but also shed light on the mysterious substances, such as dark matter and dark energy, that play a crucial role in the evolution of the cosmos. Each new discovery in observational cosmology provides a piece of the cosmic puzzle, helping to refine our understanding of the universe's origins and its ongoing evolution. As technology improves, so too do our tools for exploring the cosmos. Telescopes like the Hubble Space Telescope have revolutionized our understanding of the universe, offering stunning images of distant galaxies and providing invaluable data about the universe's expansion, its age, and the processes that govern its evolution. One of Hubble's most significant contributions has been its ability to measure the rate of expansion of the universe. This expansion was first observed by astronomer Edwin Hubble in the 1920s when he discovered that distant galaxies were moving away from us. This phenomenon, now known as Hubble's law, was the first observational evidence that the universe was expanding. Since then, Hubble has provided more accurate measurements of the expansion rate, known as the Hubble constant, helping scientists refine their models of the universe's evolution. Hubble has also provided stunning images of distant galaxies, allowing astronomers to study the formation of galaxies in the early universe. Because light from these galaxies takes millions or even billions of years to reach us, Hubble essentially lets us look back in time. This allows scientists to study how galaxies formed, how they interacted with one another, and how they evolved over cosmic time. Hubble has also played a key role in studying the cosmic microwave background radiation, which is the afterglow of the Big Bang. By measuring variations in the temperature of this radiation, scientists can refine their estimates of the universe's age, which is currently thought to be roughly 13.8 billion years. As our technology improves and our understanding of the universe deepens, observational cosmology continues to evolve. The questions we ask today will shape the answers of tomorrow, and each new discovery brings us one step closer to unraveling the mysteries of the cosmos. The universe, vast and incomprehensible, still holds countless secrets, and through the tools of observational cosmology, we are slowly piecing together the grand story of everything. The Hubble Space Telescope has played an instrumental role in unveiling some of the universe's most profound secrets, particularly its acceleration. Dark energy, the mysterious force thought to be behind this phenomenon, has been one of the most significant discoveries in modern cosmology. By studying the brightness of distant supernova, Hubble has uncovered surprising evidence that the rate at which the universe is expanding is increasing. This discovery offers profound clues about the future of the cosmos, suggesting that its fate might not be as predictable as once thought. Through its incredible observations, the Hubble Space Telescope has provided invaluable insights into how the universe began and how it continues to evolve. It has helped us understand the formation of galaxies, the nature of cosmic background radiation, and the elusive role of dark energy, enriching our comprehension of the cosmos. As we explore these findings, we begin to see the universe not as a static entity, but as a dynamic, ever-changing system, a reality that is far more complex than we could have imagined. When we look at the origins of the universe, the concept of time becomes an especially fascinating subject. Time, as we understand it, is inextricably tied to the evolution of the cosmos, and it has shaped everything that we know about existence. One of the most prominent theories that seeks to explain the universe's birth is the Big Bang theory. This theory suggests that the universe began as an incredibly hot and dense point, far smaller than even the head of a pin, before rapidly expanding in what we now call the Big Bang. This event, often described as the universe's beginning, marks the point at which time itself began. Before the Big Bang, there was no before in the way we understand it. Time as a measure of change, as a process of cause and effect, simply did not exist. The universe and time were born together, and as the universe expanded from that infinitesimal point, time unfolded alongside it. This realization challenges traditional views, suggesting that time is not an external constant, but is woven into the fabric of the universe itself. Without time, there could be no events, no changes, no formation of stars, no birth of galaxies. Essentially, there would be no universe at all. Yet, the relationship between time and space is far from simple. As we move through the cosmos, we can observe the effects of gravity on time. The stronger the gravitational field, the slower time flows. This means that in regions near massive objects like black holes or stars, time is not a constant. Instead, it stretches, bends, and behaves in ways that defy our everyday experiences. Time in these regions behaves almost like a malleable substance, distorting as it interacts with the immense forces of gravity. These effects have profound implications for how we perceive the universe's evolution. When we begin to contemplate the essence of time, it helps to consider the notion of nothing. Imagine a state of pure void, an absence of everything. There would be no motion, no change, no events occurring. In this nothing, Time itself would have no meaning because there would be no passage, no markers by which to measure its flow. Time, in this context, only gains significance in a universe that is teeming with change. The universe, unlike nothing, is full of constant activity. Stars are born, galaxies collide, life evolves, and all of these processes unfold within the framework of time. Quantum cosmology takes this exploration a step further, offering a fascinating lens through which we can examine the universe's birth. This field seeks to understand the origins of the universe by studying the smallest building blocks of reality, quantum particles, and how these tiny units are connected to the vast cosmos. In quantum mechanics, nothing is not a simple void. Instead, it is a place brimming with possibilities. This is best understood through the phenomenon known as quantum fluctuations, where particles can appear and vanish within the blink of an eye. These fluctuations imply that under certain conditions, nothingness can give rise to something. This concept challenges our traditional understanding of existence. Quantum cosmologists propose that the universe may have emerged from such fluctuations, where energy and particles appeared from a void. To visualize this, imagine the still surface of a pond. If you toss a pebble into it, ripples spread outward, creating waves. Similarly, the birth of the universe may have been triggered by a small, energetic fluctuation that expanded rapidly, eventually giving rise to galaxies, stars, and everything else we see today. In this framework, time itself began with the universe's creation. This means that asking what happened before the universe is a question that doesn't quite apply. Before the Big Bang, there was no before in the way we understand it. Time, space, and the very fabric of the universe began at the moment of the Big Bang. This perspective radically changes our understanding of the cosmos, implying that time is not an external, independent force, but an integral part of the universe's unfolding story. The Wheeler-DeWitt equation is one of the key concepts in quantum cosmology, bridging the realms of general relativity and quantum mechanics. To grasp the significance of this equation, imagine trying to describe the entire history and structure of the universe, not in terms of time, but through a snapshot of its geometry. This equation presents the universe in a timeless framework, capturing all possible states of the cosmos at once. In other words, rather than evolving in a linear fashion, the universe, according to this equation, exists in a state where every possibility coexists simultaneously. This model represents a dramatic shift from how we typically understand the passage of time. It suggests that the universe doesn't evolve in the traditional sense. Instead, it exists within a complex network of possible outcomes, all unfolding together. The Wheeler-DeWitt equation captures this dynamic relationship between time, space, and the quantum fluctuations that give rise to the universe's most fundamental structures. However, the equation also presents challenges for scientists as it lacks a clear notion of time, making it difficult to derive specific classical events from quantum origins. Despite these challenges, researchers continue to explore the equation's potential, seeking to unlock deeper insights into the very nature of existence. In recent years, advances in both physics and astronomy have significantly reshaped our understanding of the universe's origins. For much of history, it was believed that the universe started from a static, unchanging state. But with the advent of powerful telescopes and advanced observation techniques, this notion has evolved. Today, we understand that the universe was not born from stasis, but rather from a singular, highly energetic event, the Big Bang. This event, roughly 13.8 billion years ago, marks the beginning of the universe as we know it. One of the most compelling pieces of evidence for the Big Bang theory is the discovery of cosmic microwave background radiation. This faint glow is the afterglow of the Big Bang itself, a remnant of the universe's early fiery stages. As the universe expanded and cooled, this energy spread out, and today it can still be detected. This radiation, present throughout the cosmos, provides a snapshot of the universe's early moments and confirms that it has been evolving ever since. But the Big Bang is not the only revelation that has reshaped our understanding of the cosmos. The discovery of dark energy, an invisible force that is driving the accelerated expansion of the universe, has raised new questions about the future of the universe. If the expansion of the universe is indeed speeding up, then what will the ultimate fate of the cosmos be? Will the universe continue to expand indefinitely, or will it eventually collapse? These questions remain open, but dark energy is providing crucial clues that may help scientists answer them. Another exciting development is the discovery of exoplanets, planets outside of our solar system. These discoveries have expanded our understanding of the conditions that might exist elsewhere in the universe, opening the door to the possibility that similar processes, like those that led to the birth of our universe, might be occurring in distant galaxies. The search for habitable planets and signs of life has added yet another layer of complexity to our understanding of the universe's early history. As our tools for observing the universe become more sophisticated, scientists are able to peer deeper into the cosmos than ever before. Advanced telescopes, observational technology, and techniques like the study of gravitational waves, ripples in space-time caused by massive cosmic events, are offering entirely new ways of exploring the universe's origins. These waves allow scientists to study the most cataclysmic events, such as black hole mergers or neutron star collisions, offering a fresh perspective on the universe's early days. Each of these discoveries, from the detection of cosmic background radiation to the detection of gravitational waves, enriches our understanding of the universe. Far from being a static, unchanging entity, the universe is a dynamic and evolving system, constantly reshaping itself. Through these exciting breakthroughs, we are only beginning to uncover the true scope of the cosmos and its mysteries that continue to unfold with each passing moment. Simulations on powerful supercomputers allow researchers to recreate and model the conditions of the early universe with remarkable precision. By simulating cosmic evolution, these models give scientists the tools to predict how structures formed and evolved, offering insights that help either validate or challenge existing theories about the universe's origins. When combined with observational data gathered from telescopes and other instruments, these simulations offer a more detailed understanding of how the universe transitioned from a hot, dense state to the vast, complex cosmos we observe today. Together, these cutting-edge techniques push the boundaries of our understanding, revealing new possibilities in our quest to comprehend the universe's origins and the fundamental processes that shaped it. Each breakthrough provides another piece of the cosmic puzzle, unraveling the incredible narrative of our universe's earliest moments. A universe that emerged from nothing stands as one of the most profound mysteries of existence, challenging our very understanding of what it means to be. Imagine a state where there is no matter, no space, and no time, a concept so alien to our everyday experience that it forces us to reconsider the very foundation of reality itself. In such a scenario, the universe might have emerged from a quantum fluctuation, defying our traditional notions of a beginning. This universe, instead of having a conventional starting point, could have resulted from a spontaneous event where energy formed and gradually evolved into matter, leading to the creation of a vast and intricate cosmos. In the initial moments of such a universe, the conditions would have been chaotic and tumultuous, marked by a rapid, uncontrollable expansion. It might have been so hot and dense that it would have been completely inhospitable to any form of life or stable structure. Yet, as the universe expanded and began to cool, matter could slowly form into simple particles. Over time, these particles might clump together under the influence of gravity, eventually giving rise to stars, galaxies, and other cosmic structures that we see today. An intriguing aspect of this hypothetical universe is that it might lack any of the initial conditions that we typically associate with the universe we know, things like the specific laws of physics. Instead, its fundamental properties could evolve over time, driven by the interactions between particles and fields. This raises the possibility that the universe's governing laws might differ radically from the ones we are familiar with, leading to phenomena that might be utterly unexpected or beyond our comprehension. In this story of a universe born from nothing, time itself would be a concept that only emerges gradually. In the earliest stages, moments may be indistinguishable, a blur of events without any clear passage. But as structures form and evolve, time would begin to emerge as a measure of change, marking the progression of the universe's development as we experience it. What began as an almost formless void would, over billions of years, develop into the complex tapestry of reality that we observe in the present day. While such a universe might share certain characteristics with our own, it would likely possess a set of rules and features all its own, shaped not by a predetermined design, but by the inherent possibilities that arose from the sheer act of existence itself. Understanding how scientists predict the conditions of such a universe, one that may have come into being from nothing, requires us to first examine what nothing truly means in this context. In the realms of science, nothing is not the absolute void that we might imagine. Instead, it refers to a state devoid of traditional matter and energy, an emptiness that nonetheless can be filled with subtle fluctuations. This is an abstract concept that challenges our everyday understanding of existence. To explore how the universe could emerge from such a state, scientists employ theories from cosmology and physics, which provide a framework for understanding the nature of empty space and the fluctuations within it. One of the most widely accepted ideas is that the universe began with an immense expansion, commonly known as the Big Bang. Before this event, even in what might be considered nothing, energetic fluctuations could have been occurring, leading to the creation of particles and eventually the formation of the universe we know. In order to predict conditions in this early universe, scientists rely on three fundamental elements: theoretical models, observational evidence, and mathematical frameworks. Theoretical models offer a blueprint for how interactions between particles and energy fields might have led to the universe's formation. For example, quantum physics suggests that particles can spontaneously appear due to fluctuations in energy fields, creating the building blocks from which the universe could have emerged. Observational evidence, gathered from cutting-edge telescopes and experiments like particle collisions in advanced laboratories, feeds directly into these models, providing real-world data that supports or refines the predictions made by theorists. One of the most crucial pieces of evidence for understanding the early universe comes from the cosmic microwave background radiation. This faint radiation is a remnant from the universe's infancy, a remnant of the hot, dense state it existed in just after the Big Bang. By studying this radiation, scientists can glean critical information about temperature fluctuations, density variations, and the conditions of the early universe, providing a window into its origins and the processes that occurred in its first moments. Mathematics, too, plays a vital role in this investigation. Complex equations are used to model the interactions between space, time, and energy, helping physicists predict how the universe might have evolved over billions of years. By inputting various parameters into these mathematical frameworks, researchers can create simulations that reveal how galaxies, stars, and other structures might have formed over time. In essence, the combination of theoretical exploration, empirical observation, and mathematical interpretation allows scientists to craft a detailed narrative of the universe's creation, even from what we perceive as a void. Though the idea of a universe arising from nothing may seem paradoxical, these scientific techniques offer a powerful means of understanding how our vast cosmos came into existence. Visualizing nothing itself is a fascinating challenge, one that engages both scientists and artists, albeit from different perspectives. For scientists, nothing is often conceptualized as a vacuum, an empty space devoid of matter. However, even in these vacuums, there is activity. Theoretical models and simulations allow scientists to explore how energy and fields behave in what seems like empty space, offering a deeper understanding of the universe's most fundamental nature. For artists, the notion of nothing is approached differently. Through painting, sculpture, and digital media, artists engage with the idea of absence, often conveying emptiness through minimalist designs or vast, empty spaces. A blank canvas might invoke the feeling of nothingness, prompting viewers to reflect on the concept of absence in their own way. This artistic expression encourages conversations about voids, silence, and emptiness, offering a space for introspection about what nothing truly means. In this sense, both scientists and artists contribute to our understanding of nothing, albeit from different angles. While scientists explore the theoretical and empirical nature of an empty universe, artists offer a more emotional and philosophical reflection on what that absence means to humanity. The convergence of these two approaches, scientific and artistic, helps enrich our comprehension of some of the most abstract and challenging concepts in existence. In popular culture, nothing is often conceived as a complete void, an empty space where absolutely nothing exists. However, this understanding is not entirely accurate in the context of the universe. In fact, the concept of nothing is much more nuanced. Even in vast expanses of space that appear empty, there is still the presence of radiation, particles, and even gravity. Scientists refer to these minute fluctuations as quantum vacuum energy, which means that even in what seems like empty space, there is still activity occurring at incredibly small scales. Furthermore, the universe is filled with dark energy and dark matter, mysterious substances that we cannot directly observe, but that play a pivotal role in shaping the cosmos. Though these elements are invisible to our senses and our instruments, they exert a profound influence on the universe, affecting its expansion and the formation of galaxies and other large-scale structures. Understanding these unseen forces is critical to our comprehension of how the universe behaves, and their discovery has led to a redefinition of what nothing truly means in the context of cosmology. In conclusion, the idea of nothing, both in the scientific and artistic senses, forces us to confront the limits of our understanding. It challenges our preconceived notions of emptiness, space, and time, inviting us to explore the very origins of the universe and the complex forces that shaped it. Through the collaborative efforts of physicists, cosmologists, and artists, we continue to refine our understanding of what it means for something to emerge from nothing, reshaping our perceptions of reality itself. Whether it is through equations, simulations, or visual art, the search for answers to these profound questions enriches our appreciation of the universe and its boundless mysteries. The idea of creating a state of true nothingness is a concept that has intrigued philosophers, scientists, and thinkers alike for centuries. Many may imagine such an idea as a complete vacuum, where time and space cease to exist. However, the intricate relationship between time and space, as understood in physics, challenges this notion. Time and space are not independent entities. They are deeply interwoven into the fabric of the universe. This interconnection means that the removal of one inevitably affects the other. In other words, you cannot truly eliminate one without altering the very nature of the other. This relationship complicates the idea of an absolute nothingness that would exist outside the structure of time and space. Even in the most seemingly empty regions of the universe, time still fluctuates, albeit in an elusive, almost imperceptible manner. The concept of nothing is thus far from simple, as it cannot exist in isolation. It must exist within some framework of time and space, no matter how faint that existence might seem. Furthermore, there is a prevailing idea that the universe originated from a state of nothingness, leading many to think that everything we see today emerged from a void, a true emptiness. This simplified view of the universe's origin has been ingrained in popular understanding, but science presents a more complex picture. The birth of the universe, according to the prevailing theories, did not originate from absolute nothingness. Instead, the universe began from a state that was incredibly dense and hot, a singularity where both matter and energy were packed into a minuscule point. It was not the creation of something from nothing, but rather the expansion and transformation of an already existing state of extreme conditions. This understanding is crucial, for it helps to explain how the universe evolved from that initial dense and hot state to the vast, structured cosmos we observe today. By dispelling these misconceptions, we can gain a deeper understanding of the intricate and often paradoxical nature of reality. It allows us to better appreciate the universe not just as an abstract concept, but as a living, dynamic system that has evolved over billions of years. This knowledge is more than just an academic pursuit. It has real implications for our understanding of existence and our place in the universe. Grasping the origins of the universe provides us with answers to some of the most profound questions humanity has ever posed. How did we get here? What is our role in this vast cosmos? How do we fit into this grand narrative of space and time? Understanding the universe's origins also serves as a catalyst for further inquiry, driving scientific advancements that have far-reaching consequences. The very act of seeking answers to these deep questions propels us forward, encouraging new technological breakthroughs and refining our methods of scientific inquiry. Consider, for example, the tools we've developed to explore distant galaxies, detect cosmic radiation, and map the universe's structure. These technologies have not only advanced our understanding of the cosmos, but they have also led to remarkable innovations that benefit humanity in many unexpected ways. The instruments that help us peer into the depths of space also enable us to detect the faintest signals of ancient radiation, providing valuable insights into the universe's early history. Beyond simply expanding our knowledge, understanding the universe's beginnings fosters innovations that impact various industries. Advances in optics, for instance, have enabled us to create more powerful telescopes and observatories, allowing astronomers to peer further back in time, capturing light from galaxies formed billions of years ago. These same optical innovations have trickled down into other fields, such as medical imaging and diagnostic technologies, improving healthcare and saving lives. Similarly, the development of sophisticated detectors and satellites that study cosmic background radiation has not only deepened our understanding of the universe's infancy, but has also driven progress in telecommunications and data processing. Moreover, the quest to understand the universe's origins has prompted advancements in mathematics and computer science. The need to analyze vast amounts of data gathered from telescopes, satellites, and other instruments has led to the creation of complex algorithms that process these data sets. These computational tools not only enhance our ability to map cosmic structures and the universe's expansion, but also influence other fields such as finance, medicine, and artificial intelligence. The ability to manage and interpret large volumes of data has opened up new possibilities for understanding and controlling systems in various domains of life. Additionally, the study of high-energy particle collisions at facilities such as particle accelerators has provided invaluable insights into the fundamental particles that make up the universe. By recreating conditions similar to those present during the early universe, scientists are able to probe the very fabric of matter. The technologies developed for these experiments have led to innovations in material science, imaging, and engineering, applications that have a direct impact on industries ranging from manufacturing to healthcare. Through all of this, the study of the universe's origins is not just an academic exercise. It is a driving force behind innovation and discovery that shapes our daily lives. Every breakthrough, every new understanding, spurs the creation of new tools, techniques, and technologies that improve the human condition in ways that often go unnoticed but are deeply embedded in the way we live, work, and interact with the world around us. The formation of the universe and the creation of black holes represent two fundamental events in the cosmic timeline, yet they are vastly different in their nature and consequences. The Big Bang, widely accepted as the event that marks the beginning of the universe, was a cataclysmic expansion that unfolded across space and time. From this singular, hot, and dense point, the universe began to expand, allowing space itself to stretch and grow. The universe, as we know it today, is the result of this initial explosion, a continual expansion that has allowed galaxies to move apart from each other, increasing the distances between them at staggering speeds. This process of expansion continues to shape the universe today, as galaxies and stars evolve in ways that are influenced by the initial conditions set in the aftermath of the Big Bang. In stark contrast, black holes are the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own weight. Imagine a towering building suddenly losing its structural supports and collapsing inward under the force of gravity. In a black hole, this process is taken to an extreme. Gravity becomes so powerful that not even light can escape its grasp. The event horizon, the boundary surrounding a black hole, marks the point beyond which nothing can return. Black holes then represent the end of a star's life, not the beginning of everything. While the Big Bang is often seen as the birth of the universe, black holes are more like the final chapters in the life cycles of individual stars. Yet, despite their vastly different origins and consequences, both the Big Bang and black holes are linked by the theme of transformation. The Big Bang marked the origin of galaxies and the very framework of the universe as we understand it, while black holes represent the ultimate collapse and transformation of stars. In some cases, black holes can even influence the evolution of galaxies, dictating their structure and the forces at play within them. The merger of black holes, for instance, creates gravitational waves that ripple through space-time, sending shockwaves across the universe and altering the very fabric of reality itself. Studying these cosmic phenomena, both the explosive birth of the universe and the enigmatic nature of black holes, provides profound insights into the fundamental workings of the cosmos. It allows us to understand the forces that govern the universe, from the violent beginnings of everything to the slow, inevitable collapse of stars into black holes. Each provides a different yet complementary view of the universe's complex structure and evolution. Finally, the study of the death of stars and their transformation into black holes gives us a clearer picture of the broader processes that have shaped the universe. Stars, those brilliant cosmic engines, fuse lighter elements into heavier ones, producing the materials necessary for the formation of planets and life. When a star reaches the end of its life, it can no longer counteract the force of gravity, leading to a cataclysmic collapse. This explosion, known as a supernova, scatters elements like carbon, iron, and oxygen into space, enriching the cosmos with the very building blocks of life. These elements are scattered across the universe, eventually coming together to form new stars, planets, and, in some cases, life itself. The death of a star is thus not an end, but rather a crucial part of the ongoing cycle of cosmic creation. Through these events, scientists are able to piece together the story of the universe, from its explosive birth to the complex processes that continue to shape it. By studying these phenomena, we gain a deeper understanding of the universe's history, its structure, and its future. And in doing so, we uncover the ultimate truths about the nature of existence itself. Through this exploration, we learn not only about the cosmos, but also about ourselves and our place within it. Moreover, the study of stellar life cycles offers a profound window into the intricate processes that shaped the early universe. The elements formed within the cores of stars contribute not only to the next generation of stars, but also to the birth of galaxies, revealing a continuous, interwoven cycle of creation and destruction that stretches across cosmic time. This ongoing cycle plays a crucial role in allowing astronomers to reconstruct a timeline of the universe's evolution. Starting from the Big Bang, when only the simplest, lightest elements existed, to the diverse and complex stars and galaxies we observe in the universe today. Every time we witness the death of a star, we are, in essence, glimpsing both the past and the future of the cosmos. Each stellar demise marks a critical moment that fuels the ongoing transformation of the universe, offering scientists valuable insights into how the cosmos came into being and how it continues to evolve. By closely examining these dramatic stellar phenomena, we not only learn about the individual journeys of stars, but also uncover the grand narrative of the universe itself, a story written in the light of distant stars and etched into the cosmic landscape. Symmetry is a key concept that aids scientists in understanding the origins of the universe. At its most basic level, symmetry in nature means that certain properties remain unchanged, even when viewed from different perspectives or under different conditions. Imagine a perfectly balanced scale. Regardless of how you turn it, the scale behaves the same way, maintaining its balance. This principle holds true for the cosmos as well. Early in the universe's existence, right after the Big Bang, it was believed to be highly symmetrical. In this primordial state, physical laws were uniform throughout space and time, and energy and matter may have been distributed evenly, without any discernible preference for direction or form. This state of symmetry was vital because it provided the foundation upon which the forces and particles that make up everything around us could emerge. However, as the universe expanded and began to cool, this symmetry broke down. This transformation of symmetry into asymmetry set the stage for the formation of distinct particles, such as protons and neutrons, and the forces that govern them, like gravity and electromagnetism. The process can be likened to a river's journey. At first, the flow seems smooth and unbroken, but as it moves along, it encounters obstacles, creating whirlpools and ripples that give the river its structure and variety. Similarly, the breaking of symmetry in the early universe created the fundamental particles and forces that would give rise to the diverse structures we see in the cosmos today. By studying these asymmetries and the transitions they sparked, scientists can gain a deeper understanding of the universe's infancy. They can explore how the early state of the universe influenced the formation of galaxies, stars, and the potential for life itself. The relationship between symmetry and its eventual breakdown holds the key to many of the universe's most profound mysteries, helping us to piece together the story of how everything came to be. This process of symmetry breaking is not only captivating in its own right, but also vital for our broader understanding of physics and cosmology. Asymmetry plays an especially crucial role in shaping the cosmos. Imagine the universe beginning as a vast, uniform field of energy. At this moment, particles and their counterparts, matter and antimatter, would have formed in equal amounts. However, what we observe today, an expansive universe filled with stars, planets, and galaxies, suggests that something went awry during those first moments after the Big Bang. A small imbalance, a slight asymmetry between matter and antimatter emerged, and this imbalance is at the heart of the universe we know today. If matter and antimatter had been perfectly balanced, they would have annihilated each other upon contact, leaving behind nothing but empty space, filled only with radiation. It is this asymmetry that allowed matter to survive and evolve into the stars and galaxies we see today. Without it, the universe would be a vastly different place, devoid of the physical structures that make up the cosmos. Scientists are still actively exploring the origins of this imbalance, delving into theories involving fundamental forces, particle interactions, and even the possible existence of new, undiscovered particles. Understanding how this asymmetry emerged could not only provide crucial insights into the origins of the universe, but also offer clues about its ultimate fate. This imbalance, therefore, is not just a footnote in the universe's creation story, but a foundational aspect that enabled the complexity and diversity of matter to unfold, ultimately leading to our own existence in a vibrant, dynamic cosmos. Quantum entanglement is another extraordinary phenomenon that adds a layer of mystery and complexity to our understanding of the universe. In its simplest form, quantum entanglement refers to the way in which two particles become so deeply interconnected that the state of one can instantaneously affect the state of the other, regardless of how far apart they are in space. This strange relationship suggests that the universe, at its most fundamental level, may not be as separated as it appears. Instead, the behavior of one particle can instantaneously influence the other, creating a connection that transcends our usual understanding of space and time. When considering the origins of the universe, particularly the moments immediately following the Big Bang, quantum entanglement takes on an even more intriguing significance. During these early moments, the universe was incredibly small and dense, and it is believed that all particles were deeply entangled with each other in a way that might have shaped the very fabric of reality itself. As the universe expanded, these entangled particles spread out across vast distances, but their interconnectedness remained. This suggests that even as the universe grew larger, there was a fundamental coordination between distant regions, which may have played a pivotal role in how particles formed into atoms, stars, and eventually galaxies. Some scientists propose that understanding quantum entanglement could shed light on how seemingly distant regions of the universe, separated by enormous distances, can still exhibit correlations. In essence, the universe's earliest moments may have been marked by an intricate web of entangled relationships between particles, helping to influence the course of cosmic evolution in ways that are only now beginning to be understood. This subtle but profound interconnectedness forms an invisible thread that binds the cosmos together, suggesting that even the largest cosmic structures may have their origins in these fundamental, invisible connections. Quantum information theory, a rapidly emerging field, explores the ways in which information is stored, processed, and transmitted at the smallest scales, where the strange rules of quantum mechanics dominate. When we apply this theory to the origins of the universe, it offers unique insights that could radically change our understanding of how everything began. According to quantum information theory, information is as fundamental to the universe as matter and energy. Imagine the universe as a vast, interconnected tapestry, with every thread representing a piece of information. In the earliest moments after the Big Bang, the universe was a hot, dense soup of particles and radiation. Even at this primordial stage, it is believed that information was being exchanged in ways that we now explore through the lens of quantum physics. One of the central principles of quantum information theory is the phenomenon of entanglement. This occurs when particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how distant they may be. This interconnectedness, established in the earliest moments of the universe, may have played a critical role in shaping the early structure of the cosmos. By studying quantum entanglement and other aspects of quantum information theory, scientists are beginning to unravel how the universe's most fundamental properties were shaped by the flow of information on the quantum level. This research could lead to new and profound insights into the birth of the universe and the forces that continue to shape it. Quantum information theory has revolutionized the way we think about knowledge itself, proposing that information is not just a concept we use to describe things, but a vital resource, akin to energy, essential to understanding the universe's vast processes. As the universe continues to expand, how information behaves, spreads, and transforms could hold the key to some of the deepest mysteries of existence. Scientists are beginning to recognize that by examining how information changes in extreme conditions, we might unlock secrets about the universe's very beginning, shedding light on how it has evolved over time. This shift perspective opens a new door in cosmology and physics. The behavior of information could, for instance, provide clues to elusive phenomena like dark matter and dark energy, two mysterious forces that seem to control the universe's structure and expansion, yet remain nearly invisible to our most advanced instruments. Researchers are increasingly focusing on how information can be manipulated and understood within the strange realm of quantum mechanics. This exploration could ultimately lead to groundbreaking insights into the universe's origins and its continuous transformation. The more we understand about how information flows and changes, the closer we get to understanding not just how the universe began, but also how it reshapes itself over time. The implications of these discoveries are profound, potentially altering our very concept of reality. As the boundaries between the realms of physics, information theory, and the nature of reality itself blur, we may be on the cusp of a paradigm shift. These realizations promise to challenge our understanding of everything from the formation of galaxies to the very building blocks of existence. Several exciting space missions are currently on the horizon, each designed to unravel these cosmic mysteries and deepen our understanding of the universe's early moments. One of the most anticipated is the James Webb Space Telescope, which is set to observe distant galaxies and the formation of stars and planets in unprecedented detail. Equipped with cutting-edge infrared technology, it will allow scientists to peer further back in time than ever before, providing fresh insights into the critical moments just after the Big Bang, when the universe was in its infancy. Webb's ability to capture faint light from some of the earliest galaxies will serve as a time machine, offering a glimpse into the universe's distant past. The European Space Agency's Euclid mission is another landmark project in the pursuit of understanding the universe's hidden dimensions. This satellite aims to map the geometry of the dark universe, studying the distribution of dark matter and dark energy by observing large-scale cosmic structures. By tracing how these invisible components interact with visible matter, Euclid hopes to shed light on the universe's evolution over billions of years, further enhancing our comprehension of its vast, unseen components. Meanwhile, NASA's series of exoplanet missions are expanding our horizons by exploring the atmospheres of distant planets orbiting stars far beyond our solar system. These missions will indirectly help us understand the chemical ingredients present in the early universe, as well as how these building blocks contributed to the formation of planets that could one day support life. As scientists study these exoplanets, they will gain clues about the environments where life could potentially arise, bringing us closer to answering the age-old question of whether we are alone in the cosmos. On Earth, ground-based projects are also playing a critical role. The Large Synoptic Survey Telescope, for example, aims to create the most detailed map of the cosmos to date. By capturing vast amounts of data from the sky, the telescope will help scientists understand how galaxies formed, evolved, and interacted throughout history. These projects not only aim to deepen our understanding of the early universe, but also serve to inspire new generations of scientists and space enthusiasts, sparking curiosity about the universe and humanity's place within it. Through these groundbreaking missions, the complex puzzle of how everything began is slowly coming together. These space observatories, telescopes, and satellites are providing glimpses into the ancient past of the universe, offering insights that were once thought impossible to obtain. International collaboration in space research has been integral to this progress. By pooling together diverse expertise, resources, and perspectives, countries across the globe are working together to tackle questions that no single nation could solve alone. International partnerships enable scientists to share access to cutting-edge technologies and state-of-the-art facilities. Each nation brings unique capabilities to the table: advanced telescopes, powerful laboratories, and sophisticated spacecraft, which can be combined to conduct more comprehensive and rigorous investigations. These global efforts lead to large-scale projects such as space missions to study cosmic phenomena or experiments designed to replicate the conditions that existed just after the Big Bang. The synergy between different nations helps create a more holistic approach to space exploration, with observations across various wavelengths and instruments providing richer, more diverse data. By collaborating on such a massive scale, the chances of uncovering hidden patterns or anomalies that might reveal new truths about the universe are greatly enhanced. Cultural exchange is also an essential component of these collaborations. As scientists from different countries work together, they bring their unique methodologies, problem-solving strategies, and viewpoints. This diversity of thought fosters innovation and creativity, leading to breakthroughs that might never have emerged in a more homogeneous environment. Moreover, the global cooperation that emerges from these partnerships creates a shared sense of purpose, a collective drive to explore the unknown and contribute to humanity's expanding knowledge of the cosmos. The cooperative spirit of these international efforts not only strengthens our understanding of the universe's origins, but also fosters a deeper sense of unity among nations. By collaborating across borders, we collectively confront the mysteries of existence, forging a legacy that transcends national boundaries and benefits all of humanity. At the cutting edge of these explorations, artificial intelligence, AI, and machine learning are poised to become indispensable tools in decoding the universe's origins. Think of these technologies as highly advanced assistants, capable of processing vast amounts of data far faster than any human could. Every time a new observation is made, whether from space telescopes or particle accelerators, the amount of data collected is often overwhelming. AI can sift through this deluge of information, detecting patterns and trends that might otherwise go unnoticed. One area where AI is proving invaluable is in the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light holds clues about the universe's earliest moments. By analyzing subtle variations in this radiation, AI algorithms can help scientists understand how the universe expanded and evolved. These systems are trained on existing data, allowing them to predict new findings and guide scientists in the next stages of their research. In addition to analyzing data, AI is transforming the way researchers simulate cosmic events. By making real-time adjustments to models based on actual observations, AI helps create more accurate simulations, enabling researchers to test hypotheses quickly and efficiently. These tools not only speed up the process of discovery, but also open new avenues for inquiry. As AI becomes more advanced, it will encourage scientists to ask new questions about the nature of the universe and push the boundaries of our understanding. Beyond just processing data, AI and machine learning are also essential in recognizing and classifying celestial phenomena, such as supernovae or distant galaxies. By automating these tasks, AI allows astronomers to focus on interpreting the broader implications of these discoveries, In the coming years, AI will be an invaluable ally in the quest to piece together the universe's grand narrative, helping us to explore the deepest mysteries of existence. As we continue to delve into these complex topics, education systems can play a pivotal role in making the universe's mysteries more accessible. Teachers can help students relate abstract concepts like the origins of the universe by tying them to familiar ideas. For example, they could explain how something can arise from nothing by asking students to imagine a blank canvas turning into a beautiful painting. This analogy provides a starting point for discussing more complicated cosmological theories. Breaking down the history of cosmological thought can also help contextualize modern discoveries. By examining how ancient civilizations viewed the cosmos and how their understanding evolved, students gain a deeper appreciation for the ideas that led to today's breakthroughs. It is equally important to introduce basic astronomy principles, such as the nature of the universe, the formation of galaxies, and the fundamental forces at play, like gravity. Hands-on activities can help make these ideas more tangible. For example, teachers might use balloons to demonstrate how space itself is expanding, mirroring the universe's expansion from a singular point. Visual aids, simulations, and videos of phenomena like the Big Bang or cosmic inflation can further captivate students, allowing them to visualize concepts that might otherwise be difficult to grasp. By fostering curiosity and providing students with the tools to explore these questions, education can help inspire the next generation of scientists and thinkers, encouraging them to delve into the mysteries of the universe and contribute to the ongoing quest for knowledge. Through collaboration, technology, and education, we are poised to uncover more secrets about the cosmos than ever before, pushing the limits of our understanding and unlocking the potential for discoveries that will shape our future. Encouraging critical thinking and discussions in educational environments creates opportunities for students to dive deeply into the core mysteries of existence and reality. By fostering spaces where questions of profound significance can be explored without fear of judgment, educators enable students to engage directly with complex material, not only to understand scientific concepts, but also to grasp broader philosophical and existential implications. This approach invites students to question the very nature of the universe itself, challenging them to explore not only the how of scientific phenomena, but also the why, questions that have driven human thought for millennia. When physics and philosophy intersect in educational settings, students can investigate not just the observable world, but also the deeper meanings and potential purposes that lie beneath it. This blending of disciplines nurtures curiosity about the universe, motivating students to think critically and ask bold questions that encourage intellectual growth. Through these methods, educational systems are uniquely positioned to demystify complex cosmological concepts and inspire a broader understanding of our universe. What were once impenetrable mysteries can become accessible to all, providing new avenues for both learning and exploration. The public's perception of the universe's origins has undergone a radical transformation, largely due to advancements in scientific discovery. In ancient times, creation myths shaped the way people understood the cosmos. These stories, often involving gods or supernatural forces, offered simple, relatable explanations for a universe that seemed otherwise impenetrable. Over time, however, and especially during the Enlightenment, humanity began to adopt a more empirical and scientific perspective. The geocentric model, which posited Earth as the center of the universe, was eventually replaced by the heliocentric view, championed by early astronomers such as Copernicus and Galileo. Their groundbreaking work demonstrated that Earth, like the other planets, revolved around the sun, a shift that radically altered humanity's understanding of its place in the cosmos. The most significant leap in cosmological understanding occurred in the 20th century with the development of the Big Bang theory. This theory posits that the universe began as an incredibly hot and dense point, then expanded rapidly, giving birth to the vast cosmos we see today. Observations of cosmic background radiation, which are remnants of that early universe, provided compelling evidence for this model. As people learned about this scientific perspective, the narrative surrounding the origins of the universe shifted from one based on myth and superstition to one grounded in observation, reason, and empirical data. Further discoveries, including the observation of galaxies moving away from each other, strengthen the notion of an expanding universe. This revelation not only deepened interest in cosmology, but also prompted deeper questions. What existed before the Big Bang? If the universe is expanding, what lies at its edges? This shift in our understanding marked the beginning of a new intellectual era, one driven by the pursuit of knowledge about the birth, nature, and underlying principles of the universe. Today, the frontiers of cosmology are being pushed even further with the introduction of theories about dark matter and dark energy, substances that, while undetectable by our senses, seem to account for most of the mass and energy in the universe. These discoveries have made the narrative of cosmic origins even more complex, suggesting that our current understanding is just a glimpse of a much larger and more intricate reality. The public's awareness of this ongoing process of discovery is growing. More and more, people are coming to realize that our understanding of the universe is still in its infancy, and new discoveries are emerging at an accelerating pace. This increasing awareness only fuels curiosity about the cosmos. While scientific theories continue to evolve, so does our collective fascination with the vast, enigmatic universe. People today are not only accepting scientific explanations for the universe's origins, but are also captivated by them, driving renewed interest in science and space exploration. In this way, the evolving understanding of the universe's origins exemplifies humanity's unyielding journey toward greater knowledge, continually reshaping our perception of our place in the cosmos. Cosmic horizons represent the boundaries of our observable universe. Picture standing at the edge of a great ocean where the horizon limits your view of everything beyond it. In the cosmos, these horizons define the furthest distance we can see, a boundary determined by the finite speed of light and the expansion of the universe. At the moment of the Big Bang, roughly 14 billion years ago, the universe was an intensely hot and dense mass filled with energy and matter. As the universe expanded, light from this early phase began to travel through space. However, due to the ongoing expansion of the universe, there are regions so far away that light from those regions hasn't had time to reach us. This creates what scientists refer to as a cosmic fog, a kind of veil that limits our ability to study the earliest moments of the universe's existence. This limitation is significant when we try to learn about the universe's birth. While we can gather some information from ancient light in the form of the cosmic microwave background, CMB, radiation, remnants from the early universe, there are countless regions we are unable to study. There are parts of the cosmos from which we cannot receive light or any other signals, preventing us from directly observing much of what happened during the first moments of the universe's existence. As a result, our understanding of the universe's origins is not based on direct observation, but on scientific models and inferences constructed from the data we do have. In essence, cosmic horizons do not limit our understanding by what exists, but by the very fabric of space and time itself. Beyond the observable universe lies a realm of speculation and mystery. Some scientists propose that the universe is infinite, stretching far beyond the limits of our observational capabilities. According to this view, there are countless galaxies and phenomena that we have yet to explore, each beyond the reach of our telescopes and instruments. Another fascinating possibility is that our universe might be just one of many in a vast multiverse, each universe existing as a separate bubble in an ocean of infinite possibilities. In this view, each bubble, each universe may possess its own set of physical laws, possibly giving rise to entirely different realities. These theories challenge our fundamental understanding of existence, suggesting that there could be other universes where the laws of space and time unfold in ways we can hardly imagine. These ideas touch on the concept of nothing. Traditionally, nothing has been understood as the complete absence of matter, space, and time. It is the void, the ultimate emptiness. However, in the strange world of quantum physics, nothing sometimes teams with activity. In the quantum vacuum, particles can appear and disappear spontaneously, flaring into existence and then vanishing again. This phenomenon challenges our conventional ideas about nothing, suggesting that even in the absence of matter, activity may still occur on a fundamental level. Thinking about what lies beyond the observable universe forces us to reconsider the very nature of existence, urging us to explore the boundaries of nothing and everything in ways that were once beyond our comprehension. Cosmic inflation is a critical concept in understanding the universe's origins. Immediately after the Big Bang, the universe was tiny, dense, and incredibly hot. But then, in an extraordinarily brief period, on the order of fractions of a second, the universe underwent a dramatic, exponential expansion. This rapid inflation helped the universe grow from a size smaller than a proton to a vast, sprawling cosmos, many times larger than the observable universe today. Inflation explains several key features of the universe that otherwise seem puzzling. For example, the uniformity of the cosmic microwave background radiation across the universe can be understood as a result of inflation, which spread out regions of space that were once in contact with one another. This helped create the even temperature distribution observed in the CMB. Inflation also addresses the problem of the universe's flatness, its shape, or lack of curvature. Without inflation, the universe would not appear as flat as it does today. Instead, inflation provided a mechanism for stretching the universe evenly in all directions, smoothing out irregularities and ensuring that the structure of the cosmos remains balanced. This understanding of inflation is essential for explaining how the universe evolved from a tiny, hot, dense point into the vast expanse we observe today, filled with galaxies, stars, and planets. Overall, the concept of cosmic inflation is a cornerstone in our understanding of the universe's development. It not only provides a framework for explaining the observable features of the cosmos, but also raises profound questions about the transition from nothing to the dynamic, complex universe that we experience today. It is a reminder of the immense, ongoing journey toward unraveling the deepest mysteries of existence. To understand the origins of our universe, we must begin by considering the concept of nothing. Yet this nothing does not simply refer to an empty void. In fact, it's a far more complex idea, a state where neither energy, matter, nor space as we know them existed. Imagine a time before the Big Bang, when the universe was a realm of pure potential, existing in an entirely different form than we experience today. A fascinating model to explain this is the idea of quantum fluctuations, tiny, spontaneous changes in energy that occur within invisible fields permeating all of space. These fields, known as quantum fields, are a fundamental part of the universe's underlying structure. In this model, a minuscule region of these quantum fields could suddenly experience a dramatic surge in energy. This surge, though momentary, might be enough to trigger a chain reaction that forever alters the fabric of the cosmos. Such an event, referred to as inflation, would have marked the beginning of our universe. The energy generated by this fluctuation would stretch space itself, rapidly expanding it and transforming the universe from a state of nothing into one brimming with energy and matter. This explosion in space is the foundation of what we recognize today as the Big Bang. Another possibility for how the universe came into existence is through the notion of a false vacuum. In this theory, the universe existed in a state that appeared empty but was actually full of energy that had not yet manifested as matter. It's akin to a pot of water that seems calm before it begins to boil, where unseen energy rises, waiting for the right moment to burst forth. If the false vacuum were to become unstable, it could release this energy in a dramatic burst, again sparking inflation and the birth of our universe. Some scientists have proposed even grander models where our universe is but one of many, an individual bubble floating in an immense ocean of other universes. In such a scenario, our universe could have formed through fluctuations that spontaneously create new universes, each with its own unique properties, all evolving through processes of inflation. While these models vary in specifics, they share a core idea. Even from a state of nothingness, the universe can arise from fluctuations in quantum fields or energy pockets. These theories offer intriguing new ways of thinking about how the cosmos began. Even though definitive proof is still out of reach, these models push the boundaries of our understanding and invite us to think about the universe's origins in more imaginative and profound ways. A critical concept in understanding the evolution of the universe from this initial state of nothingness is entropy. In simple terms, entropy refers to the amount of disorder or randomness in a system. The early universe, at its inception, was incredibly hot and dense, a state often referred to as the Big Bang. In this dense condition, everything was packed together in a highly ordered manner, which meant that entropy or disorder was low. As the universe began to expand and cool, this initial order started to break down. Matter and energy began to spread out across space, and as they did, entropy began to rise. To grasp this idea, picture a container of gas. When all the gas molecules are clustered in one corner of the container, the system has low entropy. However, as the gas spreads throughout the container, the disorder increases, and so does the entropy. This movement towards greater disorder played a central role in the formation of the stars, galaxies, and the other structures that populate the universe today. It's important to note that this increase in entropy was not random. It was part of a broader process that shaped the universe's development. As matter began to clump together under the force of gravity, it formed stars and galaxies. Along the way, energy was released in the form of light, heat, and other radiations, which further contributed to the unfolding complexity of the universe. This energy release is an essential mechanism for how order can emerge locally, even as overall entropy increases across the universe. In the broader scope, entropy plays a central role in how the universe evolves, according to the second law of thermodynamics. This law states that in an isolated system, entropy will tend to increase over time. So while the universe might have begun in a state of relatively low entropy, it has since transitioned into a much more complex and disordered state, one filled with stars, planets, and even life. In this context, entropy is not just about randomness, it's a key driver of the universe's transformation. It's what allows stars to form, galaxies to coalesce, and new structures to emerge. However, even as the universe's entropy rises, we see that complexity can still arise from simplicity. For example, when stars die, they often explode in supernovae, scattering elements across space. This may seem like an increase in disorder, but it also sets the stage for new generations of stars to form. So, even as the universe grows in disorder, it simultaneously creates new cycles of complexity. Local pockets of order emerge within the broader rise of entropy. On Earth, this process of increasing entropy also allowed for the development of life. The local reduction of entropy, such as the formation of living systems, stands in stark contrast to the overall increase in disorder across the cosmos. These opposing forces, the spread of disorder and the formation of complex, ordered structures, serve as the foundation for much of the universe's ongoing evolution. To understand how all of this happened, scientists have turned to computer simulations. These simulations serve as powerful tools for modeling the universe's early conditions and testing hypotheses about its origins. At the core of this computational approach is the understanding that the universe operates according to a set of physical laws, such as gravity and thermodynamics, that can be modeled through algorithms. These models allow researchers to simulate the universe's evolution from its highly energetic beginnings to the formation of galaxies, stars, and planets. By adjusting different variables in these simulations, such as the density of matter or the strength of gravitational forces, scientists can observe how these changes affect the development of cosmic structures. This ability to recreate early universe conditions in a virtual environment gives researchers a unique window into cosmic history. Moreover, simulations can replicate significant events like the Big Bang itself, offering invaluable insights into how the universe began. The results of these simulations are then compared to actual astronomical data gathered from telescopes and satellites. If the simulation's outcomes closely match observed data, it strengthens the validity of the hypothesis being tested. This iterative process, constantly refining simulations in light of new data, helps scientists better understand the universe's origins. These computer-based explorations provide both imaginative insights and scientifically grounded conclusions that allow us to probe the mysteries of the cosmos in ways that would be impossible through observation alone. The earliest moments of the universe are among the most captivating and mysterious periods in the history of the cosmos. Thanks to advancements in astrophysics and particle physics, our understanding of these moments has grown significantly. For instance, through computer simulations, scientists can recreate the extreme conditions of the early universe, including the formation of basic particles like protons and neutrons. These particles eventually combine to form simple atoms, primarily hydrogen and helium. A breakthrough in our understanding came with the discovery of the cosmic microwave background radiation, which represents the faint afterglow of the Big Bang. This radiation offers crucial clues about what happened shortly after the universe began. In addition, particle accelerators, devices designed to simulate the high-energy conditions of the early universe, have allowed scientists to test theories about the fundamental forces and particles that shaped the universe's evolution. The discovery of the Higgs boson, for example, has helped us better understand how particles acquire mass, which is essential for comprehending the fabric of the early universe. As these discoveries continue to accumulate, we are gradually piecing together a more detailed picture of the universe's remarkable and mysterious origins. Through the use of simulations, experiments, and observational data, we are uncovering the intricate processes that have shaped the cosmos from its very beginnings, providing answers to questions that have puzzled humanity for millennia. The advancements in observational astronomy have dramatically transformed our understanding of the universe's origins and its evolution. Over the past few decades, astronomers have gained new insights into the distribution of galaxies and cosmic structures, which have provided critical evidence about how the universe expanded from a hot, dense state into the vast, complex cosmos we witness today. These observations have reinforced and refined several theoretical models of cosmic inflation, a concept that explains the rapid and immense expansion of the universe in the moments immediately following the Big Bang. In fact, this theory suggests that, shortly after the universe began, it underwent a tremendous growth spurt that shaped its very structure, leading to the formation of galaxies, stars, and other celestial phenomena. As these new breakthroughs accumulate, they offer a richer, more detailed understanding of the birth of the universe and the intricate interplay of particles and forces that governed its earliest moments. The story of the universe's emergence, once confined to the realms of speculation, has now become a clearer, more scientifically grounded narrative, and with each observation, our understanding of our cosmic origins becomes more profound. At the same time, the realm of art has found new inspiration in these scientific theories, bridging the gap between complex ideas and human emotion. Artists, captivated by the mind-boggling concepts surrounding the origins of the universe, often translate these intricate scientific notions into visual masterpieces that ignite imagination. The idea that the universe emerged from a state of absolute nothingness is, to many, a fascinating yet perplexing notion. This abstract idea has become the focal point of numerous artistic representations. These works often depict vast, dark spaces, punctuated by shimmering stars, symbolizing the transition from an empty, formless void to the vibrant, dynamic universe we inhabit today. The sheer scale of this transition, moving from nothing to something, is a powerful theme in artistic renditions, invoking feelings of awe, wonder, and even the fragility of existence itself. Some artists choose to visualize the Big Bang itself, capturing the immense energy and chaotic beauty of the moment when the universe exploded into being. Through dynamic patterns and explosive colors, they express the intensity of creation in ways that transcend pure science. Others, in contrast, focus on the concept of void, using stark contrasts between light and dark to highlight the surreal nature of this shift from nothingness to existence. As these artists explore these profound cosmic themes, they also wrestle with deep philosophical questions. What does it mean for something to emerge from nothing? How does such an event challenge our conventional understanding of reality and existence? These questions are not only central to the work of the artists, but also serve as an invitation to the viewers to reflect on their own perceptions of life, the universe, and their place within it. Through their interpretations, artists help to bring to life the intangible and often incomprehensible ideas of cosmology, making them more accessible and emotionally resonant for a broader audience. Their work doesn't just aim to inform, it invites viewers to feel, to wonder, and to reflect. Moreover, the art of storytelling has emerged as an invaluable tool in presenting the abstract and complex nature of cosmology in a way that captivates and engages audiences. Storytelling techniques enable intricate scientific ideas to come alive by embedding them within a narrative framework. At its core, effective storytelling transforms what could otherwise be an intimidating or abstract concept into a narrative that evokes curiosity, intrigue, and understanding. One of the most powerful techniques is the use of characters. When a scientist or explorer is portrayed as the protagonist, it humanizes the journey of discovery. The character might encounter obstacles, make groundbreaking discoveries, and experience the same awe and wonder that we feel when learning about the universe. This turns the quest for knowledge into an adventure, one full of excitement and challenges, not simply a series of cold facts and figures. Another compelling tool in storytelling is the use of analogies and metaphors. Complex phenomena like the expansion of the universe can be difficult to grasp, but comparisons to everyday experiences, such as likening it to inflating a balloon, can make these concepts much easier to visualize and understand. The analogy helps audiences comprehend how galaxies move apart as space itself stretches. Furthermore, a well-crafted narrative structure that unfolds sequentially, like a story with a clear beginning, middle, and end, can help contextualize the subject. For instance, starting with humanity's earliest observations of the stars, progressing through our development of modern astrophysics, and concluding with the cutting-edge discoveries of today, provides a logical progression that mirrors the growth of our understanding over time. Such a structure mirrors the process of scientific discovery itself, making the material both educational and captivating. Additionally, visual storytelling plays a crucial role in communicating cosmic phenomena. Supernovae, the birth of black holes, and the evolution of galaxies can be beautifully illustrated with stunning graphics and visuals that not only enhance understanding but also stir a sense of awe. These visuals allow audiences to experience the universe's grandeur and beauty in a visceral way, making abstract concepts more tangible and emotionally resonant. Ultimately, when complex cosmological ideas are framed within a captivating narrative, they become accessible, inspiring, and thought-provoking. Storytelling serves as a gateway for viewers to explore the mysteries of the universe, while simultaneously simplifying the scientific concepts that underpin our understanding of reality. It invites us to embark on a journey of exploration, one that deepens our appreciation for the vastness and complexity of the cosmos, while also fostering a deeper understanding of our place within it. The concept of evolutionary cosmology offers a fascinating and ever-evolving perspective on the universe's origins, one that sees the cosmos not as a static entity, but as a dynamic process that unfolds over immense stretches of time. Unlike traditional cosmological views, which often emphasize a singular moment of creation, evolutionary cosmology sees the universe as an ongoing process, much like biological evolution on Earth. At the heart of this idea is the belief that just as life evolves through natural selection, so too does the universe. Galaxies form, evolve, and eventually die, only to give rise to new cosmic structures in a continual cycle of renewal. The universe, then, is not merely a passive backdrop for the events we observe, but an active participant in its own evolution. This perspective challenges the classical view of the universe, which often suggests a defined starting point and, at times, a predetermined fate. In contrast, evolutionary cosmology suggests that the universe's path is shaped by countless ever-changing factors, giving it the potential to evolve in various directions. Galaxies might form and disperse, stars may explode and die, and new cosmic phenomena could arise. The universe is not fixed, it is continually in motion, constantly evolving, and always adapting. Moreover, this viewpoint opens the door to the intriguing possibility of a multiverse, where our universe is just one of many, each experiencing its own unique evolutionary path. This idea suggests that the cosmos is far more complex and vast than we can currently comprehend, and that our universe is merely a small part of a much larger, more intricate existence. This perspective also invites questions about the future. How will the universe continue to evolve long after we are gone? What cosmic events await us as the universe moves forward on its journey? Evolutionary cosmology encourages curiosity and wonder about the future, urging us to think beyond our current moment and consider the ongoing, ever-changing nature of the cosmos. It pushes us to view the universe as a living, evolving entity, one that continues to adapt and change in ways that are often beyond our comprehension. When we speak of nothing in the context of the universe's origins, we are not referring to an absolute void in the traditional sense. Instead, we are talking about a state of potential, a cosmic emptiness in which conventional matter, energy, time, and space did not yet exist. This nothing is not the absence of everything. Rather, it is a fertile ground teeming with quantum fluctuations, tiny minute changes that occur even in the most empty-seeming space. These fluctuations may have sparked the creation of the universe itself. In evolutionary cosmology, this initial nothing is seen not as a finality, but as a starting point, an opportunity for evolution and transformation. From this state of potential, particles began to form, merge, and evolve into atoms, stars, galaxies, and eventually planets. The universe, like life on Earth, is constantly evolving, influenced by the fundamental laws of physics that govern how everything interacts. As we explore this journey from nothing to the richly structured cosmos we know today, we gain a deeper understanding of our place in the universe. The universe, from its earliest moments to its present complexity, is a dynamic and evolving entity, a grand narrative that continues to unfold with us as part of its ongoing story. Understanding this process helps us see how everything, including ourselves, is intricately woven into the ever-changing fabric of the cosmos. In the ongoing quest to understand the universe, scientists have developed several competing theories to explain its fundamental forces and particles. One of the most ambitious is string theory, which proposes that the most basic building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings, depending on their vibrational modes, can give rise to the myriad particles that make up everything we observe in nature. String theory aims to unify quantum mechanics and general relativity, suggesting that at the smallest scales, the laws of physics behave in ways that are fundamentally different from our macroscopic experience. Another competing theory is loop quantum gravity, which offers a different approach. Instead of relying on strings, it proposes that space itself is made up of tiny loops, forming a network woven into the fabric of the universe. This theory seeks to reconcile the differences between quantum mechanics and gravity, aiming to provide a unified description of the cosmos. Meanwhile, the idea of the multiverse suggests that our universe is just one of many, each with its own set of physical laws. This perspective challenges our notion of a singular reality, proposing that our universe is only a small part of a much larger, more complex system. Lastly, the concept of emergent gravity challenges our understanding of space and time. This theory suggests that gravity is not a fundamental force, but emerges from deeper microscopic interactions. By framing gravity in terms of quantum physics and information theory, emergent gravity could reshape our understanding of the very fabric of the universe. Each of these theories, string theory, loop quantum gravity, the multiverse, and emergent gravity, offers a unique perspective on the universe and its underlying principles. As scientists continue to explore these frameworks, they strive for a more complete understanding of the cosmos, one that may one day unify these various ideas into a single narrative of existence. It is a journey filled with complexity, uncertainty, and awe, a journey that continues to push the boundaries of human knowledge and deepen our appreciation of the universe and everything it contains. The origins of the universe and the very idea of how everything began continue to provoke deep and endless questions. While modern scientific theories offer remarkable insights into how a universe could emerge from nothing, they also reveal the vast unknowns that persist. What truly sparked the initial fluctuations that set everything in motion? What lies beyond the boundaries of our universe? Although frameworks like the Big Bang Theory describe the birth of the cosmos, they cannot definitively answer these ultimate questions. Instead, they remind us that the search for understanding is far from complete. Each theory opens new avenues for inquiry, urging us to explore further into the nature of existence, the peculiar rules that govern its evolution, and the true origins of reality itself. This quest to understand the universe's beginnings is not simply an academic pursuit. It stems from a profound human curiosity about our place in the cosmos and the nature of everything surrounding us. For scientists, the inquiry is driven by an unrelenting desire to uncover the fundamental physical laws and forces that have shaped the very fabric of space and time. They are captivated by the possibility of finding the principles that govern the universe, including how all things emerged from what many refer to as a singular event, the Big Bang. Philosophers also engage deeply with this question, though their approach is more contemplative and existential. They wonder about the deeper implications of such origins. If the universe came into being from nothing, what does that say about the meaning of existence? What is humanity's place in this vast, often indifferent universe? Are we merely the result of chance, or is there a deeper, more intentional design at play? These philosophical questions complement scientific exploration as both fields converge in a shared quest to understand the universe's fabric. Together, they form a dialogue that feeds the pursuit of knowledge, a knowledge that seeks not only to understand how stars and galaxies formed, but also to comprehend the deeper significance of our tiny speck in the boundless expanse of the cosmos. At the heart of the scientific exploration lies the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This remnant of the universe's earliest moments offers us a glimpse into the past, a key piece of the puzzle that scientists have long sought to put together. Each new discovery sparks further inquiry, leading us to ask not just how the universe works, but why it exists at all. What is the significance of our small, fleeting presence in a universe that has spanned billions of years? As researchers continue their work, these questions become ever more pressing, urging us to search for meaning not only in the mechanics of the cosmos, but also in the narrative of existence itself. While science drives the quest for knowledge, it is essential to recognize that our understanding of the universe's origins is shaped by more than just empirical evidence. Personal beliefs, cultural backgrounds, spiritual teachings, and life experiences all influence how we interpret the vast unknown. For some, belief in creation stories rooted in religious traditions provides a sense of meaning and purpose. These narratives often present a divine hand as the creator of the cosmos, infusing the scientific theories with a spiritual dimension. Others may take a more scientific approach, focusing on models like the Big Bang theory, which explains the universe's origins from a hot, dense state and its ongoing expansion. However, even those who embrace scientific theories may find themselves contemplating the possibility of design, seeing the intricacy of the universe as evidence of a greater purpose behind it all. In addition to personal belief systems, emotions and psychological factors can play a powerful role in shaping how individuals respond to the idea of the universe's beginnings. The vastness of the cosmos, with its infinite expanse and seemingly limitless complexity, can invoke feelings of awe or fear. These emotional reactions may shape one's search for answers, as individuals seek explanations that resonate with their inner sense of wonder or trepidation. In this way, our relationship with the universe is deeply personal, influenced not only by facts and figures, but by our own emotional and psychological landscapes. Our beliefs, whether scientific, spiritual, or philosophical, create a lens through which we view the cosmos, offering meaning and purpose in a universe that often feels incomprehensible. Over the centuries, countless brilliant minds have contributed to our understanding of the universe's origins, and their work continues to guide modern thought. Albert Einstein, one of the most influential figures in the history of science, revolutionized our understanding of time, space, and gravity with his theory of relativity. His groundbreaking insights laid the foundation for much of today's cosmology, raising important questions about the universe's birth. Building on Einstein's ideas, Georges Lemaitre proposed what would later become known as the Big Bang theory, suggesting that the universe expanded from a singular, hot, and dense point, a theory that fundamentally changed the way we understand cosmic origins. In the 20th century, Edwin Hubble's observational work provided compelling evidence for Lemaitre's theory. By discovering that galaxies were moving away from us, he demonstrated that the universe is indeed expanding, supporting the notion that it began from a single dense state. More recently, figures like Stephen Hawking and Alan Guth have made significant contributions to our understanding of the universe's early moments. Hawking's work on black holes and singularities offered insight into the conditions that may have existed at the very birth of the universe, while Guth's theory of cosmic inflation explained the rapid expansion that occurred just after the Big Bang. These thinkers, alongside many others, have shaped our understanding of the universe's origins. They've sparked new questions, encouraged deeper exploration, and laid the groundwork for the research that continues today. Much like early explorers mapping out uncharted lands, these pioneers have provided the tools and knowledge that allow today's scientists to continue probing the mysteries of the cosmos. The legacy of early astronomers and physicists remains central to our ongoing research. Figures such as Galileo, who used the telescope to challenge prevailing views of the cosmos, and Einstein, who reshaped the very fabric of time and space, set the stage for our modern understanding of the universe. Their contributions fundamentally altered how we perceive our place among the stars, revealing that Earth is not at the center of the universe, but rather just one tiny speck in a vast, expanding cosmos. Today, scientists continue to investigate these foundational concepts, delving into phenomena such as dark matter and dark energy, which make up the vast majority of the universe but remain largely elusive. These ongoing efforts represent the continuation of a search for knowledge that stretches back centuries. As technology advances, our ability to observe and measure the cosmos grows exponentially. Advanced telescopes, particle accelerators, and space missions all offer new ways to observe and analyze the universe, bringing us closer to answering some of the most profound questions about our origins and our place in the cosmos. Technological advancements are not only shaping our understanding of the universe, but also helping bridge the gap between science and spirituality. With powerful telescopes and space observatories, we can observe galaxies and cosmic events from billions of light years away, offering new perspectives on the formation of stars, planets, and galaxies. This ability to peer into the depths of space allows us to gain a clearer picture of the universe's beginnings, influencing how people of various spiritual and religious backgrounds think about creation. Moreover, technology allows us to explore the building blocks of existence in unprecedented ways. High-energy particle colliders, for example, explore the subatomic particles that constitute matter itself, offering clues to the conditions that existed during the earliest moments of the universe. This scientific investigation into the very nature of reality intersects with spiritual and philosophical questions about the meaning of existence and the ultimate purpose behind the cosmos. The role of communication technology also cannot be underestimated. The rise of the internet, social media, and online platforms has allowed scientists and spiritual thinkers to exchange ideas more freely than ever before. This cross-pollination of perspectives fosters a richer understanding of the universe, as different schools of thought come together to explore the mysteries of existence. In addition, immersive technologies like virtual reality allow us to simulate cosmic events and experience the wonders of the universe firsthand, evoking feelings of connection and awe that can transcend the boundaries between science and spirituality. Ultimately, technology not only accelerates our scientific understanding of the universe, but also fosters a deeper connection to the cosmos, enriching our spiritual and philosophical perspectives. It has become a tool that bridges the gap between the empirical and the mystical, offering new ways for individuals to engage with the profound questions that have always shaped our view of the universe. At the heart of these discussions lies the question of how the universe could emerge from nothing. On one side, scientists propose theories like the Big Bang, where everything, space, time, and matter, emerged from an incredibly dense point. What existed before this moment remains a profound mystery. Theories such as quantum fluctuations, where particles arise from a vacuum, suggest that the universe could have emerged from a state of nothingness. Yet these ideas raise deep philosophical and existential questions about the true nature of nothing. On the other side, many religious and spiritual traditions offer creation stories that describe the intentional act of a divine being bringing the universe into existence. These perspectives offer a sense of purpose and meaning, emphasizing the power of faith and the idea that the true nature of creation may lie beyond human comprehension. The dialogue between these two realms, science and faith, continues to evolve. For some, these perspectives are seen as complementary, each offering unique insights into the question of the universe's origins. For others, the gap between scientific explanations and spiritual beliefs remains a point of contention, with some arguing that these realms should remain distinct to avoid misunderstandings. In the end, the question of the universe's origins, how something can emerge from nothing, is a story that continues to unfold, driven by the combined efforts of scientists, philosophers, and spiritual thinkers alike. As our understanding deepens, so too does our sense of awe and wonder at the vastness and complexity of the universe, a universe that continues to elude our full comprehension, no matter how far we may seek. The vastness of the cosmos has long inspired humans to look up at the night sky, not only to marvel at its breathtaking beauty, but also to contemplate the profound mysteries it holds. These mysteries, particularly regarding the origins of the universe, have sparked endless debates and discussions across multiple disciplines: science, philosophy, theology, and art. At the heart of these conversations lies an essential question: how did everything come to be? Science offers a way to explain the how of the universe's origins, pointing to theories like the Big Bang, a colossal explosion from an infinitely dense point that began the expansion of the universe some 13.8 billion years ago. It provides a narrative rooted in empirical evidence and observation, helping us trace the universe's history from its very first moments. But while science might tell us how the universe came into being, the question of why remains a matter largely untouched by scientific inquiry. This is where faith and philosophy step in, seeking to address the existential meaning behind our existence, offering interpretations that might never be measurable or observable. These ongoing debates, where science and faith often stand on opposing sides, do more than just challenge our understanding of the universe. They push us to re-examine our place in existence, encouraging a deeper exploration of not just how we got here, but why we are here. The merging of scientific exploration with philosophical reflection opens the door to a more holistic approach to understanding. By respecting and engaging with different perspectives on the origins of the universe, we begin to close the gap between knowledge and belief, forging a shared journey that spans centuries of human thought and inquiry. Exploring the origins of the universe does more than just satisfy academic curiosity. It touches our daily lives in profound ways. At its core, learning about the universe's beginnings offers a connection to something far larger than ourselves. We are reminded that we are not solitary beings, isolated in our individual experiences, but part of an expansive cosmic narrative that stretches back to the earliest moments of time. The very atoms that make up our bodies were formed in stars, their explosive deaths scattering elements that eventually coalesced into planets, life, and eventually human beings. This realization fosters a deep sense of curiosity not only about the cosmos, but also about the world around us and our place within it. This curiosity becomes a powerful motivator in our own lives, urging us to seek knowledge, ask questions, and pursue understanding. It sparks a desire for lifelong learning, prompting us to look beyond the surface of things and into the deeper mechanisms that shape the world. It also creates an opportunity for conversations that bridge the gap between scientific inquiry and philosophical reflection. These discussions, often sparked by our exploration of the cosmos, can lead to new insights and offer perspectives that enrich our lives and communities. On a practical level, the methods developed by scientists to study the universe, observation, experimentation, and critical thinking, can be applied to all aspects of life. These approaches, which focus on careful analysis and evidence-based reasoning, can enhance our problem-solving abilities in personal and professional contexts. They teach us to view challenges through a lens of inquiry, whether we are grappling with a scientific question or navigating the complexities of daily life. This analytical mindset becomes a tool that empowers individuals to approach problems with a more thoughtful and systematic approach. Moreover, understanding the origins of the universe encourages a sense of interconnectedness, reminding us that all human beings share a common cosmic heritage. The very elements that form our bodies and our world were forged in the hearts of ancient stars, a reminder that we are part of a vast, interconnected web of existence. This realization fosters compassion, empathy, and a deep appreciation for the interdependence of life. As we come to see ourselves as a thread woven into the grand tapestry of the universe, we are more inclined to treat one another with kindness and to care for the planet that sustains us. This sense of responsibility is crucial as we recognize that our actions today shape the future for generations to come. The exploration of the universe's origins offers not just answers to scientific questions, but also invites us to reflect on our own existence. It ignites curiosity, promotes critical thinking, and deepens our understanding of our place in the cosmos. This exploration encourages us to contemplate our purpose in the universe. Are we mere observers, or do we have a role to play in the unfolding of the cosmic story? As we delve into these profound questions, we challenge ourselves to reconsider our responsibilities toward each other and the world we inhabit. The concept of nothing is central to many discussions about the origins of the universe. Before the Big Bang, there was a state of absolute nothingness, a void devoid of matter, energy, and even the fabric of space-time itself. This idea, though rooted in scientific theory, also evokes powerful philosophical and theological questions. What does it mean for something to emerge from nothing? Does this challenge our very understanding of existence? These questions invite both scientific inquiry and spiritual reflection, leading to a deep exploration of the nature of reality and the limits of human knowledge. As scientists uncover more about the universe's beginnings, cultures across the world may begin to revisit their own creation stories. Many religions have long held narratives about how the universe came to be, each one offering its own interpretation of creation. New scientific insights into the origins of the cosmos can spark conversations about reconciling ancient beliefs with modern understandings of cosmology. These dialogues can serve to bridge divides between different belief systems, as people of all faiths come together to explore the fundamental mysteries of existence. At their core, these discussions are united by one shared curiosity: the desire to understand our place in the universe. As these ideas permeate society, they can have a profound impact on future generations. Learning about the origins of the universe can spark a sense of wonder and inspiration in young minds, motivating them to pursue careers in science, technology, and exploration. This collective pursuit of knowledge strengthens society's commitment to discovery, fostering a culture that values intellectual curiosity and the search for truth. Furthermore, as we contemplate the implications of the universe's origins, we inevitably confront ethical questions about our place in the grand scheme of things. Are we merely passive observers of the universe's unfolding story, or do we have an active role to play in shaping its future? These existential questions compel us to reconsider our responsibilities, both to each other and to the planet. What does it mean to live in a universe that evolved from nothing? And how does this knowledge affect how we view our existence? In addition to science and philosophy, the concept of the universe's origins has been explored in the realm of art and literature, particularly through poetry. Historically, poets have often turned to the natural world to express profound questions about existence and the cosmos. Many early poets wrote about celestial bodies like stars, the moon, and the vastness of the night sky, using these symbols to reflect on the human condition. The stars, for example, became metaphors for life's fleeting nature, representing both awe and insignificance as people gazed upward, searching for meaning amidst the infinite expanse. As time progressed, poets began to engage more directly with the concept of nothingness, grappling with the fear and wonder that arise from contemplating a void beyond comprehension. Some saw nothingness as a source of existential dread, while others viewed it as a canvas for creation, where from the emptiness all things could emerge. This duality of hope and despair resonated deeply with the human experience, capturing the tension between the desire for meaning and the terrifying unknown that lies just beyond our understanding. In modern poetry, these themes have become intertwined with scientific discoveries about the universe. Poets now draw upon concepts from physics and cosmology, referencing the Big Bang, black holes, and the mysterious nature of space-time to explore the limitations of human understanding. Yet, despite the complexity of these ideas, poetry continues to capture the emotional essence of existence, conveying not only the vastness of the universe, but also the profound, often humbling, impact that knowledge has on our sense of self. Poetry thus serves as a bridge between the cold, logical facts of science and the warm, emotional responses we have to those facts. Where science provides the explanations, poetry captures the feelings that accompany those discoveries, feelings of awe, wonder, and even existential anxiety. Together, science and poetry offer complementary views of the universe, one grounded in reason, the other in emotion. Through this fusion of logic and feeling, we gain a deeper, more holistic understanding of the cosmos and our place within it. Poetry often carries the profound ability to convey complex concepts in a way that resonates deeply with our emotions and imaginations. Through the use of metaphor and vivid imagery, it takes abstract or technical ideas and transforms them into relatable, tangible experiences. Take, for instance, the Big Bang, a moment of cosmic birth so vast that it might be difficult for many to comprehend simply through equations or scientific jargon. A poem, on the other hand, could transform that very same idea into the image of a seed bursting open, sending out tendrils of life into the vast unknown. This image, while simple, immediately brings to mind the explosive energy of creation, the idea that one moment gave birth to all that we know, from the stars in the sky to the thoughts in our minds. In this way, poetry bridges the gap between science and the human experience, inviting a much broader audience to engage with complex scientific ideas. It opens the door to a more accessible and memorable understanding of topics that might otherwise remain distant or abstract. Beyond accessibility, poetry's unique ability to evoke emotions can also spark curiosity and inspire deeper questions about the nature of the universe. By seeing the cosmos through a poetic lens, individuals might be motivated to explore scientific mysteries with a fresh perspective, one that might not be immediately obvious through the lens of mathematics or data alone. This fusion of poetry and science invites us to look beyond the how of the universe and ponder the why. Not only does it deepen our understanding of the cosmos, but it also helps us appreciate the profound emotions tied to our existence within it. When we embrace both perspectives, logical and emotional, we honor the human quest for knowledge while acknowledging the feelings that stir within us when we contemplate the vastness of the universe and our place within it. It is through this balanced approach that we can gain a richer, fuller understanding of the universe itself. The foundations of modern cosmology, as we know it today, were built on the shoulders of great minds whose insights spanned centuries. One of the earliest contributions came from the Greek philosopher Aristotle, who developed a geocentric model of the universe, placing Earth at its very center. Although Aristotle's vision was ultimately proven to be incorrect, his ideas dominated scientific thought for nearly 2,000 years. But as history progressed, so too did humanity's understanding of the cosmos. Fast forward to the 16th century, and we encounter the groundbreaking work of Nicolaus Copernicus. With his heliocentric model, Copernicus dared to place the sun, not the Earth, at the center of the solar system. This seemingly radical idea did more than shift the perspective of astronomy. It set the stage for a wave of new discoveries, sparking curiosity and inquiry that would propel science forward. Johannes Kepler, a century later, would expand upon Copernicus's ideas with his laws of planetary motion, describing the elliptical orbits of planets around the sun. This provided a more precise framework for understanding celestial mechanics, laying crucial groundwork for future scientific breakthroughs. Isaac Newton, in the 17th century, then took this work a step further by formulating the law of universal gravitation. Newton demonstrated that the same force which causes an apple to fall to the ground also governs the motion of planets, moons, and even entire galaxies. His law of gravitation would become the bedrock of classical mechanics, a framework that remained largely unchallenged until the 20th century. Enter Albert Einstein, whose theory of general relativity revolutionized our understanding of gravity itself. Unlike Newton's theory, which treated gravity as a force between objects, Einstein proposed that gravity is a result of the curvature of space-time caused by the mass of an object. His work would forever change how we view the universe, predicting phenomena such as black holes and the expanding universe, ideas that have since been confirmed through observations. In the 20th century, astronomer Edwin Hubble made a discovery that would fundamentally reshape cosmology once again. By observing the redshift of light from distant galaxies, Hubble determined that these galaxies were moving away from us, suggesting that the universe itself was expanding. This observation provided the first evidence that the universe had a beginning, fueling the formulation of the Big Bang theory. These figures, Aristotle, Copernicus, Kepler, Newton, Einstein, and Hubble, each contributed critical insights, gradually assembling the cosmic puzzle into a framework that we continue to build upon today. The notion that the universe might have emerged from nothing is a concept that has intrigued philosophers and scientists alike for centuries. In the earliest days of human thought, cosmology was purely speculative. Without the benefit of modern tools or advanced knowledge, early thinkers pondered the nature of existence, contemplating what might have existed before the universe we know came into being. In the early 20th century, however, a breakthrough moment occurred. Edwin Hubble's observations of the expanding universe provided compelling evidence that the universe had a distinct beginning, a moment in time when space itself began to stretch outward. This led to the development of the Big Bang model, which proposes that the universe began as an extremely hot and dense point, a singularity, before expanding outward to form the cosmos we observe today. The concept of nothing in this context is not a simple void, but rather a state devoid of conventional matter and energy. Instead, it may be filled with quantum fields and fluctuating virtual particles, giving rise to a universe that defies our everyday understanding. Through the lens of quantum mechanics, particles can appear and disappear spontaneously from a vacuum, suggesting that even nothing is brimming with potential. Building on these ideas, physicists such as Stephen Hawking propose that even time itself may have a limit, meaning that questions about what came before the Big Bang might be meaningless within the context of modern physics. In this framework, the universe's origins could arise not from a traditional cause and effect, but from a quantum state that exists in a kind of superposition of possibilities. This paradigm challenges our deepest intuitions about time, causality, and existence itself. As we continue to probe these ideas, our understanding of the universe's origin evolves. Researchers today are focusing on several key areas to deepen their knowledge. One of the most promising avenues is the study of cosmic background radiation. This faint glow left over from the Big Bang serves as a snapshot of the universe as it was just moments after its creation. By enhancing our ability to measure tiny fluctuations in temperature and intensity, scientists hope to uncover new insights into the formation of the first stars and galaxies. Another central focus is dark matter and dark energy, mysterious entities that together make up around 95% of the universe. Though invisible and enigmatic, they are believed to play a critical role in the structure and expansion of the cosmos. New experiments are being developed to measure how these elusive forces interact with regular matter, which could shed light on their properties and how they shape the universe's evolution. Advanced telescopes and satellites are also set to play a crucial role in these efforts. Equipped with the latest technologies, they offer unprecedented views into distant galaxies, providing us with invaluable data about their composition, evolution, and interaction with other cosmic structures. This wealth of data promises to open new doors in our understanding of the universe's past. In the field of theoretical physics, researchers are working to merge quantum mechanics and general relativity into a unified theory. This theory of everything could offer a new understanding of the universe's earliest moments, when both quantum effects and gravitational forces were at play. These efforts could lead to transformative discoveries that challenge our current models and offer a deeper understanding of the origins of everything. Emerging technologies in space exploration are poised to push the boundaries of our knowledge even further. With advanced spacecraft and observational instruments, we can peer deeper into space than ever before, studying ancient light that has traveled across billions of light years. Gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, also offer a new frontier for exploration, providing a way to observe phenomena like black hole mergers that occurred in the infancy of the universe. Through these revolutionary techniques, we stand on the precipice of groundbreaking discoveries that promise to expand our understanding of the cosmos and the profound questions that have occupied humanity for millennia. The quest for knowledge continues, fueled by the unyielding curiosity that has driven us to ask, where did the universe come from, and how did everything begin? With each discovery, we inch closer to answers, while also uncovering more mysteries that will inspire future generations of explorers to look up at the stars and ask, what's next? Advancements in artificial intelligence, AI, are transforming how we understand the cosmos, providing us with unprecedented tools to analyze the immense volumes of data pouring in from telescopes and space missions. These sophisticated algorithms allow scientists to uncover patterns and anomalies in the cosmic data that would have once been imperceptible to the human eye. As a result, we are discovering new insights into the universe's formation and evolution, challenging long-held assumptions and opening up possibilities for new theories. Through these AI-driven analyses, scientists are not merely cataloging information, but are reinterpreting the very story of our universe. With each mission to distant moons like Europa or planets such as Mars, we gain new pieces to the puzzle of life's origins, not just on Earth, but across the cosmos. Discovering organic substances or finding conditions that might support life on these worlds could dramatically alter our understanding of the likelihood that life exists beyond our home planet. As we push the boundaries of exploration, we shift from a static understanding of the universe to a dynamic, evolving narrative that continues to reshape the way we perceive our existence. With every leap in technological advancement, we are rethinking our place in the cosmos. Each discovery builds upon the one before it, leading us deeper into a story that no longer seems like a distant mystery, but a living, breathing narrative that continues to evolve. As we learn more, we begin to see a clearer picture of the universe's birth and its gradual development, unlocking mysteries that have confounded humanity for generations. The question of the universe's origin, emerging from what we often call nothing, is one of the most profound enigmas in science. At its core, the universe didn't emerge from a void, an emptiness devoid of anything. Instead, it began from a singular point, a state where all the potential for everything that exists now was contained. It is akin to a seed that holds the possibility of growing into a towering tree. Though the seed itself might seem insignificant at first, inside it lies a vast potential. In many ways, this mirrors the beginning of human consciousness, suggesting that the universe's creation and the emergence of consciousness share common threads of untapped potential waiting to unfold. This comparison draws a fascinating parallel between the universe and the human mind. Just as the universe began from an infinitesimal point of infinite possibility, so too might human consciousness emerge from a fundamental awareness or essence that exists within all of us. This suggests that consciousness, like the universe, could have a shared source of potentiality, a primordial awareness waiting to emerge and express itself. Over time, as the universe expanded and evolved, it became increasingly complex, forming galaxies, stars, and eventually life itself. Similarly, the human mind grows and evolves through experience, weaving together thoughts, emotions, and awareness into the intricate tapestry of our consciousness. Some theories even suggest that consciousness could be a fundamental property of the universe, much like gravity or electromagnetism. This would mean that consciousness is not merely a product of the brain, but rather an inherent thread that connects all living things. While these ideas remain speculative, they provoke deep questions about the nature of reality and existence, prompting scientists and philosophers alike to explore the very fabric of our being. Could consciousness, in its essence, be as universal as the laws of physics themselves? The development of the universe and human consciousness share a deeply intertwined journey, both starting from a singularity. In the case of the universe, this moment occurred at the Big Bang, when all the matter and energy of the cosmos were concentrated in a hot, dense point. For human consciousness, the journey begins with primitive instincts and neural processes, laying the foundation for higher thought. As the universe expanded, it evolved from chaotic clouds of gas into the complex structures we observe today: stars, galaxies, and planets. Likewise, human consciousness began with simple reflexes, gradually growing into a complex web of thoughts, emotions, and self-awareness. As the universe gave rise to diverse forms of life across a variety of environments, human consciousness opened new pathways for creativity, culture, and complex social systems. The mind, much like the cosmos, became an interconnected system where each thought, emotion, and experience influenced the other, shaping our understanding of the world around us. This interconnectedness mirrors the way galaxies and stars form intricate webs of gravitational relationships, with each object exerting an influence on others. Both the universe and human consciousness evolved toward balance and harmony. Over billions of years, the cosmos found its equilibrium through the formation of stars and the cooling of space. Similarly, as individuals mature, they strive for a balance between their emotions, experiences, and rational thought, seeking harmony in both their inner and outer worlds. This shared drive for equilibrium reflects a deeper order, where the chaos of the initial moments eventually gives way to stability and understanding. Curiosity, too, is a driving force behind both cosmic evolution and human growth. The universe continues to evolve, constantly changing and expanding, while human consciousness seeks knowledge, understanding, and meaning. This innate drive to explore, to question, and to understand is a fundamental part of both our cosmic journey and our personal development. It underscores the interconnectedness of all things, highlighting how the origins of existence and consciousness are deeply entwined within the vast fabric of reality. However, as we continue to explore the universe's beginnings, we are confronted with a host of ethical questions that shape the course of our scientific journey. The deeper we delve into the mysteries of the cosmos, the more we are challenged by the impact these discoveries might have on our worldview. As scientists uncover the origins of the universe, they may reveal that challenge our beliefs about existence, creation, and our place within the grand tapestry of life. These revelations can provoke tensions between scientific understanding and cultural or religious perspectives, raising questions about the need for respect and sensitivity towards diverse beliefs. The ethical dilemmas also extend to the technologies we use in our exploration. Advanced instruments, such as telescopes and space probes, rely on significant resources and energy. This brings up important questions about the environmental impact of these technologies and whether the pursuit of knowledge justifies the harm they might cause to our planet. Moreover, the high costs associated with scientific research often limit participation to wealthy nations and institutions. This creates concerns about access and equity, prompting us to consider whose knowledge is valued and how it will be shared across global communities. In the realm of space exploration, these ethical questions become even more pronounced. As we venture into the cosmos, the potential for encountering new environments and possibly even extraterrestrial life brings up complex moral questions. If we discover life on other planets or moons, what are our responsibilities toward these environments? Should we explore and colonize these worlds, or should we focus on stewardship and preservation? These questions emphasize the need for a respectful, cautious approach to the exploration of other celestial bodies. Finally, as our scientific discoveries continue to unfold, they may provoke existential anxieties. If our explorations reveal the fragility or insignificance of humanity within the vast expanse of the universe, how might this impact our collective psyche? Balancing the pursuit of knowledge with the broader consequences of that knowledge requires careful thought and ethical consideration. We must ask ourselves not only what we are learning, but also what the implications of that knowledge will mean for our future, both on Earth and in the wider cosmos. As scientists push forward in their quest to understand the origins of the universe and consciousness, they are not only exploring the cosmos, they are navigating a landscape filled with profound ethical questions. The pursuit of knowledge is an ever-evolving journey, one that challenges us to rethink our place in the universe and consider the impact of our discoveries on both the environment and society. It is a journey that continues to captivate the minds of researchers, philosophers, and dreamers alike, as we strive to understand the very essence of existence. Moreover, the societal implications of groundbreaking discoveries concerning the origins of existence could significantly challenge or conversely confirm long-held beliefs across a variety of cultures and religions. These revelations pose profound questions that touch the very core of human understanding, often putting scientists in the delicate position of having to navigate complex discussions that respect diverse viewpoints while simultaneously sharing their findings. In such a context, open communication with the public becomes not merely a necessity, but an essential tool for fostering understanding. It also serves to mitigate the fear and misinformation that can arise when new transformative ideas are presented. Furthermore, the issue of funding remains a pivotal concern in these scientific explorations. The sources of financial support not only influence the trajectory of research, but also raise important ethical questions regarding the nature of that funding. Scientists are often faced with the responsibility of ensuring that their work serves the greater good of humanity, rather than advancing narrow, vested interests. The tension between the pursuit of knowledge and the influence of financial backers is a balancing act that researchers must continuously confront, and it is in this space that ethical considerations are most keenly felt. Ultimately, as scientists continue to probe the monumental questions surrounding the origins of existence, these ethical dilemmas remain an ongoing part of the discourse. The goal is clear: to promote a pursuit of knowledge that not only expands our understanding of the universe, but also enriches and respects our shared human experience. This delicate balance is crucial to responsible scientific inquiry and has the potential to unlock some of the deepest mysteries of our existence. To unravel the secrets of the early universe, scientists rely heavily on promising technological advancements that allow them to peer further back into the cosmic past than ever before. One of the most significant of these innovations is the development of powerful telescopes designed specifically to observe distant galaxies and stars. These telescopes, equipped with cutting-edge optics and sensors, capture light that has traveled across the vast expanse of space for billions of years. This light, once captured, provides a crucial window into the formation of the universe shortly after the Big Bang. By observing the faintest traces of light from the distant past, scientists can uncover information about how the universe took shape in its earliest moments, allowing them to piece together a clearer picture of its origins. In parallel, the field of particle physics has seen significant strides, particularly in the realm of particle colliders. These massive machines accelerate particles to nearly the speed of light and smash them together, creating conditions similar to those that existed just after the universe began. By studying the reactions and new particles formed in these high-energy collisions, scientists can gain unprecedented insights into the fundamental building blocks of matter and the forces that govern the universe's early development. This research not only provides clues about the nature of matter itself, but also sheds light on the forces that shaped the cosmos during its formative years. Space exploration, too, plays an indispensable role in our quest to understand the universe's origins. Missions aimed at studying exoplanets and other cosmic phenomena help expand our understanding of conditions that might resemble those of the early universe. For example, studying the atmospheres of distant planets provides valuable data that can reveal details about their origins, potentially mirroring processes that occurred in the infancy of the universe. Alongside these efforts, the development of advanced computer simulations has become a vital tool for researchers. These simulations allow scientists to model complex cosmic events, such as the rapid expansion or inflation of the universe, enabling them to visualize phenomena that are otherwise invisible to the naked eye. The accuracy of these simulations has improved dramatically over time, significantly enhancing our comprehension of the early cosmic history. Gravitational wave detectors, another cutting-edge innovation, have opened an entirely new realm of exploration. These detectors are sensitive to ripples in space-time, caused by massive events like the merging of black holes. By observing these waves, scientists can learn about the extreme conditions that existed in the universe's early days, conditions that traditional light-based methods cannot detect. These waves offer a new lens through which to view some of the most violent and mysterious events that have shaped the universe, contributing crucial data to our understanding of its evolution. Together, these technological advancements form an indispensable toolkit that allows scientists to delve deeper into the origins, structure, and evolution of the universe. Each leap forward brings us closer to answering some of humanity's most profound questions, allowing us to better understand the cosmos and our place within it. As these innovations continue to unfold, the impact on cosmological research is undeniable, enhancing our ability to make discoveries that reshape our comprehension of the universe. The ripple effect of technological advancements in other fields has been equally transformative for cosmology. Innovations in imaging technology, for example, have provided astronomers with new tools to capture clearer, more detailed images of celestial bodies. These high-resolution cameras offer unprecedented precision, allowing scientists to analyze galaxies, stars, and planets with a level of detail that was previously unimaginable. This enhanced imaging capability not only improves our understanding of these celestial objects, but also sheds light on their formation and behavior, providing key insights into the universe's broader structure. The rise of data analysis techniques from computer science, particularly the use of machine learning, has also revolutionized the way astronomers process and interpret vast amounts of data. Algorithms designed to detect patterns or anomalies in massive data sets enable researchers to sift through thousands of images and measurements far more efficiently than ever before. This leads to faster discoveries, often uncovering phenomena that were once thought to be too complex or subtle to detect. The combination of high-tech imaging and sophisticated data analysis has thus greatly accelerated our ability to unlock the universe's secrets. Material science has also made significant contributions, particularly in the development of lightweight yet durable materials that have enabled the construction of advanced telescopes and spacecraft. These materials allow instruments to endure the extreme conditions of space, enabling more ambitious missions to explore far-flung regions of the cosmos. The resulting data from these missions provides invaluable insights into regions of space that were previously unreachable, further expanding our knowledge of the universe. Even fields like biology and medicine have a role to play. The study of extremophiles, organisms that thrive in Earth's harshest environments, has provided valuable clues about the potential for life on other planets. Understanding how these organisms survive in conditions that would be inhospitable to most life forms informs the search for extraterrestrial life. By examining how life adapts to extreme environments on Earth, astrobiologists can better target their searches for life in similarly harsh locales elsewhere in the universe. As these diverse fields of study continue to evolve, they create a dynamic, interconnected landscape that fosters new perspectives and opens doors to new possibilities. The convergence of technologies and ideas across disciplines drives forward the scientific endeavor, pushing the boundaries of human knowledge and reshaping our understanding of the universe in ways that were once thought impossible. The concept of the universe's creation from nothing has captivated the human imagination for millennia, inspiring countless works of art, philosophy, and religion. In many religious traditions, the idea of creation from a void is central to the narrative of the cosmos's origins. In the Bible, for instance, the book of Genesis begins with the declaration that the universe was brought into existence through a singular divine command. This story illustrates the transition from nothingness to being, highlighting the transformative power of creation itself. In literature, the theme of creation has appeared in a variety of forms, often blending science fiction with philosophical reflection. One such example is the iconic novel The Hitchhiker's Guide to the Galaxy by Douglas Adams. The book humorously explores the idea of the universe as a cosmic accident, where the emergence of life and the progression of existence unfold in ways that are as unpredictable as they are absurd. Through a mix of satire and absurdity, Adams offers a playful yet thought-provoking take on the randomness of creation and the evolution of life in a universe that seems to have come into being by pure chance. In cinema, the visual representation of creation is most famously explored in Stanley Kubrick's 2001 A Space Odyssey. This film vividly portrays the dawn of humanity and the mysterious evolution of life, all set against the backdrop of the vastness of space. Through stunning visuals and enigmatic storytelling, the film captures the profound mystery of existence, offering an interpretation of how life might emerge from primal chaos and evolve into the intelligent beings we are today. Through these various lenses, scientific, artistic, and philosophical, the question of the universe's origin from nothing continues to captivate, challenge, and inspire. Each discovery, each new technological breakthrough, and each cultural reflection adds layers of depth to our ongoing exploration of existence, offering new ways to understand the cosmos and our place within it. In the world of visual arts, works like The Creation of Adam by Michelangelo serve as timeless representations of divine creation, capturing one of the most pivotal moments in human history. This iconic fresco, painted on the ceiling of the Sistine Chapel, is not merely an artistic masterpiece, but a profound exploration of the relationship between the creator and the created. It invites viewers into a symbolic interpretation of the divine, where the touch of God's finger, almost within reach of atoms, seems to represent the spark of life, creation, and connection between humanity and the divine. The beauty and intricacy of Michelangelo's work elevate this moment into an eternal reflection on existence and our place within the cosmos. This concept of creation is not confined to the realms of art, however. It resonates powerfully within contemporary scientific discussions and documentaries, where filmmakers and writers tackle the origins of the universe. One of the most influential narratives within modern cosmology is the Big Bang Theory, which suggests that the universe emerged from a singular point of unimaginable density and temperature. Just like in The Creation of Adam, this theory captures a moment of transformation, only on a cosmic scale, as it explains the birth of the universe from an initial singularity, followed by rapid expansion. Filmmakers use dynamic visuals, clear narratives, and advanced animation techniques to bring this abstract idea to life, helping the public grasp the unfolding of the universe. The Big Bang, much like the divine touch in Michelangelo's painting, symbolizes an essential act of creation, albeit on a vastly different scale. These diverse cultural works, spanning from classical art to modern science, reflect humanity's ongoing fascination with the origins of the universe. Through every interpretation, we see an expression of our quest for meaning and understanding, a search for the answers to the most profound questions of our existence. Each new interpretation, whether through art or science, brings its own flavor, guiding audiences to reflect on the mysteries of the universe. This ongoing dialogue, through paintings, documentaries, and scientific discussions, continuously evolves, encouraging us to ponder not just where we come from, but what our place is in the vastness of everything. Popular media plays an immense role in shaping the way the public engages with cosmological theories. Films, television shows, books, and documentaries have brought ideas like the Big Bang, black holes, and the very nature of the universe into the mainstream. Concepts that once belonged solely to scientists have now entered the conversations of everyday people. Works like the film Interstellar and the television series Cosmos not only captivate with stunning visuals, but also introduce concepts such as time dilation, the vastness of space, and the mysterious nature of black holes. These productions don't just entertain, they ignite curiosity, providing a gateway for people to explore the science behind them. Even though they often take creative liberties, these works spark the imagination of the audience and encourage exploration. Moreover, the digital age has revolutionized how knowledge is disseminated. Social media platforms provide an immediate and vast network for information to be shared, clarifying misconceptions and spreading the latest research in cosmology. Public figures, scientists, and educators use these channels to correct misunderstandings and make complex ideas more accessible. In an instant, a tweet or a shared video can spread cutting-edge knowledge far and wide, making previously difficult topics much easier to comprehend. Yet there's a flip side. The same platforms can sometimes fuel the spread of misinformation when scientific ideas are misrepresented or oversimplified. Despite this, the power of social media in shaping public understanding cannot be underestimated. It has transformed science from an elite, specialized field into a shared human endeavor, inviting everyone to join in the quest for understanding. The role of popular media, however, goes beyond entertainment. It has evolved into an educational tool, bridging the gap between complex cosmological theories and the public's understanding. It serves not only to fascinate, but also to educate, making the vast and intricate workings of the universe more accessible. This blend of inspiration and education cultivates a deeper appreciation for the complexities of cosmology and for our place in the universe. One of the greatest challenges in communicating complex cosmological ideas lies in relating these grand concepts to everyday experiences. Many of the most profound scientific ideas can feel distant and difficult to grasp, but by using simple comparisons or analogies, these concepts can become much more tangible. For instance, to explain the vastness of space, one can compare the universe to a balloon. Each dot on the surface represents a galaxy, and as the balloon inflates, the dots, the galaxies, move farther apart. This visual helps illustrate how galaxies are racing away from each other as space itself expands. Another analogy to explain black holes is to describe them as a funnel, pulling everything around them inward with their intense gravitational force. Such simple, relatable images help make the abstract more understandable, even for those without a background in physics. Storytelling also plays an essential role in this process. The narratives of scientists and astronomers, their journeys of discovery, and the triumphs and setbacks they face are compelling and engaging. When these stories are shared in an accessible way, they not only inform, but also emotionally connect audiences to the subject matter. It humanizes the pursuit of knowledge, making it feel like a shared adventure. Simple, clear language is crucial in this process. Complex jargon and technical terms can alienate the general public, but when explained in everyday terms, difficult ideas become much more relatable. For example, instead of discussing gravitational waves, we can talk about ripples in space caused by massive objects moving, which conveys the same idea in a way that's easier to understand. Encouraging curiosity is also vital. When people are encouraged to ask questions and explore concepts, they become active participants in their learning. The more they can relate to the topic, whether through visual aids, engaging stories, or interactive discussions, the more likely they are to understand and retain these complex ideas. In this way, education about the cosmos becomes not just about imparting knowledge, but about sparking wonder and curiosity. One common misconception that arises in popular discussions of cosmology is the idea that the universe emerged from nothing. This misconception can stem from oversimplifications in media and casual conversations. To effectively address this, science communicators must first clarify what nothing actually means in this context. In traditional terms, nothing implies the absence of matter, energy, and even space. However, in the realm of quantum mechanics, nothing is far more complicated. Modern physics suggests that even in empty space, energy fluctuations can occur, leading to the creation of particles. These fluctuations could have been the seed that sparked the rapid expansion associated with the Big Bang. However, it's important to note that this does not mean the universe came from absolute nothingness. A useful analogy to clarify this is to compare it to a calm body of water. Imagine that the surface of the water is perfectly still, but suddenly small ripples begin to form, even though there is no visible cause. These ripples, though small and fleeting, can grow and spread, much like the fluctuations that might have triggered the Big Bang. This analogy helps make the concept of nothing more understandable, while dispelling the myth of the universe emerging from absolute void. Furthermore, it's crucial to emphasize that the universe did not simply appear out of thin air. Scientific theories propose that it originated from a singular point, an initial state of extreme density and temperature, and over time, this point expanded rapidly, setting the foundation for everything that followed. By explaining these concepts in clear and engaging ways, science communicators can help the public appreciate the depth and complexity of the universe's origins. Equally important is distinguishing between scientific theories and the popular interpretations of them. Theories like the Big Bang and quantum fluctuations often get oversimplified or misrepresented in media, leading to misconceptions. By using clear language and relatable examples, science communicators can help people understand the difference between the inspiring, often complex truths of the cosmos and the myths that arise from misinterpretations. This clarity is essential for creating a more accurate and informed understanding of the universe's beginnings. Theories about alternate realities and the origins of multiple universes have also emerged from the fields of quantum physics and cosmology. These speculative ideas often suggest that from a state of nothing, tiny fluctuations in quantum fields could create bubbles of energy that rapidly expand, each potentially giving rise to new universes. These universes, each with its own set of laws of physics, could form distinct realities, independent from one another but interconnected at a quantum level. One such concept, the multiverse theory, suggests that our universe is just one bubble in a larger cosmic foam, where each universe evolves separately but might share a common origin. In these alternate realities, the very laws that govern matter and energy could differ, allowing for entirely different forms of existence. Some theorists even wonder if these universes might interact with one another, possibly through quantum entanglement or other unknown mechanisms. These ideas, though speculative, open up exciting possibilities about the nature of reality itself and our understanding of the cosmos. Each new theory, each new discovery only deepens the mystery and wonder of the universe, inviting us to explore the infinite complexities of existence. The concept of alternate realities challenges our understanding of the universe in profound ways, urging us to rethink our very perception of time and existence. In an endless sea of infinite possibilities, decisions and events could unfold in an array of unique configurations, each creating a new branch of reality. Every choice we make could give rise to a different universe, leading to a complex web of interconnected, coexisting realms. This idea suggests that our universe, with all its vastness and intricacy, is not an isolated entity, but rather a singular expression in an ever-expanding cosmic tapestry. Each reality might be a reflection of the infinite decisions we make, echoing across parallel worlds where alternate versions of ourselves live out divergent paths. In a way, the dream of nothingness, the idea of an empty, static void, transforms into a boundless expanse of infinite possibilities. Every moment of choice, every event, spins off new timelines, new branches of existence, blurring the line between creation, choice, and being itself. The notion of alternate realities, also known as parallel universes, forces us to confront the limits of our understanding about the universe's origin. When we consider our own universe, we often picture it as one singular, vast space, a single canvas on which the story of existence unfolds. But what if there are countless other universes, each one existing in parallel to ours, each governed by its own set of laws and principles? This concept shifts our perspective from a singular universe to a grand, multidimensional cosmos, a collection of worlds, each with its own narrative, its own set of possibilities. Picture the universe not as a solitary entity, but as a massive book, where each universe represents a different page. Each page tells its own tale, with unique characters, events, and laws. This shift in perspective allows us to reconsider the very structure of our own reality. If other universes exist alongside ours, then perhaps our own universe, with its specific conditions that allow for life, is merely one possibility among countless others. The presence of these alternate realities opens up fascinating questions about the nature of cause and effect. Could every decision we make create a branching pathway, an alternate version of ourselves, in a different universe? For instance, consider the monumental event of the Big Bang. The theory that all matter and energy in our universe began as a singular, highly condensed point before rapidly expanding suggests a singular origin. However, if alternate realities exist, this event could have unfolded in numerous different ways, creating various outcomes in different universes. Each one could reflect a unique set of circumstances, outcomes, and conditions, leading to realities both similar to and vastly different from our own. This exploration of parallel universes challenges the boundaries of science and thought, pushing scientists and philosophers to extend the limits of their imagination. It prompts deep inquiry into the nature of existence itself, What does it mean to exist in a universe that could have infinite variations? If alternate realities do exist, they force us to re-examine fundamental questions about time, space, and even the essence of life. Could it be that our understanding of the cosmos is limited by our perception of what is observable? The very notion of parallel universes stretches our comprehension of the universe's structure and its origins, suggesting that what we know may only be a fraction of a much larger cosmic narrative. The idea of parallel universes invites a deeper conversation about scientific literacy. As our understanding of cosmology advances, it becomes essential for the public to engage with these ideas in meaningful ways. When people grasp fundamental scientific concepts, they can better appreciate the wonders of the universe, from the expansion of space to the mysteries of dark matter. A scientifically literate public is not only better equipped to understand complex phenomena, but also more likely to engage critically with the questions that shape our future. Questions about space exploration, the search for extraterrestrial life, and the implications of climate change. Understanding the cosmos is not just about gazing at distant stars, but about cultivating a culture of curiosity and inquiry. Educational institutions play a pivotal role in this process. Schools and universities provide the framework for exploring fundamental questions about existence, offering students and the public the tools to grapple with the complexities of the universe. These institutions serve as hubs of discovery, where the latest scientific findings are shared and discussed, helping individuals to better understand the origins of the universe, the life cycles of stars, and the formation of galaxies. Beyond the classroom, educational institutions foster collaboration and innovation, driving research programs that contribute to major discoveries in space exploration and astronomy. Through hands-on experience and participation in cutting-edge research, students and faculty members alike contribute to our growing understanding of the cosmos. They help develop new technologies, such as advanced telescopes, and play an integral role in the ongoing search for answers to some of the most profound questions humanity has ever asked. Moreover, these institutions extend their impact through public outreach programs which introduce younger generations to the wonders of the universe. Stargazing nights, planetarium shows, and science fairs all serve to inspire curiosity about the cosmos. By making astronomy engaging and accessible, these programs cultivate a new generation of scientists and informed citizens, individuals who understand the universe's ongoing evolution and their place within it. In this sense, educational institutions are not simply places of learning. They are beacons of knowledge, guiding individuals toward a deeper understanding of the complexities of the universe. They inspire a shared fascination with the cosmos, one that transcends the confines of the classroom and permeates every facet of society. This collective curiosity can lead to broader appreciation of our responsibilities as stewards of the Earth and participants in the larger cosmic narrative. Fictional narratives, too, have long been fascinated with the universe's origin. Writers often blend scientific theories with imaginative storytelling, weaving intricate plots about the birth of the cosmos. At the heart of many of these stories lies the Big Bang theory, which posits that the universe began from a singular point of immense density and energy before expanding rapidly. This explosive event serves as a rich backdrop for tales of creation, transformation, and cosmic evolution. In these stories, authors frequently draw inspiration from concepts like cosmic inflation, the rapid expansion of the universe immediately following the Big Bang. This idea is sometimes portrayed as the sudden appearance of new worlds, realms teeming with diverse life forms, each evolving along a different path. In these fictional realms, the laws of physics might operate in entirely different ways, leading to civilizations unlike anything we could imagine. These creative interpretations of the universe's origins not only spark the imagination, but also highlight the potential for infinite possibilities that might exist in alternate realities. Moreover, narratives within science fiction and speculative genres often introduce elements like dark matter and dark energy, two of the most mysterious and enigmatic forces that govern the universe. While scientists acknowledge the immense role these unseen components play in shaping the structure and expansion of the cosmos, popular fiction frequently amplifies their properties, bending them into fantastical elements. In doing so, it transforms them from abstract concepts into tangible forces that directly affect the lives of characters, immersing audiences in stories where these scientific unknowns become key drivers of drama. Through these explorations, science fiction not only highlights the power of these forces, but also shows how complex and often perplexing scientific questions about our existence can be translated into thrilling, engaging plots. In these stories, characters embark on journeys through time and space that are often shaped by the concept of the multiverse, a theory that proposes the existence of countless parallel universes, each with its own unique properties. Within these fictional worlds, this theory morphs into realms of alternate realities, where the characters' lives unfold differently based on the decisions they make, creating rich opportunities for adventure and philosophical exploration. These narrative universes are not just venues for action, but serve as a lens through which audiences can examine profound ideas about fate, free will, and the very nature of reality itself. Characters living different lives across parallel worlds prompt viewers and readers to question how small choices can alter the course of existence, urging us to reflect on our own lives and the paths we choose. By weaving together scientific concepts with imaginative storylines, speculative fiction constructs a bridge between the known and the unknown, fact and fantasy. It sparks curiosity about actual scientific theories, such as the true nature of dark matter, black holes, or the origin of the universe, while offering an engaging, often thought-provoking way to explore fundamental questions about existence and humanity's place within the vast expanse of the cosmos. These stories keep audiences captivated, urging them to continue pondering the universe's profound mysteries long after they've turned the last page or watched the final scene. In doing so, speculative fiction encourages an ongoing dialogue between the imagination and scientific inquiry, fostering a deeper understanding of both. At the heart of this genre is a fascination with the unknown, and speculative fiction provides a fascinating lens through which we can consider complex, often unanswerable questions about the universe. By stretching the imagination, it allows us to explore possibilities that transcend current scientific understanding, pushing the boundaries of what we think is possible. This genre frequently delves into themes such as the limits of human technology, the nature of existence, and the ethical dilemmas posed by space exploration. These themes challenge audiences to think critically about the direction humanity is heading and can help inform our understanding of cosmology, technology, and the moral responsibilities we face as we advance further into the unknown. One of the most significant lessons conveyed through speculative fiction is the importance of curiosity, the drive to explore, question, and understand the universe. Many works in this genre celebrate humanity's innate desire to push beyond known boundaries and seek out knowledge. This resonates deeply with the real-world pursuit of cosmic understanding, where scientists relentlessly strive to uncover the mysteries of black holes, dark matter, the birth of galaxies, and the nature of time itself. In this way, speculative fiction often mirrors the ongoing quest of real-world cosmologists and physicists to uncover the secrets of the universe, reinforcing the importance of intellectual curiosity and the spirit of exploration. Speculative fiction also emphasizes the interconnectedness of life in the universe. Many stories imagine distant civilizations on far-off planets, each bound by the same fundamental laws of nature. By exploring these imagined worlds, we are reminded of the vastness of the cosmos and the complex web of life that may extend far beyond our own Earth. These narratives urge us to think about how the laws of the universe might manifest in different environments and encourage a deeper appreciation for the extraordinary complexity of cosmological phenomena. In doing so, speculative fiction reveals that while we may view ourselves as distinct, we are also part of something far greater, interconnected with the cosmic order in ways we may never fully comprehend. In addition, speculative fiction often serves as a vehicle for examining potential futures, whether utopian or dystopian. These stories shed light on the choices we face today, particularly concerning the ethical use of technology, the environment, and our interactions with the cosmos. By envisioning the long-term consequences of our current actions, speculative fiction challenges us to consider the impact of our decisions on future generations. How will our technological advances, environmental policies, and interactions with space shape the world of tomorrow? These questions are at the core of many speculative narratives, urging us to think critically about the path we are forging and the future we are creating. Moreover, speculative fiction frequently tackles the ethical dilemmas associated with advanced technologies and space travel. As humanity stands on the brink of significant technological breakthroughs, whether in artificial intelligence, space exploration, or genetic engineering, these stories push us to reflect on the moral implications of our progress. What responsibilities do we hold when it comes to exploring the unknown? What ethical considerations must guide our decisions as we venture into uncharted territories, both on Earth and beyond? These questions, raised by speculative fiction, challenge us to think deeply about our role in the cosmos and the responsibilities that accompany our scientific and technological advancements. In comparing speculative fiction with the realities of cosmology, we uncover a wealth of lessons about the importance of curiosity, interconnectedness, the power of choice, and the ethical considerations that come with scientific progress. These narratives not only serve to expand our imaginations, but also reinforce the importance of grounding our ambitions in thoughtful reflection. As we continue to navigate the vast unknowns of the universe, we are reminded that the questions we ask and the choices we make shape not only the future of our world, but also our understanding of the cosmos itself. One of the most profound and enduring questions in cosmology remains the origin of the universe. How something can emerge from nothing. Despite the wealth of knowledge we have gained about the expansion of the universe, the formation of galaxies, and the nature of cosmic radiation, we still struggle with understanding how the universe came into being. This question is at the heart of some of the most fundamental and awe-inspiring inquiries in science. What exactly does nothing mean in this context? Does it refer to an absolute absence, an absence of space, time, and matter, or is it simply a vacuum that holds the potential for creation? Some theories suggest that quantum fluctuations, tiny random variations in energy at the subatomic level, could enable particles to spontaneously emerge from a state of nothingness. If proven correct, this theory could imply that the universe emerged as a natural consequence of quantum processes, though the exact mechanisms behind such an emergence remain unclear. Another avenue of investigation centers around cosmic inflation, a rapid expansion of space that occurred moments after the Big Bang. Some scientists hypothesize that this inflationary period might be connected to the universe's origin, though questions about its true nature remain unresolved. Furthermore, some theorists propose that our universe might be just one of many within a vast multiverse. If this idea is correct, it raises yet another intriguing question. What lies beyond our universe? Could we be one bubble in an infinite sea of universes, each governed by different physical laws and containing countless possibilities for life and existence? This question adds another layer of mystery to the puzzle of the universe's creation, and suggests that the answers we seek may be far more complex and far-reaching than we ever imagined. As we contemplate the origins of the universe, we must also consider its ultimate fate. Understanding how the universe began could provide valuable insights into its future. Will it continue to expand forever, growing colder and darker as stars burn out? Or will it eventually collapse in on itself, leading to a big crunch where all matter is pulled back into a singularity? Or perhaps the universe will transform in ways we cannot yet fathom. These are the questions that drive modern cosmologists to continue their research, seeking answers to the mysteries of existence while exploring the deeper implications of our place in the universe. The pursuit of these answers invites us to probe the very fabric of reality and the fundamental laws that govern the cosmos. As contemporary cosmologists strive to unravel the mysteries of dark matter, dark energy, and the origins of the universe, they are confronted with a landscape of unanswered questions, many of which seem as elusive as the universe itself. In determining which questions to pursue, scientists must balance the potential significance of these inquiries with the tools and technologies currently available to investigate them. To prioritize these mysteries, cosmologists often evaluate the potential for groundbreaking discoveries, the feasibility of observational methods, and the scientific importance of each question. Some mysteries, such as those related to dark energy and dark matter, are at the forefront of research due to their potential to fundamentally alter our understanding of the universe. However, some questions, despite their theoretical importance, remain out of reach due to limitations in observational technology. For example, exploring the earliest moments of the universe, just after the Big Bang, requires highly specialized instruments capable of detecting faint signals from that time, pushing the boundaries of modern scientific capabilities. This balancing act between ambition and practicality guides the direction of cosmological research, ensuring that the pursuit of knowledge remains both visionary and achievable. In the world of cosmology, there exists a spirit of collaboration that transcends borders and disciplines. Researchers within this community often share their findings, insights, and ideas, fostering an ongoing dialogue that is vital to the advancement of the field. This continuous exchange of knowledge helps to refine research priorities, guiding the exploration of the universe's greatest mysteries. Questions that ignite collective curiosity, those that present opportunities for innovative approaches or the application of emerging technologies, can quickly become focal points of investigation. The ever-evolving nature of cosmological research means that new discoveries can alter the direction of the field almost overnight. As new telescopes come online or space missions deliver fresh data, previously unconsidered questions can suddenly rise to prominence, shifting the priorities of researchers and institutions alike. This dynamic nature of research ensures that cosmologists must remain adaptable and responsive. They must continuously recalibrate their focus to align with the latest advancements in information, ensuring that their work remains relevant and impactful. In this sense, the process of prioritizing unanswered questions in cosmology is far from simple. It is an intricate balancing act, requiring scientists to consider factors such as the potential impact of a discovery, the feasibility of pursuing it, and the extent to which it encourages collaborative exploration. Ultimately, by directing their efforts toward the most promising and scientifically relevant inquiries, cosmologists aim to unravel the vast mysteries of the cosmos, advancing humanity's understanding of its place within this awe-inspiring universe. The role of skepticism in shaping cosmological research cannot be overstated. Skeptical perspectives have historically played an essential role in refining our understanding of the universe's origins. For instance, when the Big Bang theory was first proposed, there was significant skepticism surrounding the idea. This skepticism acted as a necessary filter, forcing researchers to seek out more robust evidence and develop stronger, more testable hypotheses. The questioning mindset of skeptics encourages deeper scrutiny and more rigorous validation, rather than accepting ideas at face value. This approach has led to groundbreaking discoveries such as the confirmation of cosmic background radiation, an essential piece of evidence supporting the Big Bang theory. Moreover, skepticism in cosmology often extends beyond the scrutiny of individual theories. It fosters a culture of interdisciplinary collaboration. The complexities of the universe's origins require expertise from diverse fields such as astronomy, physics, and quantum mechanics. When skeptics challenge the assumptions of one field, it encourages dialogue and cooperation across these disciplines, prompting scientists to explore new avenues of thought and develop innovative theories that enhance our collective understanding of cosmic evolution. But skepticism does more than challenge existing ideas. It opens the door to alternative possibilities. For example, the exploration of cyclic models of the universe, or the multiverse concept, has encouraged cosmologists to reconsider traditional frameworks and embrace new, potentially revolutionary ideas. In this sense, skepticism acts not as a barrier, but as a catalyst for scientific progress, driving cosmologists to think more broadly and creatively about the nature of the universe. This cyclical nature of skepticism and discovery has shaped many of the most significant moments in the history of cosmology. One of the most striking examples of this is the shift from the Earth-centered view of the universe to the Sun-centered model. Early astronomers, such as Copernicus, faced immense resistance when they proposed that the Sun, not the Earth, occupied the center of our solar system. This skepticism was grounded in long-held beliefs and observational habits that seemed to support the traditional geocentric model. However, as later scientists like Galileo used the telescope to gather new evidence, they were able to challenge these assumptions. Their willingness to question established knowledge led to a profound shift in our understanding of space and our place within it. Similarly, the discovery that our Milky Way galaxy is just one of countless others in the universe was met with skepticism when it was first proposed in the early 20th century. Many astronomers doubted the existence of galaxies beyond our own, but Edwin Hubble's groundbreaking observations of distant nebulae, later identified as separate galaxies, revolutionized our view of the cosmos. Hubble's work not only confirmed the existence of other galaxies, but also provided the first solid evidence that the universe is expanding, an insight that would lay the foundation for modern cosmological models. These historical shifts demonstrate that skepticism is not merely a force of doubt, but an essential driver of progress, challenging existing beliefs and prompting investigations into transformative discoveries. The ongoing cycle of skepticism and discovery remains a fundamental aspect of the scientific method, particularly in cosmology. By constantly questioning and reevaluating our assumptions about the universe, scientists open themselves to new insights that challenge the status quo. Curiosity, whether driven by doubt or wonder, remains the key to unlocking the mysteries of the cosmos. At the heart of the human pursuit of knowledge about the universe is an innate curiosity, an insatiable drive to understand our origins, our place in the universe, and the nature of existence itself. The idea that the universe could emerge from nothingness is a concept that both fascinates and perplexes scientists. How could such vast complexity arise from what appears to be no material substance at all? This question lies at the core of modern cosmological inquiries and drives much of the research in the field. The desire to understand how something as immense and intricate as the universe could spring from nothingness is a powerful motivator for scientists and astronomers. It compels them to explore new theoretical models and to seek answers through the study of particle physics, quantum mechanics, and cosmology. One of the leading theories about the universe's origins, the Big Bang, suggests that space and time, along with all matter and energy, began as a singularity, an infinitely dense point. The Big Bang is often described as the birth of the universe itself, but the question of how and why this event occurred remains a central puzzle. Researchers continue to explore ideas such as the quantum vacuum, where even empty space is thought to harbor fluctuations that could give rise to particles and ultimately entire universes. These theories push the boundaries of human knowledge, and each discovery raises more questions, further fueling the cycle of inquiry that drives scientific progress. Human curiosity about the cosmos is not limited to scientific inquiry alone. It is also deeply embedded in our cultural narratives. Throughout history, mythology, philosophy, and religion have all sought to explain the nature of existence and the origins of the universe. From ancient creation myths to modern scientific theories, humanity's quest for understanding has always been tied to a deeper need to find meaning in the cosmos. As our scientific tools and methods have advanced, so too has our ability to probe these profound questions with increasing sophistication. The drive to understand the universe from a state of nothingness reflects our collective desire to comprehend the very fabric of reality. It is not simply an intellectual exercise. It is a quest for meaning, for a deeper connection to the cosmos. In the process of exploring the universe, we learn not only about the stars and galaxies that populate space, but also about ourselves. This exploration forces us to confront profound questions about the nature of existence, time, and reality, leading to new insights into what it means to be human. The stories of the scientists themselves often reveal the personal motivations behind their work. One prominent astrophysicist, for example, grew up gazing at the night sky through his father's old telescope, captivated by the stars. His childhood curiosity evolved into a lifelong pursuit of astrophysics, driven by a desire to understand the stories behind each star, planet, and galaxy. For him, each twinkle in the sky represented a mystery waiting to be solved, a glimpse into the vast processes of the universe. This personal connection to the cosmos fueled his passion for research and continues to inspire others. Another scientist turned her struggle with dyslexia into a source of strength. While reading was difficult for her, she discovered a talent for visualizing the universe through art. This creative ability led her into the field of engineering, where she worked on spacecraft exploring distant worlds. Her unique perspective, shaped by both art and science, allowed her to contribute to groundbreaking advancements in space exploration. Her story exemplifies how the quest for understanding the cosmos can be driven not only by intellectual pursuits, but also by personal experiences, creativity, and resilience. Each of these scientists, with their distinct personal stories, shows how the pursuit of knowledge about the universe is not just a scientific endeavor. It is deeply intertwined with the human experience. These narratives remind us that science is not just about equations and theories. It is also about the individuals who dedicate their lives to unraveling the mysteries of the cosmos. The global nature of cosmological research further enriches this quest for knowledge. Scientists from all over the world, representing diverse cultures and backgrounds, come together to share their expertise and resources. This collaboration allows for the exchange of groundbreaking ideas that might not emerge in isolated environments. Major cosmological projects, such as space telescopes or particle accelerators, require vast amounts of funding, expertise, and technological innovation, resources that are often beyond the reach of any single nation. By pooling their efforts, countries can develop the advanced instruments needed to probe the universe's deepest mysteries. This united effort fosters an environment where knowledge flows freely across borders, enhancing our collective understanding of the cosmos and pushing the boundaries of what is possible in the study of space. Ultimately, the exploration of the universe is not a solitary endeavor. It is a collective journey driven by the curiosity, skepticism, and collaboration of scientists and individuals from all corners of the globe. Through their efforts, we continue to deepen our understanding of the universe, expanding our knowledge of its origins, its vastness, and our place within it. Global collaborations in science play an essential role in shaping a shared language, one that allows researchers across the world to communicate and collaborate effectively. This unifying aspect of scientific work is crucial when tackling some of the most complex and abstract concepts, such as dark matter or cosmic evolution. When scientists work together globally, they contribute to an evolving narrative, one that pushes the boundaries of human knowledge and facilitates future revelations about the origins and structure of the universe. Furthermore, the sharing of data between global teams accelerates the pace of scientific discovery. When research is not confined to borders and barriers, the flow of information increases, creating a more connected scientific community. For example, a single observation made by one team can trigger new questions for others, sparking a chain reaction that propels the research forward. This global exchange of knowledge, whether it's data from telescopes or findings from particle accelerators, accelerates the pace at which we understand the universe. It's through this kind of cross-border collaboration that scientists can begin to tackle questions like the universe's beginnings in more profound and insightful ways. The results are not just more discoveries. They're discoveries that have the potential to reshape how we see ourselves and the cosmos we inhabit. In this way, scientific collaboration doesn't only serve to increase knowledge, it enriches the way we think about the universe. It creates an environment in which innovation can thrive. When scientists from various disciplines and countries come together, each bringing their own expertise, a unique synergy is born. This collective effort is vital in uncovering the secrets of the universe and can ultimately bring us closer to understanding how everything began. This quest to answer the most fundamental question of all, how did the universe come to be, drives humanity forward and represents one of the purest expressions of human curiosity and intellectual pursuit. Historically, humans from different cultures have added their own perspectives on the cosmos, each enriching our understanding of the universe. These diverse views have shaped our approach to cosmology, offering new ways to interpret the stars, the planets, and the nature of existence itself. Ancient civilizations, for instance, made invaluable contributions to the field of astronomy. The Mayans, for example, were not only keen observers of the stars, but also developed intricate calendars based on their observations of celestial bodies. These calendars helped them predict eclipses and other significant astronomical events with remarkable accuracy. More importantly, the Mayans understood how the cosmos could influence their agricultural practices, aligning their crop cycles with the movements of the stars, creating a deep connection between the heavens and daily life. In a similar vein, many indigenous cultures around the world view the night sky as a tapestry of myths and stories. For them, the stars are not just distant lights in the sky, but symbols of teachings and wisdom passed down through generations. Aboriginal Australians, for instance, see the Milky Way not just as a band of stars, but as a river of stars that plays an important role in their navigation and understanding of seasonal changes. These cultural narratives are not only fascinating, but also have a profound spiritual significance that enriches scientific discourse. By integrating these cultural perspectives with modern scientific research, we can create a more holistic understanding of the universe, a blending of ancient wisdom with contemporary knowledge that opens up new avenues for exploration. Eastern philosophies such as Buddhism and Hinduism further deepen our understanding of cosmology by introducing the concept of cyclical time. These philosophies emphasize the constant state of transformation and rebirth that defines the universe. Instead of viewing time as linear and fixed, they see it as a dynamic process that continually evolves. This perspective challenges conventional models of time and existence, pushing scientists to think beyond the idea of a universe that has a clear beginning and end. By considering the universe as an entity that is perpetually in motion, scientists can approach cosmological questions with a deeper, more nuanced understanding. The blending of these cultural insights with the methods and findings of modern science provides an enriched, multifaceted approach to cosmology. It encourages collaboration across disciplines and fosters dialogue between scientists, philosophers, and cultural thinkers. Different cultures bring not only unique knowledge, but also an appreciation for the mystery and beauty of the cosmos. These diverse perspectives help shape the ongoing quest to understand our place in the universe, a journey that transcends borders and unites us all. The origin of the universe itself is a concept that captivates far more than just the scientific community. It touches on fundamental questions that resonate with everyone. Where did we come from? How did everything begin? The theory of the Big Bang, which posits that the universe began as an incredibly hot and dense point and has been expanding ever since, is not just a scientific explanation. It's a doorway to deeper philosophical reflections on the nature of existence. The story of the universe's birth sparks curiosity about the very nature of space and time. Questions like, what is space and what happened before the Big Bang? These are not just scientific queries, but existential ones that invite contemplation on the mysteries of life itself. The Big Bang Theory, while fascinating, does more than explain how the universe began. It creates a bridge between human experience and the cosmos. Every person, regardless of background or education, can look up at the night sky and wonder about the stars and galaxies. This shared experience of awe and wonder fosters a sense of connection to the universe, making it more than just an abstract concept. The story of creation invites us to think not only about how the universe began, but also about what the future holds. If the universe has been evolving for billions of years, does that mean it will continue to change forever? Or are we approaching the end of its journey? These questions challenge us to reflect on the cyclical nature of existence, as well as our own place in the larger narrative of the cosmos. In this way, the universe's origin becomes more than just a scientific puzzle. It evolves into an epic tale, a story that unites us in our shared quest to understand the mysteries of existence. It evokes wonder and awe, inspiring hope about humanity's place in the cosmos. The study of cosmology, the science of the universe and its origins, is a fascinating subject that has the power to ignite curiosity in people of all ages. It encourages us to look up at the night sky and ask the big questions. How did we get here? What lies beyond the stars? What laws govern the universe? These questions, which have puzzled humanity for centuries, are not just about science. They're about our place in the grand scheme of things. For young minds, these cosmic questions serve as a gateway to creativity, critical thinking, and scientific exploration. By learning about the origins of the universe, the expansion of galaxies, and the mysterious nature of black holes, young people are introduced to the fundamental laws that govern our reality. Every discovery in cosmology helps us understand who we are and where we fit into the vast, seemingly infinite universe. By sharing the wonders of the cosmos with the next generation, we inspire young people to pursue careers in science, technology, engineering, and mathematics, STEM, fields that are crucial for unraveling the mysteries of the universe. In addition to fueling scientific curiosity, the collaborative nature of cosmological research highlights the importance of teamwork and diverse perspectives. When young people see scientists from around the world working together on large-scale projects such as space missions or the construction of powerful telescopes, they learn an important lesson. Solving the biggest questions requires collaboration and open-mindedness. This approach fosters innovation, cultivates a sense of global citizenship, and encourages future generations to work together for the betterment of humanity. As the excitement around space exploration continues to grow, with new space missions, images of distant galaxies, and the possibility of life elsewhere in the universe, the next generation is being inspired to dream big and ask deeper questions. They are the ones who will continue the quest to understand the cosmos, and by nurturing their curiosity, we lay the foundation for a future rich with discovery and exploration. Finally, the idea that the universe could have arisen from nothing challenges traditional ideas about how existence begins. Imagine, if you will, an empty space devoid of matter or energy. This is the concept of nothing. Yet this nothing is not a complete absence of everything, but rather a state in which the laws of physics can still operate. Quantum mechanics, for instance, suggests that particles can appear and disappear in empty space, indicating that even in what we perceive as nothing, there are layers of reality that can manifest unexpectedly. This idea challenges our conventional understanding of energy and existence, suggesting that the universe itself may not need an external source to generate energy. Instead, it could have arisen from quantum fluctuations, energy changing forms in ways we are still trying to fully understand. The origins of space and time themselves also come into question within this framework. It's possible that space and time, as we understand them, did not exist before the birth of the universe. This raises profound questions about cause and effect, suggesting that the creation of the universe may not have followed the rules we typically associate with reality. This line of thought opens up exciting possibilities for how we think about existence itself and the nature of the universe. Though this is a complex and speculative area of research, it challenges us to rethink fundamental questions about reality, offering new ways to approach the mysteries of the cosmos.